In this lesson and in this series of lessons, we will introduce you to the concept of data structures. Data structure is the most fundamental and building block concept in computer science, and good knowledge of data structures is a must to design and develop efficient software systems. Okay, so let's get started. We deal with data all the time, and how we store, organize, and group our data together matters. Let's pick up some examples from our day to day life where organizing data in a particular structure helps us. We are able to search a word quickly and efficiently in a language dictionary because the words in the dictionary are sorted. What if the words in the dictionary were not sorted? It would be impractical and impossible to search for a word among millions of words. So, dictionary is organized as a sorted list of words. Let's pick up another example. If we have something like a city map, the data like position of a landmark and road network connections, all this data is organized in the form of geometries. We show the map data in the form of these geometries on a two-dimensional plane. So map data needs to be structured like this so that we have scales and directions and we are effectively able to search for a landmark and get route from one place to another. And I'll pick one more example. For something like daily cash in and cash out statement of a business, what we also call a cash book in accounts, it makes most sense to organize and store the data in the form of a tabular schema. It is very easy to aggregate data and extract information if the data is organized in these columns, in these tables. So different kind of structures are needed to organize different kind of data. Now computers work with all kind of data. Computers work with text, images, videos, relational data, geospatial data, and pretty much any kind of data that we have on this planet. How we store, organize, and group data in computers matters because computers deal with really, really large data, and even with the computational power of machines, if we do not use the right kind of structures, the right kind of logical structures, then our software systems will not be efficient. A formal definition of a data structure would be that a data structure is a way to store and organize data in a computer so that the data can be used efficiently. When we study data structures as ways to store and organize data, we study them in two ways. So I'll say that we talk about data structures as one, we talk about them as mathematical and logical models. When we talk about them as mathematical and logical models, we just look at an abstract view of them. We just look at from a high level what all features and what all operations define that particular data structure. Example of abstract view from real world can be something like the abstract view of a device named television can be that it is an electrical device that can be turned on and off. It can receive signals for satellite programs and play the audio video of the program. And as long as I have a device like this, I do not bother how circuits are embedded to create this device or which company makes this device. So this is an abstract view. So when we study data structures as mathematical or logical models, we just define their abstract view, or in other words, we have a term for this. We define them as abstract data types. An example of abstract data type can be, I want to define something called a list that should be able to store a group of elements of a particular data type, and we should be able to read the elements by their position in the list, and we should be also able to modify element at a particular position in the list. I would say store a given number of elements of any data type. So we are just defining a model. Now we can implement this in a programming language in a number of ways. So this is a definition of an abstract data type. We also call abstract data type as ADT. And if you see, all the high level languages already have a concrete implementation of such an ADT in the form of arrays. So arrays give us all these functionalities. So arrays are data types which are concrete implementation. So the second way of talking about data structures is talking about their implementation. So implementations would be some concrete types and not an abstract data type. We can implement the same ADT in multiple ways in the same language. For example, in C or C++, we can implement this list ADT as a data structure named linked list. And if you have not heard about it, we will be talking about them a lot. We will be talking about linked list a lot in the coming lessons. Okay, so let's define an abstract data type formally, because this is one term that we will encounter quite often. Abstract data types are entities that are definitions of data and operation but do not have implementations. So they do not have any implementation details. We will be talking about a lot of data structures in this course. We will be talking about them as abstract data types, and we will also be looking at how to implement them. Some of the data structures that we will talk about are arrays, linked list, stack, queue, tree, graph, and the list goes on. There are many more to study. So when we will study these data structures, we will study their logical view. We'll study what operations are available to us with these data structures. We'll study the cost of these operations, mostly in terms of time. And then definitely we will study the implementation in a programming language. So we will be studying all these data structures in the coming lessons. And this is all for this introductory lesson. Thanks for watching. In our previous lesson, we introduced you to the concept of data structures, and we saw how we can talk about data structures in two ways. One as a mathematical and logical model that we also term as an abstract data type, or ADT, and then we also study data structures as concrete implementations. In this lesson, we will study one simple data structure. We will first define an abstract view of it. We will first define it as an abstract data type, and then we will see the possible implementations. And this data structure is list. List is a common real world entity. List is nothing but a collection of objects of the same type. We can have a list of words, we can have a list of names, or we can have a list of numbers. So let us first define list as an abstract data type. So when we define abstract data type, we just define the data that we'll store, and we define the operations available with the type, and we do not go into the implementation details. Let us first define a very basic list. I want a list that can store a given number of elements of a given data type. This would be a static list. The number of elements in the list will not change, and we will know the number of elements before creating the list. We should be able to write or modify element at any position in the list, and of course we should be able to read element at a particular position in the list. So if I ask you for an implementation of such a list, and you have taken a basic course in programming, a basic introductory course, then you'll be like, hey, I know this. An array gives us all these features. All these operations are available with an array. We can create an array of any data type. So let's say if we want to create a list of integers, then we declare the array type as integer, and then we can give the size as a parameter in declaration. I can write or modify element at a particular position. The elements are a0, a1, and are accessed something like this. We all know about arrays. And then we can also read elements at particular position. The element at ith position is accessed as ai. So array is a data structure that gives us implementation for this list. Now I want a list that should have many more features. I want it to handle more scenarios for me. So I'll redefine this list here. I do not want a static list, a static collection with a fixed size. I want a dynamic list that should grow as per my need. So the features of my list are that I'll call my list empty if there are no elements in the list. I'll say the size of the list is 0 when it is empty, and then I can insert an element into the list, and I can insert an element at any position in the list and in an existing list. I can remove element from the list. I can count the number of elements in the list, and I should be able to read or write, or rather read or modify element at a particular position in the list. And I should also be able to specify the data type for the list. So I should be able to, while creating the list, I should be able to say whether this is a list of integers or whether this is a list of string or float or whatever. Now I want a data structure which is implementation of this dynamic list. So how do I get it? Well, actually we can implement such a dynamic list using arrays. It's just that we will have to write some more operations on top of arrays to provide for all these functionalities. So let us see how we can implement this particular list using arrays. Let's, for the sake of simplicity of design, assume that the data type for the list is integer. So we are creating a dynamic list of integers. What we can do is, to implement such a list, we can declare a really large array. We will define some max size and declare an array of this max size. Now as we know, the elements in the array are indexed as A0, A1, A2, and we go on like this. So what I'll do is I'll define a variable that will mark the end of the list in this array. So if the list is empty, we can initialize this variable, or we can set this variable as -1, because the lowest index possible is 0. So if end is -1, the list is empty. At any time, a part of the array will store the list. Okay, so let's say initially when the list is empty, this pointer end is pointing to index -1, which is not valid, which does not exist. And now I insert an integer into this array. And let's say if we do not give the position at which the number is to be inserted, the number is always inserted towards the tail of the list, towards the end of the list. So the list will be like, we will have an element at position 0, and now end is index 0. So at any time, end marks this variable end marks the end of the list in this array. Now if I want to insert something in the list at a particular position, let's say I want to insert number 5 at index 2, then to accommodate 5 here at this particular position, we will have to shift all the elements 1 unit towards the right. All the elements starting index 2. We need to shift all the elements starting index 2 towards the right. Okay, I just inserted some elements into the list. Let me also write the function call for these. Let's say we went in this order. We inserted 2, then we inserted 4, and then we inserted. In the end, we are inserting 5, and we will also give the position at which we want to insert. So this insert with 2 arguments would be the call to insert element at a particular position. So after all these operations, after all these insertions, this is what the list will look like. This arrow here marks the end of the list in the array. Now if I want to remove an element from a particular position, let's say I make a call to something, to the remove function. I want to remove the element 2, so I'll pass the index 0 here. I want to remove the element at index 0. So to do so, all these elements after index 0 will be shifted 1 unit towards the left or towards the lower indices, and 2 will go away. Now this end variable here is being adjusted after each insertion that we are making. So after this insertion, end will be 0, after this 1, 2, 3, and so on. After this remove, end will be 4 again. Okay, looks like we pretty much have an implementation of this list in the left that is described as an abstract data type. We have a logic of calling the list empty when we have this variable end is equal to -1. We can insert element at a particular position in the list. We can remove element. It's just that we have to perform some shifts in the array. We can count the number of elements in the list. It will be equal to end plus 1, the value in the variable end plus 1. We can read or modify element at a position. Well, this is an array, so we can definitely read or modify element at a particular position. If we wanted to choose the data type, it was just choosing the array of that particular data type. This looks like a cool implementation, except that we have one problem. We said that the array will be of some large size, some max size. But what is a good max size? We can always exhaust the array. The list can always grow to exhaust the array. There is no good max size. So we need to have a strategy for the scenario when the list will fill up the whole array. So what do we do in that case? We need to keep that into our design. We cannot extend the same array. It is not possible to do so. So we will have to create a new array, a larger array. So when the array is full, we will create a new larger array and copy all the elements from the previous array into the new array. and then we can free the memory for the previous array. Now the question is, by how much should we increase the size of the new array? This whole operation of creating a new array and copying all the elements from the previous array into the new array is costly in terms of time, and definitely a good design would be to avoid such big cost. So the strategy that we choose is that each time the array is full, we create a new larger array of double the size of the previous array. And why this is the best strategy is something that we will not discuss in this lesson. So we will create a larger array of double size and copy elements from previous array into this new array. This looks like a cool implementation. The study of data structures is not just about studying the operations and the implementation of these operations. It's also about analyzing the cost of these operations. So let us see what are the costs in terms of time for all these operations that we have in the dynamic list. The access to any element in this dynamic list, if we want to access it using index for read or write, then this will take constant time because we have an array here. And in array, elements are arranged in one contiguous block of memory. Using the starting address or the base address of the block of the memory, and the index or the position of the element, we can calculate the address of that particular element and access it in constant time. Big O notation that is used to describe the time complexity of operations. For constant time, it is written as, in terms of big O, the time complexity is written as big O of 1. If we wanted to insert element at the end of the array, end of the list, then that again will be constant time. But if we would insert element at a particular position in the list, then we will have to shift elements towards higher indices. In the worst case, we will have to shift all the elements to the right when we will be inserting at the first position. So the time taken for insertion will be proportional to the length of the list. Let's say the length of the list is n, or in other words, we will say that insertion will be big O of n in terms of time complexity. If you do not know about big O notation, do not bother. Just understand that inserting an element at a particular position will be a linear function in terms of the size of the list. Removing an element will again be big O of n. Time taken will be proportional to the current size of the list. N is the size of the list here. Okay, now inserting an element at the end, we just said that it will happen in constant time. It is not so. If the array is full, then we will create a new array. Let's call inserting element at the end as adding an element. Adding an element will take constant time if the list is not full, but it will take time proportional to the size of the list, size of the array if the array is full. So adding in the worst case will be big O of n again. As we said, when the list is full, we create a new copy, double the size of the previous array, and then we copy the previous array, the elements from previous array into the new array. So prima facie, what looks like the good thing with this kind of implementation? Well, the good thing is that we can access elements at any index in constant time, which is the property of the array. But if we have to insert some element in between, and if we have to remove element from the list, then it is costly. If the list grows and shrinks a lot, then we will also have to create a new array and have all this thing of copying elements from previous array into new array again and again. And one more problem is that a lot of time, a lot of the array would be unused. The memory there is of no use. And definitely the use of array as a dynamic list is not efficient in terms of memory. This kind of implementation is not efficient in terms of memory. This leads us to think, can we have a data structure that will give us a dynamic list and use the memory more efficiently? We have one data structure that gives us good utilization of the memory, and this data structure is linked list, and we will study about the linked lists in the next lesson. So that's it for this lesson. Thanks for watching. In this lesson, we will introduce you to linked list data structure. In our previous lesson, we tried to implement a dynamic list using arrays, and we had some issues there. it was not most efficient in terms of memory usage, in terms of memory consumption. When we use arrays, we have some limitations. To be able to understand linked list well, we need to understand these limitations. So I'm going to tell you a simple story to help you understand this. Let us say this is computer's memory and each partition here is 1 byte of memory. Now as we know, each byte of memory has an address. We are showing only a section of the memory, that's why it is extending towards the bottom and the top. Let's say the address increases from bottom to top. So if this byte is address 200, the next byte would be address 201 and next byte would be address 202 and so on. What I want to do is I want to draw this memory from left to right horizontally instead of drawing it from bottom to top like this. This looks better. Let's say this byte here is address 200 and as we go towards the right the address increases. So this is like 201 and we go on like 202, 203 and so on. It doesn't really matter whether we show memory from bottom to top or left to right. These are just logical ways to look at the memory. So coming back to our story, memory is a crucial resource and all the applications keep asking for it. So Mr. Computer has given this job of managing the memory to one of his components, to one of his guys, who he calls the memory manager. Now this guy keeps track of what part of the memory is free and what part of the memory is allocated, and anyone who needs memory to store something needs to talk to this guy. Albert is our programmer and he is building an application. He needs to store some data in the memory, so he needs to talk to the memory manager. He can talk to the memory manager in a high level language like C. Let us say that he is using C to talk to the memory manager. First he wants to store an integer in the memory. So he communicates this to memory manager by declaring an integer variable, something like this. The memory manager sees this declaration and he says that okay, you need to store an integer variable, so I need to give you 4 bytes of memory because integer variable is stored in 4 bytes in a typical architecture, and let us say in this architecture it is stored in 4 bytes. So the memory manager looks for 4 bytes of free space in the memory and assigns it or allocates it for variable x. Address of a block of memory is the address of the first byte in the memory. So let us say this first byte of memory here is at address 217. So variable x is at address 217. So memory manager kind of communicates it back to Albert that hey, I have assigned address 217 for your variable x. You can store whatever you want there. And Albert can fill in any data into this variable. Now Albert needs to store a list of integers, a list of numbers. And he thinks that the maximum number of integers in this list will be 4. So he asks the memory manager for an integer array of size 4 named A. Now array is always stored in memory as one contiguous block of memory. So memory manager is like, okay, I need to look for a block of memory of 16 bytes for this variable, this array A. So the memory manager allocates this block starting address 201 and ending address 216 for this variable A, which is an array of 4 integers. Because array is stored as one contiguous block of memory and memory manager conveys the starting address of this block, whenever Albert tries to access any of the elements in the array, let's say he tries to write some value at the 4th element in the array, which he accesses as A3, Albert's application knows where to write this particular value because it knows the base address, the starting address of the block A, the array A, and from base address using the index, which is 3 here, it calculates the address of A3. So it knows that A3 is at address 213. So to access any of the elements in the array, the application takes constant time. And this is one awesome thing about arrays, that irrespective of the size of the arrays, an application can access any of the elements in the array in constant time. Now let's say Albert uses this array of 4 integers to store his list. So I'll fill in some values here at these positions. Let's say this is 8, this is 2, this is 6, this is 5, this is 4. Now Albert at some point feels that, okay, I need to have one more element in this list. Now he has declared an array of size 4 and he wants to add a 5th element in the array. So he asks the memory manager that, hey, I want to extend my array A. Is it possible to do so? I want to extend the same block. And the memory manager is like, when I allocate memory for an array, I do not expect that you will ask for an extension. So I use whatever memory is available adjacent to that block for other variables. In some cases, I may extend the same block, but in this case, I have an element and a variable x next to your block, so I cannot give you an extension. So Albert is like, what all options do I have? Memory manager is like, you can tell me the new size and I can recreate a new block at some new address, and we will have to copy all the elements from the previous block to the new block. So Albert says that, okay, let's do it. But the memory manager is like, you still need to give me the size of the new block. Albert thinks that this time he'll give a really large size for the new array or the new block so that it does not fill up. This new block starting address 2 to 4 is allocated. Albert asks memory manager to free the previous block, and this is some cost. He has to copy all the elements, all the numbers from the previous block into the new block, and now he can add one more element to this list. And he has kept his array large this time just in case he needs more numbers in the list. So the only option that Albert had was to create A as an entirely new block, as an entirely new array. And Albert is still feeling bad because if the list is too small, he is not using some part of the array, and so memory is getting wasted. And if the list again grows too much, he will again have to create a new array, a new block, and he will again have to copy all the elements from the previous block into the new block. Albert is desperately seeking a solution to this problem, and the solution to this problem is a data structure named linked list. So let us now try to understand linked list data structure and see how it solves Albert's problem. What Albert can do is that instead of asking the memory manager for an array, which will be one large contiguous block of memory, he can ask memory for one unit of data at a time, for one element at a time in a separate request. I'm cleaning up the memory here. Once again, let's say Albert wants to store this list of 4 integers in the memory. What if he requests memory for one integer at a time? So first he pings memory manager for some memory to store number 6. Memory manager will be like, okay, you need space to store an integer. So you get this block of 4 bytes at address 204. So Albert can store number 6 here. Now Albert makes another request, a separate request for number 5. Let's say he gets this block starting address 217 for number 5. Because he makes a separate request, he may or may not get memory adjacent to number 6. Higher probabilities that he will not get an adjacent memory location. So similarly, Albert makes separate requests for number 4 and 2. So let's say he gets these 2 blocks at address 232 and 242 respectively for numbers 4 and 2. So as you can see, when Albert makes separate requests for each integer, instead of getting one contiguous block of memory, he gets these disjoint, non-contiguous blocks of memory. So we need to store some more information here. We need to store the information that this is the first element in the list and this is the second element in this list. So we need to link these blocks together somehow. With an array, it was very simple. We had one contiguous block of memory, so we knew where a particular element is by calculating its address using the starting address of the block and the position of the element in the array. But here we need to store the information that this is the first block which stores the first element, and this is the second block which stores the second element, and so on. To link these blocks together and to store the information that this is the first block in the list and this is the second block in the list, what we can do is that we can store some extra information with each block. So what if we can have 2 parts in each block, something like this, and in one part of the block we store the data or the value, and in the other part of the block we store the address of the next block. In this example, in the first block, the address part would be 217, the address of the next block that stores 5, and in this next block or the second block the address part would be 232. In the block at address 232 we will store the address 242, the address of the next block that stores number 2, and the block at 242 is the last block. There is no next block after this, so in the address part we can have address as 0. 0 is invalid address. 0 can be used to mark that this is the end of the list. There is no link to the next node or next block after this particular block. So Albert now actually has to request memory manager for a block of memory that will store two variables. One, an integer variable that will store the value of our element, and one, a pointer variable that will store the address of the next block or the next node in the list. In C, he can define a type named node like this. He will have two fields in the node, one to store the data. This field will be an integer, and one more field to store the address of the next node in the list. So Albert will ask memory for a node from the memory manager, and the memory manager will be like, okay, you need a node that needs 4 bytes for an integer variable and 4 more bytes for the pointer variable that will store the address. Pointer variable also in a typical architecture is stored in 4 bytes. So now memory manager gives us a block of 8 bytes and we call this block a node. Now notice that the second field in the node structure is node star, which means pointer to node. So this field will only store an address of the next node in the list. So if we store the list like this in the memory as these non-contiguous nodes connected to each other, then this is a linked list data structure. Logical view of the linked list data structure will be something like this. Data is stored in these nodes and each node stores the data as well as the link to the next node. So each node kind of points to the next node. The first node is also called the head node, and the only information about the list that we keep all the time is address of the head node or address of the first node. So address of the head node kind of gives us access to the complete list. The address in the last node is null or 0, which means that the last node does not point to any other node. Now if we want to traverse the linked list, the only way to do it is we start at the head, we go to the first guy, and then we ask the first guy the address of the next guy, address of the next node, and then we go to the next node and ask the address of the next node. And this is the only way to access the elements in the linked list. If we want to insert a node in the linked list, let's say we want to add number 3 at the end of the linked list, then all we need to do is first create a node in the linked list. Create a node independently and separately. It will get some memory location. So we created this node with value 3. Now all we need to do is fill the address properly, adjust these links properly. So the address of this particular node will be filled in this node with value 2, and this node, the address part can be null, so it is the last node, it does not point to any other node. Let's also show this these nodes in the memory here. So I've written the address of each node in brown at top of these nodes, and I've also filled in this address field of each node. Let's say the node for value 3 gets address 252. So this is how things will be in the memory, and this is how the logical view will be. The linked list is always identified by the address of the first node, and unlike arrays, we cannot access any of the elements in constant time. In the case of arrays, using the starting address of the block of memory and using the position of the element in the list, we could calculate the address of the element. But in this case, we have to start at the head and we have to ask this element for next element and then ask the next element who is your next. It's like playing treasure hunt. You go to the first guy and then you get the address for the second guy, and then you go to the second guy and you get the address for the third guy. So the time taken to access elements will be proportional to the size of the list. Let's say the size of the list is n. There are n elements in the list. In the worst case, to traverse the last element, you will go through all the elements. So time taken to access elements is proportional to n, or in other words, we say that this operation will cost us, or rather the time complexity of this operation is big O of n. Insertion into the list. We can insert anywhere in the list. We first need to create a node and just adjust these links properly. Like say I want 10 at third position in the list, so all we need to do is create a node, store the value 10 in the data part, something like this. Let's say we get the node 10 at address 310. So we will adjust the address field in the second node to point to this node with address 310, and this node will point to the node with value 4. Now to insert also, we will have to traverse the list and go to that particular position, and so this will be big O of n again in terms of time complexity. The only thing is that the insertion will be a simple operation. We will not have to do all the shifts as we had to do in an array. To insert something in between, we had to shift all the elements by one position towards higher indices. Similarly, to delete something from this list will also be on. So we can see some good things about linked list. There is no extra use of memory in the sense that some memory is unused. We are using some extra memory. We are using some extra memory to store the addresses, but we have the benefit that we create nodes as and when we want, and we can also free the nodes as and when we want. We do not have to guess the size of the list beforehand like in the case of arrays. We will discuss all the operations on linked list and the cost of these operations as well as comparison with arrays in our next lessons. We will also be implementing linked list in C or C++. So this is all for a basic introduction to linked list. Thanks for watching. In our previous lesson, we introduced you to linked list data structure, and we saw how linked lists solve some of the problems that we have with arrays. So now the obvious question would be, which one is better, an array or a linked list? Well, there is no such thing as one data structure is better than another data structure. One data structure may be really good for one kind of requirement, while another data structure can be really good for another kind of requirement. So it all depends upon factors like what is the most frequent operation that you want to perform with the data structure, or what is the size of the data, and there can be other factors as well. So in this lesson, we will compare these two data structures based on some parameters, based on the cost of operations that we have with these data structures. So all in all, we will comparatively study the advantages and disadvantages and try to understand in which scenario we should use an array and in which scenario we should use a linked list. So I will draw two columns here, one for array and another for linked list. And the first parameter that we want to talk about is the cost of accessing an element. Irrespective of the size of an array, it takes constant time to access an element in the array. Now, this is because an array is stored as one contiguous block of memory. So if we know the starting address or the base address of this block of memory, let us say what we have here is an integer array and the base address is 200. The first byte in this block is at address 200. Then let's say if we want to calculate the address of element at index I, then it will be equal to 200 plus I into size of an integer in bytes. So size of an integer in bytes is typically 4 bytes. So it will be 200 plus 4 into I. So if 0th element is at address 200, if we want to calculate the address for element at index 6, it will be 200 plus 6 into 4, which will be equal to 224. So knowing address of any element in an array is just this calculation for our application. In terms of big O notation, constant time is also called big O of 1. So accessing an element in an array is big O of 1 in terms of time complexity. If you are not aware of big O notation, check the description of this video for a tutorial on time complexity analysis. Now in a linked list, data is not stored in a contiguous block of memory. So if we have a linked list, something like this, let's say we have a linked list of integers here, then we have multiple blocks of memory at different addresses. each block in the linked list is called a node, and each node has two fields, one to store the data and one to store the address of the next node. So we call the second field the link field. The only information that we keep with us about a linked list is the address of the first node, which we also call the head node. And this is what we keep passing to all the functions also, the address of the head node. To access an element in the linked list at a particular position, we first need to start at the head node or the first node, and at the first node we need to see the address of the second node, and then we go to the second node and see the address of the third node. In the worst case, to access the last element in the list, we will be traversing all the nodes in the list. In the average case, we will be accessing the middle element maybe. So if n is the size of the linked list, n is the number of elements in the linked list, then we will traverse n by 2 elements. So the time taken in the average case also is proportional to number of elements in the linked list. So we can say that the time complexity in average case is big O of n. So on this parameter, cost of accessing an element, array scores heavily over a linked list. So if you have a requirement where you want to access elements in the list all the time, then definitely array is a better choice. Now the second parameter that we want to talk about is memory requirement or memory usage. With an array, we need to know the size of the array before creating it, because array is created as one contiguous block of memory. So array is of fixed size. What we typically do is we create a large enough array, and some part of the array stores our list and some part of the array is vacant or empty, so that we can add more elements in the list. For example, we have an array of 7 integers here, and we have only 3 integers in the list. Rest 4 positions are unused. There would be some garbage value there. With linked list, let's say we have this linked list of integers. There is no unused memory. We ask memory for one node at a time, so we do not keep any reserved space, but we use extra memory for pointer variables. And this extra memory requirement for pointer variables in a linked list cannot be ignored. In a typical architecture, let's say, integer is stored in 4 bytes and pointer variable also takes 4 bytes. So if you see, the memory requirement for this array of 7 integers is 28 bytes, and the memory requirement for this linked list would be 8 into 3, where 8 is the size of each node, 4 for integer and 4 bytes for the pointer variable. So this is also 24 bytes. If we add one more element to the list in the array, we will just use one more position, while in linked list we will create one more node and will take another 8 bytes, so this will be 32 bytes. Linked list would fetch us a lot of advantage if the data part is large in size. So in this case we had a linked list of integers, so integer is only 4 bytes. What if we had a linked list in which a data part was some complex type that took 16 bytes? So 4 bytes for the link and 16 bytes for the data. Each node would have been 20 bytes. An array of 7 elements for 16 bytes of data would be 16 byte for each element would be 112 bytes. And linked list of 4 would be only 80 bytes. So it all depends. If the data part for the list takes a lot of memory, linked list will definitely consume lot less memory. Otherwise, it depends what strategy we are choosing to decide the size of the array. At any time, how much array we keep unused. Now, one more point with memory allocation. Because arrays are created as one contiguous block of memory, sometimes when we may want to create a really large array, then maybe memory may not be available as one large block. But if we are using linked list, memory may be available as multiple small blocks. So we will have this problem of fragmentation in the memory. Sometimes we may get many small units of memory but may not get one large block of memory. This may be a rare phenomenon, but this is a possibility. So this is also where linked list scores. Because arrays have fixed size, once array gets filled and we need more memory, then there is no other option than to create a new array of larger size and copy the content from the previous array into the new array. So this is also one cost which is not there with linked list. So we need to keep these constraints and these requirements in mind when we want to decide for one of these data structures for our requirement. Now the third parameter that we want to talk about is cost of inserting an element in the list. Remember, when we are talking about arrays here, we are also talking about the possible use of array as dynamic list. So there can be three scenarios in insertion. First scenario will be when we want to insert an element at the beginning of the list. Let's say we want to insert number 3 at the beginning of the list. In the case of arrays, we will have to shift each element by one position towards the higher index. So the time taken will be proportional to the size of the list. So this will be big O of n. Let's say n is the size of the list. This will be big O of n in terms of time complexity. In the case of linked list, inserting an element in the beginning will mean only creating a new node and adjusting the head pointer and the link of this new node. So the time taken will not depend upon the size of the list, it will be constant. So for linked list, inserting an element at the beginning is big O of 1 in terms of time complexity. Inserting an element at end for an array, let's say we are talking about dynamic array, a dynamic list in which we create a new array if it gets filled. If there is space in the array, we just write to the next higher index of the list, so it will be constant time. So time complexity is O1 if array is not full. If array is full, we will have to create a new array and copy all the previous content into new array, which will take O(n) time, where n is the size of the list. In the case of linked list, adding an element, inserting an element at the end will mean traversing the whole list and then creating a new node and adjusting the links. So time taken will be proportional to n. I'll use this color coding for linked list. Here n is the number of elements in the list. Now the third case would be when we want to insert in the middle of the list at some nth position or maybe some ith position. Again, in the case of arrays, we will have to shift elements. For the average case, we may want to insert at the mid position in the array. So we will have to shift n by 2 elements, where n is the number of elements in the list. So the time taken is definitely proportional to n in average case. So complexity will be big O of n. For linked list also, we will have to traverse till that position and then only we can adjust the links. Even though we will not have any shifting, we will have to traverse till that point, and in the average case, time taken will be proportional to n and the time complexity will be big O of n. If you can see, deleting an element will also have these three scenarios, and the time complexity for deleting for these three scenarios will also be the same. And the final point, the final parameter that I want to talk about is which one is easy to use and implement. And array definitely is a lot easier to use. Linked list implementation, especially in C or C++, is more prone to errors like segmentation fault and memory leak. It takes good care to work with linked list. So this was arrays versus linked list. In our next lesson, we will implement linked list in C or C++. We will get our hands dirty with some real code. So this is it for this lesson. Thanks for watching. In our previous lessons, we described linked list. We saw the cost of various operations in linked list, and we also compared linked list with arrays. So now let us implement linked list. The implementation will be pretty similar in C and C++. There will be slight differences that we will discuss. The prerequisite for this lesson is that you should have a working knowledge of pointers in C, C++, and you should also know the concept of dynamic memory allocation. If you want to refresh any of these concepts, check the description of this video for additional resources. Okay, so let's get started. As we know, in a linked list, data is stored in multiple non-contiguous blocks of memory, and we call each block of memory a node in the linked list. So let me first draw a linked list here. So we have a linked list of integers here with 3 nodes. As we know, each node has 2 fields or 2 parts, one to store the data and another to store the address of the next node, what we can also call link to the next node. So let's say the address of the first node is 200 and address of the second node is 100 and the address of the third node is 300 for this linked list. This is only a logical view of the linked list. So the address part of the first node will be 100, the address of the second node, and we will have 300 here. The address part of the last node will be null, which is only a synonym or macro for address 0. 0 is an invalid address. A pointer variable equal to 0 or null with address 0 or null means that the pointer variable does not point to a valid memory location. The memory block, the address of the memory block allocated to each of the nodes is totally random. There is no relation. It's not a guarantee that the addresses will be in increasing order or decreasing order or adjacent to each other. So that's why we need to keep these links. Now the identity of the linked list that we always keep with us is the address of the first node, what we also call the head node. So we keep another variable that will be of type pointer to node, and this guy will store the address of the first node, and we can name this pointer variable whatever. Let's say this pointer variable is named A. The name of this particular pointer variable that points to the head node or the first node can also be interpreted as the name for the linked list also, because this is the only identity of the linked list that we keep with us all the time. So let us now see how this logical view can be mapped to a real program in C or C++. In our program, node will be a data type that will have 2 fields, one to store the data and another to store the address. In C, we can define such a data type as structure. So let's say we define a structure named node with 2 fields. First field to store the data. The type of the data here is integer, so this will be node for a linked list of integers. If we wanted a linked list of say double, this data type would be double. The second field will be pointer to node, struct node star. We can name this link or we can name this next or whatever. This is C style of declaring node star or pointer to node. If this was C++, we could simply write node star. I would write it this way, the C++ way. It looks better to me. In our logical view here, this variable A is of type node star or pointer to node. Each of these 3 rectangles with 2 fields are of type node, and this field in the node, the first field is of type integer and the second field is of type pointer to node or node star. It is important to know which one is what in the logical view. We should have this visualization before we go on to implement linked list. Okay, so let us now create this particular linked list of integers that we are showing here through our code. To be able to do so, we will have to implement 2 operations. One to insert a node into the linked list, one operation to insert a node in the linked list, and another operation to traverse the linked list. But before that, the first thing that we want to do is that we want to declare a pointer to the head node, a variable that will store the address of the head node. For the sake of clarity, I'll write head node here. So I have declared a pointer to node named A. Initially, when the list is empty, when there is no element in the list, this pointer should point nowhere. So we write a statement something like A is equal to null to say the same. With these 2 statements, what we have done is we have created a pointer to node named A, and this pointer points nowhere, so the list is empty. Now let's say we want to insert a node in this list. So what we do is we first create a node. Creating a node is nothing but creating a memory block to store a node. In C, we use the function malloc to create a memory block. As argument, we pass the number of bytes that we want in the block. So we say that give me a memory block that will be equal to the size of a node. So this call to malloc will create a memory block. This is a dynamically allocated memory allocated during runtime, and the only way to work with this kind of memory is through reference to this memory location through pointers. Let us assume that this memory block assigned here is at address 200. Now malloc returns a void pointer that gives us the address of assigned memory block. So we need to collect it in some variable. So let's say we create a variable named temp, which is pointer to node. So we can collect the return of malloc, the address in this particular variable. We will need a typecasting here because malloc returns void pointer and we are having temp as pointer to node. So now we have created one node in the memory. And now what we need to do is fill in the data in this particular node and adjust the links, which will mean writing the correct address in the variable a and the link field of this newly created node. To do so, we will have to dereference this particular pointer variable that we just created. As we know, if we put an asterisk sign in front of the pointer variable, we mean dereferencing it to modify the value at that particular address. Now in this case, we have a node which has two fields. So once we dereference, if we want to access each of the fields, we need to put something like a dot data here to access the data and a dot link to write to the link field. So we will write a statement like this to fill in value 2 here, and we have this temp variable pointing to this right now, and the link part of this newly created node should be null because this is the first and the last node. And the final thing that we need to do is write the address of this newly created node in A. So we will write something like A is equal to temp. Okay, temp was to temporarily store the address of the node till the time we had not fixed all the links properly. We can now use temp for some other purpose. Our linked list is intact now. It has one node. These two lines that we have written here for dereferencing and writing the values into the new node, there is alternate syntax for this. Instead of writing something like start temp bracketed dot data, we could also write temp followed by this arrow and data. We will have two characters to make this arrow, one hyphen and one this right angular bracket, right angular brace. So we can write something like this, and the same thing below we can write something like this. To create a memory block in C++, we can use malloc as well as we can use the new operator. So in C++ it gets very simple. We could simply write node start temp is equal to new node like this, and we would mean the same thing. This is a lot cleaner, and new operator is always preferred over malloc. So if you're using C++, new is recommended. So far through our program, we created an empty list by creating this pointer to the head node and assigning the value null to it initially. Then we created a node and we added this first node in this linked list. When the list is empty and we want to insert a node, the logic is pretty straightforward. When the list is not empty, we may want to insert a node at the beginning of the list, or we may want to insert a node at the end of the list, or we may even want to insert a node somewhere in the middle of the list at a particular position. We will write separate functions and routines for these different kind of insertions, and we will see running code in a compiler in our coming lessons. Let's just talk about the logic here in this whatever unstructured code I have right now. So I want to write a code to insert 2 more nodes each time at the end of the list. We actually want to create the linked list with 3 nodes having values 2, 4 and 6. That was our initial example in the beginning. Okay, so let us add 2 more nodes with values 4 and 6 into this linked list. At this stage in our code, we already have a variable temp which is pointing to this particular node. We will create a new node and use the same variable name to collect the address of this new node. So we will write a statement like this. So a new node is created and temp now stores the address of this new node, which is located at address 100 here. Once again we can set the data, and then because this is going to be the last node, we need to set the link as null. Now all we need to do is build the link of this particular node, write the address of this newly created node into the address field of this last node. To do so, we will have to traverse the list and we will have to go to the end of the list. To do so, we will write something like this. We can create a new variable temp1 which will be pointed to node, and initially we can point to the head node, point this variable to the head node by a statement like this. We can write a loop like this. Now this is generic logic to reach the end of the list. It will not be so clear if we see this logic with only one node as we have in this example. Let's draw a list with multiple nodes. So we are pointing temp1 to the first node here, and if the link part of this node is null, we are at the last node, else we can move to the next node. So temp1 equal temp1 dot link will get us to the next node, and we will go on till we reach the last node. For the last node, this particular condition temp1 dot link not equal null will be false because the link part will be null, and we will exit this while loop. So this is our code logic for traversal of the list all the way till end. If we want to print the elements in the list, we will write something like this, and we will write print temp.data inside this while loop. But right now we want to insert at the end of the list, and we are only traversing the list to reach the last node. There is one more thing that I want to point out. We are using this variable temp1 and initially storing the address in A. We are not doing something like A equal A dot link and using the variable A itself to traverse the list, because if we modify A, we will lose on the address of the head node. So A is never modified. The address of the head node, whatever variable stores the address of the head node, is never modified. Only these temporary variables are modified to traverse the list. So finally, after all this, we will write a statement like temp1.link is equal to temp. Temp1 is pointing here. So now this address part is updated and this link is built. So we have two nodes now in the list. Once again, when we want to insert node with number 6 in this list, we will have to create a new node by this logic. Then we will have to traverse the list by this logic. So we will point temp1 here first, and then the loop will move the temp1 to the end. Let's say this new block is at address 300, so this last line finally will adjust the link of the node at address 100. To insert a node at the end, there is one logic in these 4 lines if the list is empty, and there is another logic in these remaining lines if the list is not empty. Ideally we will be writing all this logic in a function. We will do that in our coming lessons. We will implement separate methods to print all the nodes in a linked list, and to insert a node at the end, we will implement a separate method to insert a node at the beginning of the list and at a particular position in the list. So this is all for this lesson. Thanks for watching. In our previous lesson, we saw how we can map the logical view of a linked list into a C or C++ program. We saw how we can implement two basic operations, one traversal of the linked list and another inserting a node at the end of the linked list. In this lesson, we will see a running code that will insert a node at the beginning of the linked list. So let's get started. I will write a C program here. The first thing that we want to do in our program is that we want to define a node. A node will be a structure in C. It will have two fields, one to store the data. Let's say we want to create a linked list of integers, so our data type will be integer. If we wanted to create a linked list of characters, then our type would be character here. So we will have another field that will be pointer to node that will store the address of the next node. We can name this variable link, or some people also like to name this variable next because it sounds more intuitive. This variable will store the address of the next node in the linked list. In C, whenever we have to declare node or pointer to node, we will have to write struct node or struct node star. In C++, we will have to write only node star, and that's one difference. Okay, so this is the definition of our node. Now to create a linked list, we will have to create a variable that will be pointer to node and that will store the address of the first node in the linked list, what we also call the head node. So I will create a pointer to node here, struct node star. We can name this variable whatever. Often for the sake of understanding, we name this variable head. Now I have declared this variable as a global variable. I have not declared this variable inside any function, and I'll come back to why I'm doing so. Now I'll write the main method. This is the entry point to my program. The first thing that I want to do is I want to say head is equal to null, which will mean that this pointer variable points nowhere. So right now the list is empty. So far what we have done here in our code is that we have created a global variable named head, which is of type pointer to node, and the value in this pointer variable is null. So far the list is empty. Now what I want to do in my program is that I want to ask the user to input some numbers, and I want to insert all these numbers into the linked list. So I'll print something like how many numbers. Let's say the user wants to input n numbers, so I'll collect this number in this variable n, and then I'll define another variable I to run the loop. And so I'm running a loop here. If it was C++, I could declare this integer variable right here inside the loop. Now I'll write a print statement like this, and I'll define another variable x, and each time I'll take this variable x as input from the user. And now I will insert this particular number x, this particular integer x, into the linked list by making a call to the method insert. And then each time we insert, we will print all the nodes in the linked list, the value of all the nodes in the linked list, by calling a function named print. There will be no argument to this function print. Of course, we need to implement these two functions, insert and print. Let me first write down the definition of these two functions. So let us implement these two functions, insert and print. Let us first implement the function insert that will insert a node at the beginning of the linked list. Now in the insert function, what we need to do is we first need to create a node. In C, we can create a node using malloc function. We have talked about this earlier. Malloc returns a pointer to the starting address of the memory block. We are having to typecast here because malloc returns a void pointer, and we need a pointer to node, a variable that is pointer to node. And then only if we dereference using an asterisk sign, then we will be able to access the fields of the node. So the data part will be x, and we have an alternate syntax for this particular syntax. We could simply write something like temp and this arrow, and it will mean the same thing, and this is more common. With these two lines in the insert function, all we are doing is we are creating a node. Let's say we get this node, and let's assume that the address that we get for this node is 100. Now there is a variable temp where we are storing the address. We can do one thing. Whenever we create a node, we can set data to whatever we want to set, and we can set the link field initially to null, and if needed we can modify the link field. So I'll write one more statement, temp.next is equal to null. Remember, temp is a pointer variable here, and we are dereferencing the pointer variable to modify the value at this particular node. Temp will also take some space in the memory. That's why I have shown this rectangular block for both the pointer variables head and temp. And node has two parts, one for the pointer variables and one for the data. So this part, the link part, is null. We can either write null here or we can write it like this. It's the same thing. Logically it means the same. Now if we want to insert this node in the beginning of the list, there can be two scenarios. One, when the list is empty, like in this case. So the only thing that we need to do is we need to point head to this particular node instead of pointing to null. So I will write a statement like head is equal to temp, and the value in head now will be address 100. And that's what we mean when we say a pointer variable points to a particular node. We store the address of that node. So this is our linked list after we insert the first node. Let us now see what we can do to insert a node at the beginning if the list is not empty, like what we have right now. Once again, we can create a node, fill in the value x here that is passed as argument. Initially we may set the link field as null, and let's say this node gets address 150 in the memory, and we have this variable temp through which we are referencing this particular memory block. Now, unlike the previous case, if we just set head is equal to temp, this is not good enough because we also need to build this link. We need to set the next or the link of the newly created node to whatever the previous head was. So what we can do is we can write something like, if head is not equal to null, or if the list is not empty, first set temp.next equal head. So we first build this link. The address here will be 100, and then we say head equal temp. So we cut this link and point head to this newly created node, and this is our modified linked list after insertion of this second node at the beginning of the list. Now one final thing here, this particular line, the third line, temp.next equal null, this is getting used only when the list is empty. If you see, when the list is empty, head is already null. So we can avoid writing two statements. We can simply write this one statement, temp.next equal head, and this will also cover the scenario when the list is empty. Now the only thing remaining in this program to get this running is the implementation of this print function. So let us implement this print function. What I will do here is I'll create a local variable which is pointer to node named temp, and I need to write struct node here. I keep missing this. In C you need to write it like this, and I want to set this as address of the head node. So this global variable has the address of the head node. Now I want to traverse the linked list, so I will write a loop like this. While temp is not equal to null, I'll keep going to the next node using this statement, temp is equal to temp.next, and at each stage I'll print the value in that node as temp.data. Now I'll write two more print, one outside this while loop and one outside after this while loop, to print an end of line. Now why did we use a temporary variable? Because we do not want to modify head, because we will lose the reference of the first node. So first we collect the address in head in another temporary variable, and we are modifying the addresses in this temporary variable using temp is equal to temp.next to traverse the list. Let us now run this program and see what happens. So this is asking how many numbers you want to insert in the list. Let's say we want to insert 5 numbers. Initially the list is empty. Let's say the first number that we want to insert is 2. At each stage we are printing the list. So the list is now 2. The first element and the last element is 2. We will insert another number. The list is now 5. 5 is inserted at the beginning of the list. Again we inserted 8, and 8 is also inserted at the beginning of the list. Okay, let's insert number 1. The list is now 1852. And finally I inserted number 10. So the final list is 101852. This seems to be working. Now if we were writing this code in C++, we could have done a couple of things. We could have written a class and organized the code in an object-oriented manner. We could also have used new operator in place of the malloc function. Now coming back to the fact that we have declared this head as global variable, what if this was not a global variable? This was declared inside this main function as a local variable. So I'll remove this global declaration. Now this head will not be accessible in other functions, so we need to pass address of the first node as argument to other functions, to both these functions, print and insert. So to this print method we will pass, let's say we name this argument as head. We can name this argument as head or a or temp or whatever. If we name this argument as head, this head in print will be a local variable of print and will not be this head in main. These two heads will be different. These two variables will be different. When the main function calls print passing its head, then the value in this particular head in the main function is copied to this another head in the print function. So now in the print function we may not use this temp variable. What we can do is we can use this variable head itself to traverse the list, and this should be good. We are not modifying this head here in the main. Similarly, to the insert function we will have to pass the address of the first node, and this head again is just a copy. This is again a local variable. So after we modify the linked list, the head in main method should also be modified. There are two ways to do it. One, we can pass the pointer to node as return from this method. So in the main method, insert function will take another argument, head, and we will have to collect the return into head again so that it is modified. Now this code will work fine. Oops, I forgot to write a return here, return head, and we can run this program like before. We can give all the values and see that the list is building up correctly. There was another way of doing this. Instead of asking this insert function to return the address of head, we could have passed this particular variable head by reference. So we could have passed insert ampersand head. Head is already a pointer to node. So in the insert function, we will have to receive pointer to pointer, node star star. And to avoid confusion, let's name this variable something else this time. Let's name this pointer to head. So to get head, we will have to write something like, we will have to dereference this particular variable and write asterisk pointer to head everywhere, and the return type will be void. Sometimes we want to name this variable as head, this local variable as head. Doesn't matter, but we will have to take care of using it properly. Now this code will also work. As you can see here, we can insert nodes, and this seems to be going well. If you do not understand these concepts of scope, you can refer to the description of this video for additional resources. So this was inserting a node at the beginning of the linked list. Thanks for watching. In our previous lesson, we had written code to insert a node at the beginning of the linked list. Now in this lesson, we will write program to insert a node at any given position in the linked list. So let me first explain the problem in a logical view. Let's say we have a linked list of integers here. There are 3 nodes in this linked list. Let us say they are at addresses 200, 100 and 250 respectively in the memory, and we have a variable head, and that is pointer to node, that stores the address of the first node in the list. Now let us say we number these nodes, we number these positions on a 1 based index. So this is the first node in the list, and this is the second node, and this is the third node, and we want to write a function insert that will take the data to be inserted in the list and the position at which we want to insert this particular data. So we will be inserting a node at that particular position with this data. There will be a couple of scenarios. The list could be empty, so this variable head will be null, or this argument being passed to the insert function, the position n, could be an invalid position. For example, 5 is an invalid position here for this linked list. The maximum possible position at which we can insert a node in this list will be 4. If we want to insert at position 1, we want to insert at the beginning, and if we want to insert at position 4, we want to insert at end. So our insert function should gracefully handle all these scenarios. Let us assume, for the sake of simplicity, for the sake of simplifying our implementation, that we always give a valid position. We will always give a valid position so that we do not have to handle the error condition in case of invalid position. The implementation logic for this function will be pretty straightforward. We will first create a node. Let's say in this example we want to insert a node with value 8 at third position in the list. So I'll set the data here in the node. The data part is 8. Now to insert a node at the nth position, we will first have to go to the n-1th node. In this case, n is equal to 3, so we will go to the second node. Now the first thing that we will have to do is we will have to set the link field of this newly created node equal to the link field of this n-1th node. So we will have to build this link. Let's say the address that we get for this newly created node is 150. Once we build this link, we can break this link and set the link of this newly created node as address of this, set the link of this n-1th node as address of this newly created node. We may have special cases in our implementation, like the list may be empty, or maybe we may want to insert a node at the beginning. Let's say we will take care of special cases, if any, in our actual implementation. So now let's move on to implement this particular function in our program. In my C program, the first thing that I need to do is I want to define a node. So node will be a structure. We have seen this earlier. So node has these two fields, one data of type integer and another next of type pointer to node. Now to create a linked list, the first thing that I need to create is a pointer to node that will always store the address of the first node or the head node in the linked list. So I will create a struct node star. Let's name this variable head. And once again, I have created this variable as a global variable. To understand linked list implementation, we need to understand what goes where, what variable sits in what section of the memory, and what is the scope of these variables, what goes in the stack section of the memory and what goes in the heap section of the memory. So this time as we write this code, we will see what goes where. In the main method, first I'll set this head as null to say that initially the list is empty. So let us now see what has gone where so far in our program, in what section of the memory. And the memory that is allocated to our program or application is typically divided into these four parts or these four sections. We have talked about this in our lesson on dynamic memory allocation. There is a link to our lesson on dynamic memory allocation in the description of this video. I'll quickly talk about what these sections are. One section of the application's memory is used to store all the instructions that need to be executed. Another section is allocated to store the global variables that live for the entire lifetime of the program, of the application. One section of the memory, which is called stack, is used to store all the information about function call executions, to store all the local variables. And these three sections that we talked about are fixed in size. Their size is decided at compile time. The last section that we call heap or free store is not fixed, and we can request memory from the heap during runtime, and that's what we do when we use malloc or new operator. Now I have drawn these three sections of the memory: stack, heap, and the section to store the global variables. In our program we have declared a global variable named head, which is pointer to node. So it will go and sit here, and this variable is like anyone can access it. Initially value here is null. Now in my program what I want to do is I first want to define two functions, insert, and this function should take two arguments: data and the position at which I want to insert a node, and insert that particular node at that position, insert data at that position in the list, and another function print that will simply print all the numbers in the linked list. Now in the main method I want to make a sequence of function calls. First I want to insert number 2. The list is empty right now, so I can only insert at position 1. So after this, insert list will be having this one number, this particular number 2, and let's say again I want to insert number 3 at position 2. So this will be our list after this insertion, and I will make two more insertions, and finally I'll print the list. So this is my main method. I could have also asked a user to input a number and position, but let's say we go this way this time. Now let us first implement insert. I'll move this print above. So the first thing that I want to do in this method is I want to create a node. So I will make a call to malloc. In C++ we can simply write a new node for this call to malloc, and this looks a lot cleaner. Let's go C++ way this time. Now what I can do is I can first set the data field and set the link initially as null. I have named this variable temp1 because I want to use another temp variable in this function. I'll come to that in a while. We first need to handle one special case when we want to insert at the head, when we want to insert at the first position. So if n is equal to 1, we simply want to set the link field of the newly created node as whatever the existing head is, and then adjust this variable to point to the new head, which will be this newly created node, and we will be done at this stage, so we will not execute any further and return from this function. If you can see, this will work even when the list is empty because the head will be null in that case. I'll show a simulation in the memory in a while, so hold on till then. Things will be pretty clear to you after that. Now for all other cases, we will first need to go to the n-1th node as we had discussed in our logic initially. So what I'll do is I'll create another pointer to node, name this variable temp2, and we will start at the head, and then we will run a loop and go to the n-1th node, something like this. We will run the loop n-2 times because right now we are pointing to head, which is the first node. So if we do this temp2 equal temp2.next n-2 times, we will be pointing temp2 to n-1th node. And now the first thing that we need to do is set the next or the link field of newly created node as the link field of this n-1th node, and then we can adjust the link of this n-1th node to point to our newly created node. And now I'm writing this print here. I've written this print here. We have used a temporary variable, a temporary pointer to node, initially pointed it to head, and we have traversed the whole list. Okay, so let us now run this program and see what happens. We are getting this output, which seems to be correct. The list should be 4, 5, 2, 3 in this order. Now I have this code. I'll run through this code and show you what's happening in the memory. When the program starts execution, initially the main method is invoked. Some part of the memory from the stack is allocated for execution of a function. All the local variables and the state of execution of this function is saved in this particular section. We also call this stack frame of a function. Here in this main method, we have not declared any local variable. We just set head to null, which we have already done here. Now the next line is a call to function insert. So the machine will set the execution of this particular method main on hold and go on to execute this call to insert. So insert comes into this stack, and insert has a couple of local variables. It has two arguments, data and this variable n. This stack frame will be a little larger because we will have a couple of local variables. And now we create this another local variable, which is a pointer to node temp1, and we use the new operator to create a memory block in the heap. And this guy temp1 initially stores the address of this memory block. Let's say this memory block is at address 150, so this guy stores the address 150. When we request some memory to store something on the heap using new or malloc, we do not get a variable name, and the only way to access it is through a pointer variable. So this pointer variable is the remote control here, kind of. So here when we say temp1.data is equal to this much, through this pointer, which is our remote, we are going and writing this value 2 here, and then we are saying temp.next equal null. So null is nothing but address 0. So we are writing address 0 here. So we have created a node, and in our first call n is equal to 1, so we will come to this condition. Now we want to set temp1.next equal head. Temp1.next is this section, this second field, and this is already equal to head. Head is null here, and this is already null. Null is nothing but 0. The only reason we set temp.next equal head will work for empty case is because head would be null. And now we are saying head is equal to temp1. So head guy now points to this because it stores address 150 like temp1. And in this first call to insert, after this we will return. So the execution of insert will finish. And now the control returns to the main method. We come to this line where we make another call to insert with different arguments. This time we pass number 3 to be inserted at position 2. Now once again, memory in the stack frame will be allocated for this particular call to insert. The stack frame allocation is corresponding to a particular call. So each time the function execution finishes, all the local variables are gone from the memory. Now once again in this call, we create a new node. We keep the address initially in this temporary variable temp1. Let's say we get this node at address 100 this time. Now n is not equal to 1. We will move on to create another temporary variable temp2. Now we are not creating a new node and storing the address in temp2 here. We are saying temp2 is initially equal to head. So we store the address 150. So initially we make this guy point to the head node. And now we want to run this loop and want to keep going to the next node until we reach n-1th node. In this case, n is equal to 2, so this loop will not execute this statement even once. N minus 1th node is the first node itself. Now we execute these two lines. The next of the newly created node will be set first, so we will build this link. Oops, no, temp2 dot the next is 0 only, so even after reset this will be 0. And now we are setting temp2 dot next as temp1, so we are building this link. And now this call to insert will finish, so we go back to the main method. So this is how things will happen for other calls also. So after everything we have inserted, when we will reach this print statement in the main function, our list will be something like this in the memory. This is a little messy. I've chosen this addresses as per my convenience for the sake of example. And now print will execute, and once again I'm using a temp variable in print. By now it should have been clear to you why we use temp variable again and again, and why this variable head that stores the address of the first node is so important. Now what if this head was not global? What if we would have declared this head inside the main method? We have talked about this in our previous lesson. Head will not be accessible everywhere, so in each call to these functions, in each call to insert, we will have to return some value from the function to update this head, or we will have to pass this head by reference. We have talked about this in our previous lesson. So this is it for this lesson. In our next lesson we will see program to delete a node at a particular position in the list. So thanks for watching. In our previous lesson, we wrote program to insert a node at nth position or a given position in a list, in a linked list. Now in this lesson, we will write a program to delete a node at any given position in a linked list. So once again, I have drawn a linked list here. We have 4 nodes in this list at addresses 100, 200, 150 and 250 respectively. So this is my example of a linked list of integers, and let's say we number the positions on a 1 based index. So this is the first node in the list, and this is the second node, this is the third node, and this is the fourth node. When we talk about deleting a node from the linked list, we will have to do 2 things. First, we will have to fix the links so that the node is no more a part of the list. Let's say in this case we want to delete the node at third position, so we will go to the second node. For nth node we will have to go to the n-1th node, and we will have to set the link part of the n-1th node as the link of the nth node, which will be the n+1th node. So we will cut this link, and now this node at address 150 is not part of the linked list, because when we will traverse the linked list, we will go from address 100 to 200, and from 200 we will go to 250. This is one scenario for deletion in which we have a node before and a node after. There will be special cases like we may want to delete the node at the first position or the head itself. In that case we will have to point head to the second node. We will have to build this link. We will talk about all these special cases in our implementation. Let's first understand the logic. Now, fixing the links is not good enough because all that we do when we fix the links is that we detach the node from the linked list so that it is no more accessible, but it is still occupying space in the memory. As we know, a node is allocated space from what we call the dynamic memory or the heap section of the memory. We have talked about this earlier. In C or C++, we have to explicitly free this memory when we are done using it because it is not automatically deallocated. And memory being a crucial resource, we do not want to consume it unnecessarily when we do not need it. So the second thing that we will have to do is we will have to free the space that's being taken by the node, and that's when the node will actually be deleted from the memory. So let us now write code for this. I'm writing my C program here. The first thing that I have done is I have defined a node which is a structure with 2 fields, one to store data and another to store address of the next node. So the second field is a pointer to node. Now to create a linked list, we will have to first create a pointer to node, a variable which is pointer to node, and that will store the address of the head node or the first node in the list. And now I want to define three functions. First, insert function that will take some value, some data to be inserted into the list, and always insert this value at the end of the list. Then I want to define a print function that will print all the elements in the list. We have defined this variable head as a global variable, so it will be accessible to all these functions. And the third function that I want to write is delete, that will take the position n of the node to be deleted and delete the node at that particular position. We will go back to implementing these methods. First I'll write the main method. So in the main method, first what I'll do is I'll set head as null, so at this stage the list is empty, and then I'll make a couple of calls to insert function to insert some integers in the list. So after this fourth insert, the list will be 2, 4, 6, 5, because we are always inserting at the end of the list. This insert function will insert the node at the end of the list. Now what I want to do in my main method is I want to ask user for a position, and I'll input this position from the console, and then I'll delete the node at this particular position, and then I'll print the whole linked list. Let's also make a call to print after all the inserts. Okay, so this is what we want to do in our main method. We want to insert 4 integers in a linked list to create a list 2, 4, 6, 5 in this order. And then I want to print the list. Then I want to input a number from the console and delete the node at that particular position. Now let us assume that we will always give a valid position, and in my implementation also I will not handle the error condition when position will not be valid. We have seen implementation of insert and print earlier, so I will not go into their implementation details. What I'll do now is I'll implement delete function. Now in my delete function, let's first handle the case when there is a node before the node that we want to delete. So we have an n-1th node. What I'll do is I'll first create a temporary variable that is pointer to node and point this to head. And using this temporary variable, we will go to n-1th node. To go to the n-1th node, we will have to run a loop n-2 times, and we will have to do something like this. temp1 is equal to temp1.next. Now what I'll do is I'll create a variable to point to the nth node, name this temp2, and this will be equal to temp1.next. And now I can fix the link. I can say that adjust the link section, the link part of n-1th node to point to n+1th node, which will be temp2.next. Now our link is fixed, and this variable temp2 stores the nth node, reference to the nth node, so we can make a call to free function. Free function deallocates whatever memory is allocated through malloc. If we were using C++ and if we would have used new operator, we should have said delete temp2. Okay, now we should be good. This much code will work for scenarios when we have an n-1th node, and even if there is no n+1th node, if n+1th position is null, this will work for that scenario. I'll leave that as an exercise for you to validate. We have not handled one special case when we want to delete the head node. So if n is equal to 1, then what we want to do is we just want to set head as temp1.next. temp1 is right now equal to head, and now head has moved on to point to the second node, and temp1 still points to the first node. So links are fixed, and we can free the first node, which is now detached from the linked list because head is now pointing to the second node. Okay, so this is our delete function. I have missed one thing here. For n not equal to 1, we should not execute this section of the code. So either we put an else statement after this, or what we can do is we can say return after we execute these statements for this condition. Now this code should work if I've got everything right. So let us now run this and see what happens. I have already written the insert and print functions. I'll come back to this main function. This is my list 2, 4, 6, 5, and I can enter any of the positions 1, 2, 3 or 4. So let's first say we want to delete the head node, and we are printing the list after deleting a particular node. So the list now is 4, 6, 5. This seems to be correct. Let us run this again, and this time I delete number 5 from position 4. The list is now 2, 4, 6, which is correct again. Similarly, if I enter position 2, the list is 2, 6, 5, which is correct. So we seem to be good. I'll quickly walk you through this code in the logical view to make things further clear. Let's say we first make a call to delete node from the first position. That is, we want to delete the head node. So in this code, what we are doing is we are first creating a variable temp1, which is pointer to node. Initially, temp1 is equal to head, so it stores the address 100, so it points to the head node. Now n is equal to 1, so we come to this instruction. Head is equal to temp1 dot next. Actually, this is temp arrow dot next, but while reading we read this as temp1 dot next. This is nothing but a syntactical sugar for this statement, asterisk temp1 dot next. So we are dereferencing this pointer variable to go to this node and then accessing the next field of this node. Now we are saying head is equal to temp1 dot next. So head is now 200. So we are building this link and breaking this link. And now in the next line we say free temp1. So we want to free the memory which is being pointed to by this variable temp1. Temp1 still points to this node at address 100. So this node now will be cleared from the memory. And now we return, so this function does not execute any further. It finishes its execution. Once the function execution finishes, temp1, which was a local variable, also gets cleared from the memory. Head is a global variable, so it does not get cleared. This is how we know the linked list. This is the identity of the linked list, this particular variable head. Let's rerun this code again, and this time I want to delete the node at third position in the list. I have drawn this initial list. So once again we create this variable temp1. We say that the address here is equal to 100. So it points to the head node or the first node. And now n is not equal to 1, it is equal to 3. So we come to this particular loop. N is equal to 3, so this loop will execute exactly once. This statement will execute exactly once. So temp1 will now move to address 200. So temp1 is now pointing to the second node. This is what we wanted to do. We wanted temp1 to point to n minus 1th node. N is 3 here. Now we create another variable, another pointer to node, temp2. And we set this guy as temp1.next. temp1.next is 150, so we set this guy as 150. So this guy points to the nth node or the third node. Now in the next line we are saying that temp1.next, this value which is 150 right now, is now temp2.next, address of the n plus 1th node or fourth node. So this guy will now be 250. So we are building this link and we are breaking this link. So we have fixed the links, and now finally we are saying that free the memory which is being pointed to by temp2. So now this third node, the memory block, will be deleted from the memory. And once this function execution finishes, all the local variables temp1 and temp2 will be cleared, and this is what the list will be. This node at address 250 will now be the third node. So this was deleting a node at a particular position in the linked list. We can also have a problem where we may want to delete a node with a particular value. You can try implementing it. In the coming lessons, we will see more problems on linked list. So thanks for watching. In our lessons on linked list, so far we have implemented some of the basic scenarios like inserting a node in linked list and deleting a node from linked list. In this lesson we will write code to reverse a linked list. This is one of the most favorite interview questions, and this is a really interesting problem. So let me first define the problem. Let's say we have been given a linked list of integers like this. So this is our input. We have 4 nodes in this linked list, at addresses 100, 200, 150 and 250 respectively. I always write these addresses in the logical view because it's really important that we visualize how things are in the memory and what is what. Like this first node that we also call the head node is being pointed by this particular variable named head. So this variable is basically storing the address of the head node. This variable is only a pointer. This is not the head node itself, and we do not have any other identity of the linked list except the address of the head node. So given a linked list like this, if we have to reverse it, and by reversing we do not mean moving around data, like we cannot move 5 at address 100, 2 at address 250 and do something like this. We actually have to adjust the links. So our output should be something like this. The head pointer should point to this node at address 250, and we should go like 250 to 150, 150 to 200, and this node at address 100 should have address 0 or null. In each of these nodes, this first field in red is the data part and the second field is the address part. So this is what we will get when we will reverse the list. There are two approaches to solve this problem. One is an iterative approach where we will be using a loop. We will traverse through the list, and at each step we will revert one of the links. Another solution is using recursion. In this lesson we will try to understand the iterative solution. So coming back to our input list, the iterative solution is relatively easier to understand. What we can do is we can traverse the whole list, and as we go to each node we can adjust the link part of that node to make it point to the previous node instead of the next node. So we will start at the first node. At each step we want to reverse the link, so we want to make the node point to the previous node instead of the next node. For the first node there is no previous node, so let's say the previous node is null, and now we want to cut this particular link and we want to build this particular link. So we will simply change the address field to 0, and we have reversed the link part of this particular node. And now we will go to the next node in the list. We will come to this node. Of course the question would be, how would we go to the next node if we have broken this link here? We will come back to that in our implementation details. Let's say we are able to traverse the list and go to each of the nodes at each step. Let's say we store all the relevant information to do that in some temporary variables. Now at this node again we will reverse the link, so the address part will be set as 100 here. Now we will go to the next node at address 150. Once again, to reverse the link we will set the address as 200 here. So we will break this link, and basically we are building this link. And now we will go to address 250, the next node. We will set the address 150 here, so we will cut this link and build this link. And finally, when we have reached the last node, we will adjust the address in this head variable to 250. So this particular variable, this particular pointer, will point to this node at address 250, and our linked list is reversed now. So let us implement this particular logic in a real C program. I will redraw the original input list. In my C code I will define node as a structure like this. This is how we have defined a node in all our previous lessons. So there will be two fields, one to store the data which will be of type integer, and another to store the address of the next node. We will name this field next, and it will be of type pointer to node. And let's say head is a global variable, so head is a pointer to node. Head is a variable which is a pointer to node, and it is a global variable, so it is accessible to all the functions. We do not need to pass it around to functions. Now all I want to do in my code is I want to write a reverse function that will reverse the linked list which is pointed to by this particular pointer head. As we said, we will traverse the whole list, and at each step we will modify the link field of the node to make it point to the previous node instead of the next node. So how do we traverse a list? We would traverse a list in our C code something like this. We will first take a variable which will be pointer to node. Let's say we will name it temp, Then first we will set temp to head. By saying this, we will make temp point to the first node, and then we will run a loop like this. We will say that while temp is not equal to null, take temp to the next address with a statement like temp is equal to temp.next. In our problem here, we don't just have to traverse the list. As we traverse the list, we have to reverse the link. So we have to set the address field of a particular node as the address of the previous node instead of the next node. Now in a linked list, we would always know the address of the next node, but we would never know the address of the previous node. So as we traverse the list, we will have to keep track of the previous node in another variable. So what I will do here is something like this. I will also declare a variable named previous and initially set it to null, because for the first node or the head node, the previous node is null. And now in my loop, we will have to update both these variables, the variable temp that will store the current node and the variable prev that will store the address of the previous node. And now in my loop I can do something like this. At each step, if temp is our current node as we are traversing the list, then we will say that temp.next is equal to previous. So we will set the link part of the current node as the address of the previous node. In our example here, at the first step, we will say that temp.next will be 0. Null is nothing but address 0. So we will cut this link and we will build this link. Now we should be able to move temp to 200 now, and we should be able to move previous to 100 now in the next step. But there is a problem. As soon as we adjusted the link of this particular node at address 100 to make it point to null, we lost the address of the next node. So how do we move temp to this particular node at address 200? We cannot say temp equal temp.next. Now if we say temp equal temp.next, now we will go to null. So this is a problem. So at each step in our iteration, before we set the link field of the current node to make it point to the previous node, we should store the address of the next node in a temporary variable, in another temporary variable. So what I'll do here is something like this. First of all, I want to name this particular variable temp as current, to mean that this is the current node at any stage in my iteration. So we initially set current to head, and then we are running the loop as while current is not equal to null. And then I have also declared one more temporary pointer variable named next. What I'll do at each step in my iteration inside the while loop is that first I'll say something like next is equal to current dot next. So first I'll store the address of the next node in this particular variable next. So in our example here, for the first node, initially things will look something like this. Now we can set the link part of the current node as address of the previous node with a statement like this. So when we will write the address 0 here initially, we will break this link and create this link. We will not lose the information about the next node. Now we can redefine our previous and current. So we will first move previous to current, and then we will move current to next. Please note that this particular variable next is a local variable in the reverse function, and when we say something like current.next, we mean the link field in the node, while when we simply say next, we mean this particular local pointer variable. So they're different. This is not current.next, actually this is current arrow next, which is an alternate syntax for asterisk current.next. So we use the asterisk operator to dereference that address, and then we access the next field. For the sake of saying, we say current.next or temp.next. So with these two lines in our loop, we are resetting our previous and current pointers. This is how we are traversing the list. If you see in the next iteration, current is 200, it is not equal to null. Null is 0. So we will go to this particular statement, next is equal to current.next. So next will now store the address 150, and now we will say current.next is equal to previous. So we will cut this link. Previous is 100 right now, so we will set 100 here. So basically we will build this particular link, and then we will first move previous to current and then move current to next. and we will go on like this. So finally we will reach a stage like this. When current will be equal to null, we will come out of the loop, and when we will come out of the loop, this particular variable previous, this particular pointer previous, will store the address of the last node. And there is one more thing remaining here. We need to adjust this particular variable head. This link at this stage does not exist, and in my code I'll say head should now be equal to the address in variable previous. So head is now 250. This is our new head, and now our list is reversed. There are a couple of things that I want to point out here. One thing is that we must see whether our implementation is working for all test cases, so we must also verify it for special or corner test cases. In this case, corner test case will be when the list is empty. In that case, head will be null, or when the list is having only one node. If you see, this particular implementation will work for these two scenarios. Give it some time and you should be able to figure it out. Let's now run this code with complete implementation of all the functions to insert and print nodes. In my code here, I have written reverse function to accept the address of the head node as argument, and then return the address of the head node after modification of the list, after reversal of the list. And then I have written the main method in which I'm declaring head as a local variable, and then I'm using a couple of insert functions. I'm making a couple of calls to insert function. Insert function also takes two arguments, the address of the head node and the data to be inserted, and it returns back the address of the head node. It could either be modified or not modified. Let's say we are inserting at the end of the list, so initially our list will be 2468, and then we are making a call to the print function, which I have written to print the elements in the list, and then I'm making a call to reverse and finally printing again. My logic of the reverse function remains the same, except that I've changed the method signature, and in the end I'm returning head, which will return the address of the head node. Let's say we have written all the other functions, insert and print, correctly. These are the two functions, insert and print. So let's now run this code and see what happens. Before the list is reversed, the output is 2468, and after the list is reversed, the output is 8642. Let us try this for the case when we have only one element in the list. So I'll comment out these three insert statements, and this also seems to be working. So this was reversal of linked list through iteration. In the next lesson we will write code to reverse linked list using recursion. So thanks for watching. In our series on linked list, so far we have implemented some of the basic operations like insertion, deletion and traversal. Now in this lesson we will write code to traverse and print the elements of a linked list using recursion. A prerequisite for this lesson is that you should understand recursion as a programming concept. Recursive traversal of linked list actually helps us solve a couple of interesting problems, but in this lesson we will keep it simple. We will just traverse and print all the elements in linked list using recursion, and we will write one simple variation to print all the elements in reversed order using recursion. We will actually not reverse the list, we will just print the elements in reversed order. So once again I have taken example of a linked list of integers here. We have 4 nodes. Each rectangle here is a node. It has 2 fields, one to store the data and another to store the address of the next node. Let's say we have 4 nodes at addresses 100, 200, 150 and 250 respectively. And of course we will also have a variable that will store the address of the head node. Let's name this variable head. Programmatically in our C or C++ program, a node will be defined something like this. We will have a structure with 2 fields, one to store the data and another to store the address of the next node. What we want to do in this particular lesson is that we want to write 2 functions. First we want to write a function named print that will take address of a node as argument. We will pass this function the address of the head node, so
let's name this argument head, and in this function we will use recursion to print the elements in the list. So for this particular example here, if we want to print a space separated list of all the elements, our output will be something like this. And we also want to write another function named reverse print. Here also we will take the address of a node, so we will pass this guy the address of the head node, and in this function we will use recursion to print the elements in the list in reversed order. So if we have to print a space separated list for this example, our output will be something like this. So let's first implement the print function. In my C code here, I'll declare print function like this. It will take as argument the address of a node, so the argument is of type pointer to node. Initially we will pass the address of the head node. We can name this argument head, or we can name this argument P. We can name it whatever, but we must understand that this will be a local variable. And let's not bother about other infrastructure in the code, like how we would create a linked list and how we would insert a node in the linked list. Let's assume that they are in place. So let's keep the name of this particular argument P. Now recursion is a function calling itself. So we have been passed the address of a node, initially the head node. So what we can do in our code is, first we can print the value at that particular node with a printf statement like this, and then we can make another call to the print function, and this time we will pass the address of the next node with a statement like this. This next field is also a pointer to node, so this will pass the address of this will be the address of the next node. There is one more important thing in recursion that we should never forget, and it's the exit condition from recursion. We should not go on making recursive calls infinitely. So in this case, if we go from the first node to the second node and from the second node to the third node using recursion, then finally at one stage P will be equal to null in one of the calls. At this stage we can avoid making a recursive call. We will exit. We will show you a simulation of how things will happen in memory. Hold on for a while. So once we will reach the end of the list, P will be equal to null, and we will exit the recursion at that stage. Now I'll write the main method. I've already written the insert function here. So I'll declare a variable head as null in the main method. So head will be a local variable. Once again, we could name this particular variable A or B or whatever. Just because this variable points to the head node or the first node in the list, we name this variable as head, and then we will insert some nodes in the linked list by making call to the insert function that takes the address of the head node as argument. Initially head is set as null to say that the list is empty, and there should be two arguments to head, to the function insert, the address of the head node and the value that needs to be inserted. And why is it that this particular function insert is returning a pointer? It's because this head in the main method is a local variable, and if we pass it to the function, we just pass a copy of the address of the head node in this head, which will be a local variable of insert function. So this guy returns back the address of the modified head, so we can update it in the main function. This function inserts a node at the end of the list. So initially when head is null, head will be modified in the insert function. For other cases it will not be modified if we are inserting at the end. So we will make 4 such calls to the insert function to create a linked list of 4 integers 2, 4, 6, 5. And now we will make a call to print function and pass it the address of the head node. Let us now run this code and see what happens. As you can see, we have got this output 2, 4, 6, 5. The print function here in our code, which is a recursive implementation to print the lists, is working. Now I'll make one slight change in the print function. Instead of printing the value in the node and then making a recursive call, I'll first make a recursive call, and then when the recursive call finishes, I'll print the value in the node, and I'll not modify anything else in the code. The main method will remain the same, and if we run this code, we can say we can see that the elements in the list are printed in reversed order. So we just implemented the reverse print function that we had talked about. Let us now analyze these two recursive implementations in a logical view. In our example here, if we want to print this particular list, we will do something like, from the main method we will make a call to the print function passing it the address of the head node. So initially this print function is being called with p equal 100. Now in the execution of this function we will come here, if p is equal to null, null is address 0 and our argument is 100, so control will not go inside this if condition. We will come here, we will print p arrow data. P arrow data means that we will first dereference the address, so we will go to the address 100 and then we will look at the data field there. So on the console we will print the data field of at address 100, and now we will make a recursive call. We will make a call to print function passing it address p arrow next, which is 200, and the execution of this particular call will not finish. It will finish only after print 200 finishes. We will come back to it. Now print 200 once again prints the data at address 200 and then makes a recursive call to print function passing address 150, and we will go on like this. In this call to print with address 250, we will first print the data, and the address field, the value of p dot next, p arrow next, is 0, what we can also say null, so we will make a call like this. Now for this call with argument null, we have reached the exit condition. Recursion will not grow any further, so we will just print an end of line and return. This particular structure that we have drawn here is called recursion tree. So print null function call will finish and control will return back to print 250. There is no statement after this particular recursive call finishes, so we will simply exit this function call also, and control will return back to print 150, and we will go on like this. Finally we will come back to the main method. If you want to see how the recursion will execute in the memory, then I'll have to draw a diagram like this. Applications memory, the memory that is allocated for the execution of a program, has these two sections. All the details of function call execution and the local variables, they are stored in the stack section of the memory, and any memory that is allocated using the malloc function or the new operator in C++, they go into the heap section. The memory for the nodes in a linked list is allocated from the heap, so that's why these 4 nodes in our example are sitting in the heap. If you want to know in detail about stack and heap, check the description of this video for a lesson on dynamic memory allocation. When the program will start executing, first the main function will be invoked. Anytime a function is invoked, some amount of memory from the stack is allocated for the execution of that particular function. It's called the stack frame of that function. So let's say main is executing. We have already inserted some nodes in the linked list. We have this variable head in the main function, so all the local variables sit in the stack frame of the function. So head will sit here. Now at this stage, let's say main makes a call to print function. So main was executing and now it makes a call to print function. Execution of main will be paused, and we will go on to execute the print function. The argument passed to the print function is 100, which is stored in a local variable. This argument p is a local variable in the print function. Now print function again makes a recursive call. Now stack frame is always allocated corresponding to each call of a function. So a function calling itself is not different from a function calling another function. At any time, whatever function call is at the top of the stack is executing. Finally, when we will reach the exit condition of the recursion, stack will be something like this. And then first this call where p is 0 will finish. We will come back to this particular call, and then this will finish, and we will go on like this. So this is how recursion works. This is how things will happen in the memory. Okay, so now I'll clear this diagram of stack and heap in the right, and I'll make some change in my print function. What I've done is I have renamed my function print as reverse print, and in my function I'm first making a recursive call, and after coming back from that recursive call I'm writing a print statement, and from the main function I'll make a call to reverse print. Let's write RP as shortcut for reverse print, and initially I'll pass the address of the head node, so I'll make a call like this, reverse print 100. The control will come inside this function. P is 100, it is not equal to null, and I've also drawn the console like before. Now this particular function call does not print first, it first makes a recursive call. So this guy will go ahead and make a recursive call to the reverse print function, passing it address 200. Nothing will be written on the console, and once again this particular function will make a recursive call like this, and once again this particular function will go ahead and make a recursive call like this, and finally we will have a recursive call where the function is passed address null. At this stage we will come to the exit condition in the recursion. The recursion will not grow any further. We will simply return, the control will return to this particular call, reverse print 250. So we will come here now to this printf statement. The data field at address 250 is 4, so 4 will be printed on the console, and now this particular function call will finish, and we will go to reverse print 150, and now this call will print 5 and exit, and we will go on like this. Finally we will return back to the main function with this output on the console, the elements of the list printed in reversed order. So this was recursive traversal of linked list to print its elements. I must point out here that for normal traversal of the linked list, not for the reverse print, for the normal print an iterative approach will be a lot more efficient than the recursive approach, because in iterative approach we will just use one temporary variable, while in recursion we will use space in the stack section of the memory for so many function calls. So there is implicit use of memory there. For reverse print operation we will anyway have to store elements in some structure, so if we use recursion it's still okay. In the coming lessons we will solve more problems, more interesting problems on linked list. So thanks for watching. In our previous lesson we saw how we can traverse a linked list using recursion. We wrote code to print the elements of linked list in forward as well as reverse order using recursion. We did not actually reverse the list, we just printed the elements in reverse order. Now in this lesson we will reverse a linked list using recursion. This is yet another famous programming interview question. So if we have an input list like this, we have a linked list of integers here. We have 4 nodes in the linked list. Each rectangular block here with 2 partitions is a node. First field is to store the data, and another to store the address of the next node. The second field stores the address of the next node, and of course we will have one variable to store the address of the first node or head node. We name that variable head. We may name it anything. I have named it head. So this is our input list, and after reversal our output should be like this. This variable head should store the address of the last node in the original list. The last node in the original list was at address 250, and we will go like from 250 to 150, 150 to 200, 200 to 100, and 100 to null. Null is nothing but address 0. We have already seen how we can reverse a linked list using iterative method in one of our previous lessons. Let us now see how we can solve this problem using recursion. In our solution we must reverse the list by adjusting the links, by reversing the links, not by moving around data or something. So let us first understand the logic that we can use in our recursive approach. If you remember from our previous lesson where we had used recursion to print the list backward, print the elements in reverse order, then recursion gives us a way to traverse the list backward. In our C or C++ program, programmatically node will be a structure like this. So let's first look at the function from the previous lesson, the recursive function that was used to print the list backward. To this function we pass the address of a node. Initially we pass the address of the head node, and we have this exit condition. If the address passed is null, then we simply return, else we make a recursive call and pass the address of the next node. So main method will typically call reverse print, passing it the address of the head node, and this guy will first make a recursive call, and then when this recursive call finishes, then only it will print. So I'm writing RP as shortcut for reverse print. So the recursion will go on like this, and when it reaches this particular call, when argument is null, it will return. So this call will finish, and again the control will come to this call with address 250 as argument, and now we are printing the value of the node at address 250, which will be 4, and then this guy finishes, and then we go ahead and print 5, and similarly we then go on to print 6 and 2. So recursion kind of gives us a way to first traverse the list in the forward direction and then traverse the list in the backward direction. So let us now see how we can implement reverse function using recursion. Let's say, for the sake of simplicity in implementation, that head is a global variable, so it is accessible to all the functions. Now we will implement a function named reverse that will take the address of a node as argument. Initially we will pass address of the head node to this function. Now I want to do something like this in my recursion. I want to go on till the end. I want to go on making a recursive call till I reach the last node. For the last node, the link part will be null. So this is my exit condition from recursion. This exit condition is what will stop us from going on infinitely in a recursion. And what I'm doing here is something very simple. As soon as I'm reaching the last node, I'm modifying the head pointer to make it point to this guy. So the recursion will work like this. From the main method we will call the reverse function, passing it the address of the head node, address 100. We will come and check this condition. If p.next is equal to null, no, it is equal to 200 for the node at address 100. So this recursion will go on till we reach this call to reverse, passing it address 250. And now we will come down, and now we have come to this exit condition, and now head will be set as p, and the list will look like this. And now reverse 250, the call to reverse 250 will finish, and we will come back to reverse 150. There is no statement here after this recursive call to reverse function. If there were some statements here, then they would have executed now for reverse 150 after we would have come from reverse 250, and that's how we actually traverse the list in reverse order. If you see, when reverse 250 has finished, the node till 250 is already reversed because head is pointing to this node and the link part of this node is set as null. So till 250 we are already reversed. Now when we come to 150, we can make sure the list is reversed till 150 when we finish the execution of reverse 150. To do that, we can write statement like this. We will have to do two things. We will have to cut this node and make this guy point to this guy. So we will build this link, and we would have to cut this link and make this guy point to null, and that's how node till address 150 will be reversed after we finish this call. So I've written these 3 lines in my function that will execute after the recursive call. So they will execute when the recursion is folding up and we are traversing the list in the backward direction. So when we are executing reverse 150 and we have come back to it after recursion, we are at this particular line. So p would be 150 and q would be p.next. So q would be 250. So this guy is p and this guy is q, and we are saying that set q.next is equal to p. So we will set this particular field as 100. So we are building this link and cutting this link, and now we are saying that set p.next equal null. So we are building this link, making p.next null, and now this call to reverse 150 finishes, and when this call has finished, the list till 150 is reversed. As you can see, head is 250, so from 250 we will go to 150, and 150, from 150 we are going to null. So till 150 we have a reversed list. So this is how things will look like when the call to reverse 200 finishes. Till 200 we have a reversed list, and once again we come to execution of reverse 100. And this is how things will look like finally when reverse 100 will finish, and we will return back to the main function. We had seen in the previous lesson that how things will happen in the memory when recursion executes. In recursion we save the state of execution of all the function calls in stack section of the memory. In this function all we are doing is basically we are storing the addresses of node in a structure as we go forward in recursion, and then we first work on the last node to make it part of the reversed list, and then we once again come back to the previous node, and we keep doing this. Watch the previous lesson for detailed explanation and simulation of how things will happen in the memory for recursion. There are a couple of more things here. One thing is that instead of writing these two lines, I could write one line for these two lines. I could say something like p arrow next equal p, and that would have meant the same, except that this statement is more obfuscated. And there is one more thing. We have assumed that head is a global variable. What if head is not a global variable? This reverse function will have to return the address of the modified head. I leave that as an exercise for you to do. So this was reversing a linked list using recursion. Thanks for watching. Hello everyone. In our lessons in this series so far, we have discussed linked list quite a bit. We have seen how we can create a linked list and how we can perform various operations with linked list. Linked lists, as we know, are collections of entities that we call nodes. So far, in all our implementations, we have created linked lists in which each node would contain two fields, one to store data and another to store address of the next node. Let's say we have a linked list of integers here, so I'll fill in some values in data field of each node. Let's assume that these nodes are at addresses 200, 250 and 350 respectively. I'll also fill in the address field in each node. The address field in first node will be the address of second node, which is 250. The address field in second node will be address of third node, which is 350, and address part in third node will be 0 or null. The identity of a linked list that we always keep with us is the address of head node or reference to head node. Let's say we have a variable named head only to store the address of the head node. Remember, this variable named head is only a pointer to the head node. Ideally we should have named this something like head pointer. It's only pointing to the head node, it's not the head node itself. Head node is this guy, the first node in the linked list. Okay, so right now in the linked list that we are showing here, each node has only one link, a link to the next node. In a real program, node for the linked list that I'm showing here will be defined like this. This is how we have defined nodes so far in all our lessons. We have two fields here, one of type integer to store data and another of type pointer to node, struct node asterisk. I'm calling this field next. When we say linked list, by default we mean such a list that we can also call singly linked list. What we have here is a singly linked list. What we want to talk about in this lesson is idea of a doubly linked list. The idea of a doubly linked list is really simple. In a doubly linked list, each node would have two links, one to the next node and another to the previous node. Programmatically, this is how we will define node for a doubly linked list in C or C++. I have one more field here, which once again is a pointer to node, so I can store the address of a node. I can point to a node using this field, and this field will be used to store the address of the previous node. In a logical representation, I will draw my node like this now. I have one field to store data, one to store address of previous node, and one to store address of next node. Let's say I want to create a doubly linked list of integers. I have created 3 nodes here. Let's say these nodes are at addresses 400, 600 and 800 respectively. I'll fill in some data. Let's say the cell in the middle in each node is to store data. The rightmost cell is, let's say, to store the address of the next node. So for first node, this field will be 600, which means we have a link like this. For second node, this field will be 800. For third node, this field will be 0. For first node, there is no previous node, so this leftmost cell, which is supposed to contain the address of the previous node, will be 0 or null. The previous node for second node will be 400, and the previous node for the third node is the node at address 600. And of course we will have a variable to store the address of the head node. Okay, so what we have here is a doubly linked list of integers with 3 nodes. Okay, so with this much you already know doubly linked list. If you have ever implemented a singly linked list, then it should not be very difficult implementing a doubly linked list. One obvious question would be, why would we ever want to create a doubly linked list? What are the advantages or use cases of a doubly linked list? First advantage is that now if we have a pointer to any node, then we can do a forward as well as reverse lookup. With just one pointer we can look at the current node, the next node as well as the previous node. I am showing a pointer named temp here. If temp is a pointer pointing to a node, then temp.next is a pointer pointing to the next node. It's the address of the next node. And temp.previous, or rather temp arrow previous, this is actually a syntactical sugar for asterisk temp.prev. So this guy temp arrow prev is previous node, or in pure words, pointer to previous node. The value stored in temp for this example right now is 600, temp.next is 800, and temp.prev is 400. In a singly linked list, there is no way you can look at the previous node with just one pointer. You will have to use an extra pointer to keep track of the previous node. In a lot of scenarios, the ability to look at the previous node makes our life easier. Even implementation of some of the operations like deletion becomes a lot easier. In a singly linked list, to delete a node you would need 2 pointers, one to the node to be deleted and one to the previous node. But in a doubly linked list, we can do so using only one pointer, the pointer to the node to be deleted. All in all, this ability that we can do a reverse lookup in the linked list is really useful. We can flow through the linked list in both directions. Disadvantage of doubly linked list is that we are having to use extra memory for pointer to previous node. For a linked list of integers, let's say integer takes 4 bytes in a typical architecture, and pointer also takes 4 bytes, pointer variable also takes 4 bytes, then in a singly linked list, each node will be 8 bytes, 4 for data and 4 for link to the next node. In a doubly linked list, each node will be 12 bytes. We will take 4 bytes for data and 8 bytes for links. For a linked list of integers, we will take twice for links than data. With a doubly linked list, we also need to be more careful while resetting links. While inserting or deleting, we need to reset a couple of more links than a singly linked list, and so we are more prone to errors. We will implement doubly linked list in a C program in next lesson. We will write basic operations like traversal, insertion and deletion. This is it for this lesson. Thanks for watching. In our previous lesson we saw what doubly linked lists are. Now in this lesson we are going to implement doubly linked list in C. We are going to write simple operations like insertion, traversal and deletion. In a doubly linked list, as we saw in our previous lesson, each node contains 3 fields. I have drawn logical representation of a doubly linked list here. One to store data, one to store address of next node, and one to store address of previous node. For a linked list of integers, node will be defined like this in a C or C++ program. In the logical representation, I'll fill in some data in each node. Let's say these nodes are at addresses 400, 600 and 800 respectively. I'll also fill in next and previous fields, and we must also have a pointer variable pointing to the head node. Quite often we name this pointer variable head. In my implementation, I'm going to write these functions. I'm going to write a function to insert a node at beginning or head of linked list. This function will take an integer as argument. I'll write another function to insert a node at tail of linked list. I'll write one function to print elements in linked list while traversing it from head to tail. I'll write another one to print the elements in reverse order while traversing the list from tail to head. Reverse print function will validate whether reverse link for each node is created properly or not. Let's now write these functions in a real C program. In my C program here, I have defined node as a structure with 3 fields. First field is of type integer to store data. Second field is of type pointer to node to store reference of next node. And the third field is a pointer to node to store the reference of previous node. I have defined a variable named head, which once again is a pointer to node, and I have defined this variable in global scope. Head is a global variable. When we define a variable inside a function, it's called a local variable. The lifetime of a local variable is lifetime of a function call. It's created during a function call execution and it's cleared from the memory when function call execution finishes. But global variables live in the memory for whole lifetime of an application. They live till the time program is executing. Global variables can be accessed everywhere in all functions. Local variables are not accessible everywhere unless you access them through pointers. In all our previous implementations, we have mostly declared head as global variable. Okay, so let's now write the functions. The first function that I want to write is insert at head. This function will take an integer as argument. The first thing that we want to do here is we want to create a node. We can always declare a node like this. Just like declaration of any other variable, we can say struct node, and then we can give an identifier or name. And now in this my node that I have created, I can fill in all the fields. But the problem here is that when I'm creating a node like this, I'm creating it as a local variable, and it will be cleared from memory when function call will finish. A local variable lives in what we call stack section of application's memory, and we cannot control its lifetime. It's cleared from memory when function call finishes. We do not want this. Our requirement is that a node should be in memory unless we explicitly remove it. So that's why we create a node in dynamic memory, or what we call heap section of memory. Anything in heap is not cleared unless we explicitly free it. To create a node in heap, we use malloc function in C or new operator in C++. All malloc function does is it reserves some memory in heap, and this memory can be used for writing anything, any variable, any object. Access to this memory always happens through a pointer variable. We have talked about this concept quite a bit in our previous lessons, but I keep on repeating because this is a really important concept. So here with this statement, I have created a node in dynamic memory or heap that can be referenced through a variable which is pointer to node. I have named this variable temp. Now I can use this pointer variable to fill in values in various fields of the node. I'll have to dereference this pointer variable using asterisk operator, and then I can access various fields like data, prev, or next. There is an alternate syntax for this asterisk temp.data. We can simply write temp arrow data, and similarly I can access other fields also. So to access prev field, I can say temp arrow prev. Let's set this as null, and let's also set the next field as null. If you want to understand or refresh the concept of stack and heap in memory, then you can check the description of this video for a link to our lesson on dynamic memory allocation. Okay, so in my function insert at head, I have created a node in heap section of memory, and I'm referencing that node using this pointer variable named temp. Temp is not a very meaningful name. Let's use a name like new node or new node pointer. I would like to separate out this logic of node creation, these lines for node creation, in a separate function. I've written a function here named getNewNode that will take an integer as argument, create a node, filling in data field as x, and setting both previous and next pointers as null. This function will return a pointer to nodes, so I will return new node from here. I'm writing a separate function because I can avoid duplicate code by using a separate function for creation of node, because I'm going to create a node for function insert at head as well as in function insert at tail that I'll be writing after some time. Now in insert at head function, I can simply call this function get new node, passing it x. This function is returning a pointer to newly created node that I'm going to receive in this variable, which once again is a pointer to node named temp. We can name this variable also as new node. This new node in insert at head is different from this new node in get new node. These are local variables. This new node is local to insert at head and this new node is local to get new node. Now there will be two cases in insertion at head. List could be empty, so head will be equal to null. In this case we can simply set head as the address of new node and return or exit. Things will be clear if I'll show everything in logical view also. Right now my linked list is empty here. In this logical view that I'm showing, let's say I have made a call to insert at head passing it number 2. Get new node function will give me a new node. Let's say a new node is created at address 400. With this statement head equal new node, we are setting the address stored in new node variable in head. Null is nothing but address 0. As soon as this function insert at head will finish, this variable new node will be cleared from memory. But the node itself will not be cleared. If we would have created node like this, struct node new node, and in this declaration new node is not pointer to node, it's node. We are not saying struct node asterisk. So if we would have created node like this, the node also would have been cleared. Okay, coming back to the function here, let's write rest of the logic. To insert a node when list is not empty, this is what I'll do. Now I'm making a call to insert at head passing it number 4. Once new node is created, I'll first set the previous field of existing head node as the address of this new node. So I'm building this link. Then I'll set the next field of new node as the address of current head. And now I can break this link and build this link. So I'll set head as address of new node. This is how things will look like finally. Let's also quickly see how things will actually move in various sections of application's memory. The memory that is allocated to a program is typically divided into these 4 segments. We have seen this diagram quite a bit in our earlier lessons. Code or text segment stores all the instructions to be executed. There is a segment to store global variables. There is a section that we call stack that is used just like Scratchpad or whiteboard for function call execution. Stack is where all the local variables go, and not just local variables, all the information about function call execution. Heap is what we also call dynamic memory. I'm showing stack, heap and global sections separately here. In our program we had declared head as a global variable. Initially for an empty list we'll set head as null or 0. Let's say we will do that in main function. Now when a call to insert at head is made at this stage, let's say I'm making a call passing number 2 as argument. Let's say we are making a call to insert at head from main function. When program starts execution, first main function is invoked. Whenever a function is invoked, some amount of memory from the stack is allocated for execution of that function. That section is called stack frame of that function, and all the local variables of that function live inside its stack frame. When function call execution finishes, the stack frame is reclaimed. When main will make a call to insert at head, the execution of main will pause at the line where it's making a call. A stack frame will be allocated for execution of insert at head. I'm writing shortcut IAH for insert at head because I'm short of space here. All the arguments of insert at head, all the local variables will live inside this stack frame. We are creating a variable named new node, which is a pointer to node as local variable, and we are making a call to get new node function. Execution of insert at head will pause and we will go on to execute get new node. We could write get new node like this. Here I'm creating a node on stack. X is a local variable in get new node also. Then I'm creating a node filling in data as the value of X, which is 2. I'm setting previous and next fields as null or 0. And then because I need to return a pointer to node, I have used ampersand operator here. Using ampersand operator gives us pointer to a variable. Let's say this new node that we have in the stack frame of get new node has address 50. With this return when get new node will finish, the value in this new node of insert at head will be 50. Please note that with this code, this new node in get new node function is of type struct node, while this new node in insert at head is of type pointer to struct node. So they are different types. We can return this address 50, that's fine, but the stack frame for get new node will be reclaimed once the function finishes. So now even though you have the address 50, there is no node there. We cannot control allocation and deallocation of memory on stack. It happens automatically. That's why we use the memory on heap. If I'm using this code for creation of new node, then what I'm doing is I'm declaring this variable new node not as struct node but as struct node asterisk, that is pointer to node. I'm using malloc to create the actual node in heap section. Let's say I'm getting address 400 for this node. Now for a section of memory in heap, for something in heap, we cannot have a direct name. The only way to access something in heap is through a pointer. If we will lose this pointer, we will lose this node. Okay, so now what we are doing is using this pointer new node, which is local to get new node function. We are accessing this node, filling in data, filling in address fields, and now we are returning this address 400. Now when get new node is finishing, I am collecting the return, this address 400 in this variable, in this local variable new node. We are returning back to insert at head function at this line. Head at this stage is null. So now we are saying that set head is equal new node. Head is a global variable. It's not going to be cleared for whole lifetime of application. And now we are returning stack frame of insert at head will be cleared. And this is what we finally have. When we will make another call to insert at head, once again fresh stack frames will be allocated. In the execution of functions, appropriate links will be created, so our linked list will be modified accordingly. I hope all of this is making some sense. With another call to insert at head, when everything will finish and control will return back to main, we can have a picture like this. Let's say I got a node at 600. Right cell is for next node, right cell is storing the address of next node, and left cell is storing the address of previous node. So this is what we will have. Let's now go and write rest of the functions. Print function will be same as print for singly linked list. We will take a temporary pointer to node, initially set it to head, and then we will use this statement temp equal temp.next to go to the next node, and we will keep on printing. In reverse print, we will first go to the end node of the list using next pointer, and then we will traverse backward using this statement temp equal temp arrow prev. So we will use the previous pointer, and while traversing backward we will print the data. Okay, let's now test all these functions that we have written so far. In the main function, I'm setting head as null to say that the list is empty initially, and now I'm writing a couple of insert statements. I'm making a couple of calls to insert at head function, and after each call I'm printing the list both in forward as well as reverse direction. Let's run this code and see the output. This is what I'm getting, and I think this is as expected. There is one more function, insert at tail, that I had said I'll write. If you have understood things so far, it should not be very difficult for you to write this function, insert at tail. I leave this as an exercise for you. I'll stop here now. If you want to get this source code, check the description of this video for a link. In coming lessons, we are going to talk about circular linked list, and we will see some more interesting problems on linked list. Thanks for watching. In this lesson, we are going to introduce you to stack data structure. Data structures, as we know, are ways to store and organize data in computers. So far in this series, we have discussed some of the data structures. We have talked about arrays and linked lists. Now in this lesson, we are going to talk about stacks. And we are going to talk about stack as abstract data type, or ADT. When we talk about a data structure as abstract data type, we talk only about the features or operations available with the data structure. We do not go into implementation details. So basically, we define the data structure only as a mathematical or logical model. We will go into implementation of stack in later lessons. In this lesson, we are going to talk only about stack ADT. So we are only going to have a look at the logical view of stack. Stack as a data structure in computer science is not very different from stack as a way of organizing objects in real world. Here are some examples of stack from real world. First figure is of a stack of dinner plates. Second figure is of a mathematical puzzle called Tower of Hanoi, where we have 3 rods or 3 pegs and multiple discs, and the game is about moving a stack of discs from one peg to another with this constraint that a disc cannot go on top of a smaller disc. Third figure is of a pack of tennis balls. Stack basically is a collection with this property that an item in the stack must be inserted or removed from the same end that we call the top of stack. In fact, this is not just a property, this is a constraint or restriction. Only the top of a stack is accessible, and any item has to be inserted or removed from the top. A stack is also called last in first out collection. Most recently added item in a stack has to go out first. In the first example, you will always pick up a dinner plate from top of the stack, and if you will have to put a plate back into the stack, you will always put it back on top of the stack. You can argue that I can slip out a plate from in between without actually removing the plates on the top. So the constraint that I should take out a plate always from the top is not strictly enforced. For the sake of argument, this is fine. You can say this. In other two examples, when we have discs in a peg and tennis balls in this box that can open only from one side, there is no way you can take out an item from in between. Any insertion or removal has to happen from top. You cannot slip out an item from in between. You can take out an item, but for that you will have to remove all the items on top of that item. Let's now formally define stack as an abstract data type. A stack is a list or collection with the restriction that insertion and deletion can be performed only from one end, that we call the top of stack. Let's now define the interface or operations available with stack ADT. There are 2 fundamental operations available with a stack. An insertion is called a push operation. Push operation can insert or push some item X onto the stack. Another operation, second operation, is called pop. Pop is removing the most recent item from the stack, most recent element from the stack. Push and pop are the fundamental operations, and there can be few more. Typically there is one operation called top that simply returns the element at top of the stack, and there can be an operation to check whether a stack is empty or not. So this operation will return true if the stack is empty, false otherwise. So push is inserting an element on top of stack, and pop is removing an element from top of stack. We can push or pop only one element at a time. All these operations that I have written here can be performed in constant time, or in other words, their time complexity is big O of 1. Remember, an element that is pushed or inserted last onto a stack is popped or removed first. So stack is called last in first out structure. What goes in last comes out first. Last in first out, in short, is called LIFO. Logically, a stack is represented something like this, as a 3-sided figure, as a container open from one side. This is a representation of an empty stack. Let's name this stack S. Let's say this figure is representing a stack of integers. Right now the stack is empty. I will perform push and pop operations to insert and remove integers from the stack. I will first write down the operation here and then show you what will happen in the logical representation. Let's first perform a push. I want to push number 2 onto the stack. The stack is empty right now, so we cannot pop anything. After the push, stack will look something like this. There is only one integer in the stack, so of course it's on top. Let's push another integer. This time I want to push number 10. And now let's say we want to perform a pop. The integer at top right now is 10. With a pop, it will be removed from the stack. Let's do few more push. I just pushed 7 and 5 onto the stack. At this stage, if I will call top operation, it will return me number 5. Is empty will return me false. At this stage, a pop will remove 5 from the stack. As you can see, the element, the integer which is coming last, is going out first. That's why we call stack last in first out data structure. We can pop till the stack gets empty. One more pop and stack will be empty. So this pretty much is stack data structure. Now one obvious question can be, what are the real scenarios where stack helps us? Let's list down some of the applications of stack. Stack data structure is used for execution of function calls in a program. We have talked about this quite a bit in our lessons on dynamic memory allocation and linked lists. We can also say that stack is used for recursion because recursion is also a chain of function calls. It's just that all the calls are to the same function. To know more about this application, you can check the description of this video for a link to my Code School's lesson on dynamic memory allocation. Another application of stack is we can use it to implement undo operation in an editor. We can perform undo operation in any text editor or image editor. Right now I'm pressing Ctrl Z, and as you can see, some of the text that I have written is getting cleared. You can implement this using a stack. Stack is used in a number of important algorithms. Like for example, a compiler verifies whether parentheses in a source code are balanced or not using stack data structure. Corresponding to each opening curly brace or opening parenthesis in a source code, there must be a closing parenthesis at appropriate position, and if parentheses in a source code are not put properly, if they are not balanced, compiler should throw error, and this check can be performed using a stack. We will discuss some of these problems in detail in coming lessons. This much is good for an introduction. In our next lesson, we will discuss implementation of stack. This is it for this lesson. Thanks for watching. In our previous lesson, we introduced you to stack data structure. We talked about stack as abstract data type or ADT. As we know, when we define a data structure as abstract data type, we define it as a mathematical or logical model. We define only the features or operations available with the data structure and do not bother about implementation. Now in this lesson, we will see how we can implement stack data structure. We will first discuss possible implementations of stack, and then we'll go ahead and write some code. Okay, so let's get started. As we had seen, a stack is a list or collection with this restriction, with this constraint, that insertion and deletion, that we call push and pop operations in a stack, must be performed one element at a time and only from one end, that we call the top of stack. So if you see, if we can add only this one extra property, only this one extra constraint to any implementation of a list, that insertion and deletion must be performed only from one end, then we can get a stack. There are two popular ways of creating lists. We have talked about them a lot in our previous lessons. We can use any of them to create a stack. We can implement stacks using A, arrays, and B, linked lists. Both these implementations are pretty intuitive. Let's first discuss array-based implementation. Let's say I want to create a stack of integers. So what I can do is I can first create an array of integers. I'm creating an array of 10 integers here. I'm naming this array A. Now I'm going to use this array to store a stack. What I'm going to say is that at any point, some part of this array starting index 0 till an index marked as top will be my stack. We can create a variable named top to store the index of top of stack. For an empty stack, top is set as -1. Right now in this figure, top is pointing to an imaginary -1 index in the array. An insertion or push operation will be something like this. I will write a function named push that will take an integer x as argument. In push function, we will first increment top, and then we can fill in integer x at top index. Here we are assuming that a and top will be accessible to push function even when they are not passed as arguments. In C, we can declare them as global variables, or in an object-oriented implementation, all these entities can be members of a class. I'm only writing pseudocode to explain the implementation logic. Okay, so for this example array that I'm showing here, right now, top is set as -1, so my stack is empty. Let's insert something onto the stack. I will have to make call to push function. Let's say I want to insert number 2 onto the stack. In a call to push, first top will be incremented, and then the integer passed as argument will be written at top index. So 2 will be written at index 0. Let's push one more number. Let's say I want to push number 10 this time. Once again, top will be incremented. 10 will now go at index 1. With each push, the stack will expand towards higher indices in the array. To pop an element from the stack, I'm writing a function here for pop operation. All I need to do is decrement top by 1. With a call to pop, let's say I'm making a call to pop function here, top will simply be decremented. Whatever cells are in yellow in this figure are part of my stack. We do not need to reset this value before popping. If a cell is not part of stack anymore, we do not care what garbage lies there. Next time when we will push, we will modify it anyway. So let's say after this pop operation, I want to perform a push. I want to insert number 7 onto the stack. So top once again will be incremented, and value at index 2 will be overwritten. The new value will be 7. These two functions, push and pop, that I have written here, will take constant time. We have simple operations in these two functions, and execution time will not depend upon size of stack. While defining stack ADT, we had said that all the operations must take constant time, or in other words, their time complexity should be big O of 1. In our implementation here, both push and pop operations are big O of 1. One important thing here, we can push onto the stack only till array is not exhausted, only till some space is left in the array. We can have a situation where stack would consume the whole array, so top will be equal to highest index in the array. A further push will not be possible because it will result in an overflow. This is one limitation with array-based implementation. To avoid an overflow, we can always create a large enough array. For that, we will have to be reasonably sure that stack will not grow beyond a certain limit. In most practical cases, large enough array works, but irrespective of that, we must handle overflow in our implementation. There are a couple of things that we can do in case of an overflow. Push function can check whether array is exhausted or not, and it can throw an error in case of an overflow. So push operation will not succeed. This will not be a really good behavior. We can do another thing. We can use the concept of dynamic array. We have talked about dynamic array in initial lessons in this series. What we can do is, in case of an overflow, we can create a new larger array. We can copy the content of stack from older filled up array into new array. If possible, we can delete the smaller array. The cost of copy will be big O of n, or in simple words, time taken to copy elements from smaller array to larger array will be proportional to number of elements in stack or the size of the smaller array, because anyway stack will occupy the whole array. There must be some strategy to decide the size of larger array. Optimal strategy is that we should create an array twice the size of smaller array. There can be two scenarios in a push operation. In a normal push, we will take constant time. In case of an overflow, we will first create a larger array, twice the size of smaller array, copy all elements in time proportional to size of the smaller array, and then we will take constant time to insert the new element. The time complexity of push with this strategy will be big O of 1 in best case and big O of n in worst case. In case of an overflow, time complexity will be big O of n. But we will still be big O of 1 in average case. If we will calculate the time taken for n pushes, then it will be proportional to n. Remember, n is the number of elements in stack. Big O of n is basically saying that time taken will be very close to some constant times n. In simple words, time taken will be proportional to n. If we are taking c into n time for n pushes, to find out average we will divide by n. Average time taken for each push will be a constant, hence big O of 1 in average case. I will not go into all the mathematics of why it's big O of n for n pushes. To know about it, you can check the description of this video for some resources. Okay, so this pretty much is core of our implementation. We had talked about two more operations in definition of stack ADT. Top operation simply returns the element at top of stack. So top function will look something like this. We will simply return the element at top index. To verify whether stack is empty or not, this is another operation that we had defined. We can simply check the value of top. If it is equal to -1, we can say the stack is empty, we can return true, else we can return false. Sometimes pop and top operations are combined together. In that case, pop will not just remove an element from top of stack, it will also return that element. Language libraries in a lot of programming languages give us implementation of stack. Signature of functions in these implementations can vary slightly. Okay, now I will quickly show you a basic implementation of stack in C. In my C code here, I'm going to write a simple array-based implementation to create a stack of integers. The first thing that I'm going to do is I'm going to create an array of integers as global variable, and the size of this array is max size, where max size is defined by this macro as 101. I will declare another global variable named top and set it as -1 initially. Remember, top equal -1 means an empty stack. When a variable is not declared inside any function, it's a global variable. It can be accessed anywhere, so you do not have to pass it as argument to functions. And now I will write all the operations. This is my push function. I'm first incrementing top and then setting the value at top as x. X is the integer to be inserted, passed as argument. Instead of writing these two statements, I can write one statement like this and I will be good. I'm using pre-increment operators, so increment will happen before assignment. I also want to handle overflow. We will have an overflow when top index will be equal to max size -1, highest index available in the array. In case of an overflow, I simply want to print an error message, something like this, and return. So in this implementation, I'm not using a dynamic array. In case of overflow, push will not succeed. Okay, now this is my pop function. I'm simply decrementing top. Here also we must handle one error condition. If stack is already empty, we cannot pop. So I'm writing these statements here. If top is equal to -1, we cannot pop. I will print this error message that there is no element to pop and simply return. Now let's write top operation. Top operation will simply return the integer at top index. So now my basic operations are all written here. I have already written push, pop, and top. In main function, I will make some calls to push and pop. And I want to write one more function named print, and this is something that I'm going to write only to verify that push and pop are happening properly. I will simply print all the elements in the stack. In my main function, after each push or pop operation, I will make a call to print. I'm writing multiple function calls, 2 function calls on same line here because I'm short of space. Remember, print function is not a typical operation available with stack. I'm writing it only to test my implementation. So this pretty much is my code. Let's now run this program and see what happens. This is what I'm getting as output. We are pushing 3 integers, 2, 5 and 10, and then we are performing a pop. So 10 gets removed from the stack and then we are pushing 12. So this is a basic implementation of stack in C. This is not an ideal implementation. An ideal implementation should be something like, we should have a data type called stack and we should be able to create instances of it. We can easily do it in an object-oriented implementation. We can do it in C also using structures. Check the description of this video for link to source code of this implementation as well as of an object-oriented implementation. In our next lesson, we will discuss linked list implementation of stack. This is it for this lesson. Thanks for watching. In our previous lesson, we saw how we can implement stack using arrays. Now in this lesson, we will see how we can implement stack using linked list. For this lesson, I'm assuming that you already know about both stack as well as linked list. Stack, as we know from our discussion so far, is called a last in first out data structure. Whatever goes in last in a stack comes out first. It's a list with this restriction that insertion and deletion must be performed only from one end, that we call the top of stack. And insertion in a stack is called push operation and deletion is called pop. To implement a stack, all we need to do is enforce this behavior in any implementation of a list, that insertion and deletion must be performed only from one end, and we can call that end top of stack. It's really easy to enforce this behavior in a linked list. I have drawn a linked list of integers here. This is logical representation of a linked list. A linked list is a collection of entities that we call nodes. Each node contains 2 fields, one to store data and another to store the address of the next node. Now let's assume that these nodes are at addresses 100, 200 and 400 respectively. So I will fill up the address part as well. The identity of a linked list is the address of the first node that we also call the head node. A variable stores the address of head node. We often name this variable as head. Unlike arrays, linked lists are not of fixed size, and elements in a linked list are not stored in one contiguous block of memory. We already know how to create a linked list or insert and delete elements from a linked list from our previous lessons. I'm just doing a quick recap here. To insert an element in a linked list, we first create a new node, which is basically blocking some part of memory to store our data. In this example here, let's say for my new node, I'm getting address 350. We can set the data part of the linked list as whatever value I want to add in the list. And then I need to modify the address field of some of the existing nodes to link this node in actual list. Now for a stack, we want that insertion and deletion must always happen from the same end. We can use a linked list at stack if we always insert and delete a node at same end. We have 2 options. We can insert or delete from end of the list, what we also call tail, or beginning of the list, that we call head. If you remember from our previous lessons, inserting a node at end of linked list is not a constant time operation. The cost of both insertion and deletion at end of linked list, if we have to talk about the time complexity of it, is big O of n. Here in the definition of stack, we are saying that push and pop operations should take constant time, or their time complexity should be big O of 1. But if we will insert and delete from end, time complexity will be big O of n. To insert a new node in a linked list at the end, we need to go to the last node and set the address part of that node to make it point to the new node. To traverse a linked list and go to the last node, we should start at the head or the first node. From first node, we get the address of the second node. So we go to the second node, and from second node we get the address of the third node. It's like playing treasure hunt. You go to the first guy, ask the address of the second guy, and then you go to the second guy, ask the address of the third guy, and so on. Now once I've reached this last node in my example here, I can set its address part to make it point to the newly created node. All in all, this operation will take time proportional to number of elements in the linked list. To delete a node from end, once again we will have to traverse the whole list. We will have to go to the second last node, break this link. We will set the address field as 0 or null, and then we can simply wipe off the last node removed from the list from computer's memory. Once again, the cost of traversal will be big O of n. So inserting and deleting at end or tail is not an option for us, because we will not be able to do push and pop in constant time if we choose to insert and delete from end. The cost of inserting or deleting from beginning, however, is big O of 1. It will take constant time to insert a node at beginning or delete a node from beginning. To insert a node at beginning, we must create a new node. In this example here, once again I have created a new node. Let's say the address of the new node is 350. I will insert some data in the first field of this node. Okay, so to insert this node at beginning, we just need to build two links. First, we need to build this link. So we will set the address here as whatever the address of the current head is, and then we can break this link and make this guy the new head by setting its address here in this variable named head. To delete a node, in this example here, we will have to first cut this link and build this link, which will mean resetting the address in this variable head, and then we can free the memory allocated to this particular guy, this particular node. Deletion from beginning once again is a constant time operation. So this is the thing, if we will insert at beginning and delete from beginning, then all our conditions are satisfied. So linked list implementation of stack is pretty straightforward. All we need to do is insert a node at the beginning and delete a node from beginning. So head of the linked list is basically the top of stack. I would rather name this variable top here. I'll quickly write a basic implementation in C. I'm defining node as a structure in C. I want to create a stack of integers. So first field in the node is an integer. Another field is pointer to node that will store the address of the next node. We have seen this definition of node in all our previous lessons on linked list. The next thing that I'm doing is I'm declaring a variable named top, which is pointer to node. And initially I'm setting the address in it as null. I'm using variable named top instead of head here. When top is null, our stack is empty. By initializing top as null, I'm saying that initially my stack is empty. Now let's write push and pop functions. This is my push function. Push is taking an integer x as argument that must be inserted onto the stack. The first thing that we are doing in push function is that we are creating a node using malloc. Let's say in this example, in this logical representation that I'm showing here, I'm performing a push operation. So I'm making a call to push function, passing it number 2 as argument. So a node is created in memory, is created in what we call the dynamic memory or heap. Let's say the address of this node is 100. This variable is basically a pointer pointing to this node. Temp is a pointer pointing to this node. In the next line, we are setting the data field in this node. We are dereferencing temp to do so. Then we are setting the link part of this newly created node as existing top. So we are building this link. And then we are saying top equal temp, so we are building this link. This is simple insertion at beginning of a linked list. We have one complete video in this series on how to insert a node at beginning of linked list. Let's do one more push. Let's say I want to push number 5 onto the stack this time. Once again, a node will be created. We will set the data, and then we will first point this guy to the existing top, and then make this pointer variable point to this guy, the new top. Let's say the address of this guy is 250. So the address in this variable top will be set as 250. After this second push, this is how my stack will look like. Top here is a global variable, so we do not need to pass it as argument to functions. It is accessible to all the functions. In an object-oriented implementation, it can be a private field, and we can set it as null in the constructor. Okay, let's now see how pop function will look like. This is my pop function. Let's say for this example, I'm making a call to pop function. If the stack is already empty, we can check whether stack is empty or not by checking whether top is null or not. If top is null, stack is empty. In this case, we can throw some error and return. For this example here, stack is not empty. We have 2 integers in the stack. What we are first doing is we are creating a pointer to node temp and pointing it to the top node. And now we are breaking this link. We are setting the address in top as address of the next node. And now using this pointer variable temp, we are freeing the memory allocated to the node being removed from the list. Once I exit the pop function, this is my stack. So this pretty much is the core of our implementation. I would encourage you to write rest of the stuff yourself. You can write code for operations like top and is empty. Linked list implementation of stack has some advantages. One of the advantages is that unlike array-based implementation, we do not need to worry about overflow unless we exhaust the memory of the machine itself. Some amount of extra memory is used in each node to store reference or address, but the fact that we use memory when needed and release when not needed is something that makes push and pop operations more graceful. So this is linked list based implementation of stack. In our coming lessons, we will solve some problems using stack. This is it for this lesson. Thanks for watching. In our previous lesson, we saw how we can implement a stack. We saw 2 popular implementations of stack, one using arrays and another using linked list. A warrior should not just possess a weapon, he must also know when and how to use it. As programmers, we must know in what all scenarios we can use a particular data structure. In this lesson, I'm going to talk about one simple use case of stack. A stack can be used to reverse a list or collection, or simply to traverse a list or collection in reverse order. I'm going to talk about 2 problems, reversal of string and reversal of linked list. And I'm going to solve both these problems using stack. Let's first discuss reversal of string. I have a string in the form of a character array here. I have this string hello. A string is a sequence of characters. This is a C style string. In C, a string must be terminated with a null character, so this last character is a null character. Reversal means characters in the array should be rearranged like what I'm showing here in the right. Null character is used only to mark the end of string. It is not part of string. Okay, there are a couple of efficient ways in which we can reverse a string. Let's first discuss how we can solve this problem using a stack, and then we will see how efficient it is. What we can do is we can create a stack of characters. I'm showing logical representation of a stack here. This is a stack of characters and right now it's empty. And now what we can do is we can traverse the characters in the string from left to right and start pushing them onto the stack. So first H goes into the stack, then the next character is E, then L, then we have another L, and then the last character is O. Once all the characters in the string have gone into the stack, we can once again start at the 0th index. Now we need to write the topmost character in the stack at this index. We can get the topmost character by calling top operation, and now we can perform a pop, and now we can go to the next index, fill in whatever is at top of stack, and perform a pop again. We can go on doing this until stack is not empty, so all the positions in the character array will be overwritten. So finally we have reversed our string here. In a stack, whatever goes in last comes out first. So if we will push a bunch of items onto a stack, and once all items are pushed, if we will start popping, we will get the items in reverse order. First item pushed onto the stack will come out last. Let's quickly write code for this logic. I'm going to write C++ here. Things will be pretty similar in other languages, so it doesn't really matter. What I'm going to do in my code is I'm going to create a character array to store a string, and then I will ask user to input a string. Once I input the string, I will make a call to a function named reverse, passing it the array and length of string that I will get by making a call to string length function. And finally I'm printing the reversed string. Now I need to write the reverse function. In reverse function I want to use a stack of characters. We have already seen how we can implement stack. In C++ we can create a class named stack that would have an array of characters and an integer variable named top to mark the top of stack in array, and these variables can be private, and we can work upon the stack using these public functions. In reverse function we can simply create an object of stack and use it. This class can be an array based implementation of stack or a linked list based implementation of stack. It doesn't really matter. In C++ and many other languages, language libraries also give us implementation of stack. In this program I'm not going to write my own stack. I'm going to use stack from what we call standard template library in C++. I will have to use this include statement #include stack, and now I have a stack class available to me. To create an object of this class I need to write stack and within angular brackets data type for which we want a stack, then after space name or identifier. With this one statement here I have created a stack of characters. Let's now write the core logic. This n in the signature of reverse function is number of characters in string. This array, as we know, array in C or C++ is always passed by reference through a pointer. This C followed by brackets is only an alternate syntax for *C. It's interpreted like this by the compiler. Okay, so now what I'm going to do is I'm going to run a loop starting 0 till n-1. So I will traverse the string from left to right, and as I traverse the string I will push the character onto stack by calling push function. I will use a statement like this. Once push is done, I'll do another loop for pop. I will run a loop with this variable I starting at 0 going till n-1, and I'll first set ci as top of stack, and then I will perform a pop operation. If you want to know more about functions available with stack in STL, like their signatures and how to use them, you can check the description of this video for some resources. This is all I need to do in my reverse function. Let's run this code and see what happens. I need to enter a string. Let's enter hello. This is what I get as output, which seems to be correct. Let's run this again, and this time I want to enter my code school. This looks alright too, so we seem to be good. So this function is solving my problem of reversal. Let's now see how efficient it is. Let's analyze its time complexity. We know that all operations on stack take constant time, so all these statements within loop, inside loop, will take constant time. The first loop is running n times, and then the second loop is also running n times. First loop will execute in big O of n, and the second loop will also execute in big O of n. The loops are not nested, they are one after other. So in such scenario, complexity of the whole function will also be big O of n. Time complexity is big O of n, but we are using some extra memory here for stack. We are pushing all the characters in the string onto a stack. The extra space taken in stack will be proportional to number of characters in the string, will be proportional to n. So we can say that space complexity of this function is also big O of n. In simple words, extra space taken is directly proportional to n. There are efficient ways to reverse a string without using extra space. The most efficient way probably would be to use just two variables to mark the start and end index in the string initially. Let's say I'm using variables I and j. Initially I for this example is 0 and j is 4. While I is less than j, we can swap the characters at these positions. And once we have swapped, we can increment I and decrement j. If I is less than j, we can swap again. And once again increment I and decrement j. Now I is not less than j, I is equal to j. At this stage, we can stop swapping and we are done. This algorithm has space complexity big O of 1. We are using constant extra memory here. Time complexity of this approach once again is big O of n. We will do n by 2 swaps, so time taken will be proportional to n. Definitely because of space complexity, this approach is better than our stack approach. Sometimes when we know that our input will be very small and time and space is not much of concern, we use a particular algorithm for ease of implementation, for its being intuitive. It's clearly not the case when we are using stack to reverse a string, but for this other problem, reversal of linked list that we had said we will discuss, using a stack gives us a neat and intuitive solution. I have drawn a linked list of integers here. As we know, linked lists are collections of entities that we call nodes. Each node contains two fields, one to store data and other to store address of next node. I have assumed that these nodes in this example here are at addresses 100, 150, 250 and 300 respectively. Identity of a linked list is address of the head node. We typically store this address in a variable named head. In an array, it takes constant time to access any element. So whether it's the first element or last element, it takes constant time to access it. It is so because array is stored as one contiguous block of memory. So if we know the starting address of the array, let's say the starting address of this array is 400, and size of each element in the array, character takes 1 byte. So for this example, each element is 1 byte. Then we can calculate address of any element. So we know that A4 is at 400 plus 4 or 404. But in a linked list, nodes are stored at disjoint locations in memory. To access any node, we have to start at the head node. So we can't do something as simple as having two pointers at start and end and accessing the elements. We have already seen in this series two possible approaches that can be used to reverse a linked list. One was an iterative solution where we go on reversing links as we traverse the linked list using some temporary variables. Another solution was using recursion. The time complexity of iterative solution is big O of n. Space complexity is big O of 1. In recursive solution, we do not create a stack explicitly, but recursion uses the stack in computer's memory that is used to execute function calls. In such a case, we say that we are using implicit stack. Stack is not being created explicitly, but still we are using an implicit stack. I will come back to this and explain in detail. The time complexity of recursive solution once again is big O of n, but the space complexity is big O of n this time. Space complexity is also big O of n. Now let's see how we can use an explicit stack to solve this problem. Once again, I have drawn logical representation of stack here. Right now the stack is empty. In a program, this will be a stack of type pointer to node. What I'm going to do now is I'm going to traverse this linked list using a temporary pointer to node. The temporary variable will initially point to head. When we will go to a particular node, we will push the address of that node onto the stack. So first 100 will go to stack, and now we will move to the next node. Now 150 will go in stack, and now we will go to 250 and then to the last node at 300. We are showing addresses here in the stack, but basically the objects that we are pushing are pointers to node, or in other words, references to nodes. If node is defined like this in C++, we will have to use these statements to traverse the linked list and push all the references. Let's say head is a pointer to node, which I'm assuming is a global variable that will store the address of head node. I'm using a temporary variable that is pointer to node. Initially I'm storing the address of head node in this temporary variable, and then I'm running a loop and I'm traversing the linked list, and as I'm traversing, I'm pushing the reference onto stack. Once all the references are pushed onto stack, we can start popping them, and as we will pop them, we will get references to nodes in reverse order. It would be like going through the list in reverse order. While traversing the list in reverse order, we can build reverse links. The first thing that I'll do is I'll take a temporary variable that will be pointer to node and store the address at the top of stack, which right now is 300. Now I will set head as this address. So head now becomes 300, and then I will pop. I'm running you through this example here as I'm writing code. Head and temp right now are both 300, and now I will run a loop like this, like what I have written here. While stack is not empty, this function empty returns true if stack is empty. I'm using stack from standard template library in C++. So while stack is not empty, I'm going to say that set temp.next as address at top of stack. Basically I'm using this pointer to node temp to dereference and set this particular address field. Right now top is 250, so I'm building this reverse link. Next statement is a pop, and in the next statement I'm saying temp equal temp.next, which means temp will now point to this node at 250. Stack is not empty, so loop will execute again. We are writing address here now, then we should pop and then move to 150 using this statement temp equal temp.next. Now we are building this link, popping, and then oops, this should have been 150, and with the next temp equal temp.next we are going here. Even though we have built this link by setting this field here, this node is still pointing to this guy. Because the stack is empty now, we will exit the loop. After exit from the loop, I have written one more line, temp.next equal null. So I'm setting the last link part of last node in reversed list as null. Finally, this is my reverse function. I have assumed that head is a global variable and it's a pointer to node. If you want the complete source code, you can check the description of this video for a link. Using a stack in this case is making our life easier. Reversing a linked list is still a complex problem. Try to just print the elements of linked list in reverse order. If you will use a stack, it will be really easy. I will stop here for this lesson. If you want to know what I meant by implicit stack, you can once again check the description of this video for some resources. So this is it for this lesson. Thanks for watching. In our previous lesson, we saw one simple application of stack. We saw that a stack can be used to reverse a list or collection, or maybe to simply traverse a list or collection in reverse order. Now in this lesson we will discuss another famous problem that can be solved using stack, and this is also a popular programming interview question. And the problem is, given an expression in the form of a string comprising of, let's say, constants, variables, operators, and parentheses, and when I say parentheses, I also want to include curly braces and brackets in my definition of parentheses. So my expression or string can contain characters that can be upper or lower case letters, symbols for operators, and an opening or closing parenthesis, or an opening or closing curly brace, or an opening or closing square bracket. Let's write down some expressions here. I'm going to write a simple expression. We have one simple expression here with one pair of opening and closing parentheses. Here in this expression we have nested parentheses. Now, given such expressions, we want to write a program that would tell us whether parentheses in the expression are balanced or not. And what do we really mean by balanced parenthesis? What we really mean by balanced parenthesis is that corresponding to each opening parenthesis or opening curly brace or opening bracket, we should have a closing counterpart in correct order. These two expressions here are balanced. However, this next expression is not balanced. A closing curly brace is missing here. This next expression is also not balanced because we are missing an opening square bracket here. This next one is also not balanced because corresponding to this opening curly brace we do not have a closing curly brace, and corresponding to this closing parenthesis we do not have an opening parenthesis. If we are opening with a curly brace, we should also close with a curly brace. These two won't count for each other. Checking for balanced parenthesis is one of the tasks performed by a compiler. When we write a program, we often miss an opening or closing curly brace or an opening or closing parenthesis. Compiler must check for this balancing, and if symbols are not balanced, it should give you an error. In this problem here, what's inside a parenthesis does not matter. We do not want to check for correctness of anything that is inside a parenthesis. So in the string, any character other than opening and closing parenthesis or opening and closing curly brace or opening and closing square bracket can be ignored. This problem sometimes is better stated like this. Given a string comprising only of opening and closing characters of parentheses, braces or brackets, we want to check for balancing. So only these characters and their order is important. While parsing a real expression, we can simply ignore other characters. All we care about is these characters and their order. Okay, so now how do we solve this problem? One straightforward thing that comes to mind is that because we should have a closing counterpart for an opening parenthesis or opening curly brace or opening square bracket, what we can do is we can count the number of opening and closing symbols for each of these three types, and they should be equal. So the number of opening parentheses should be equal to number of closing parentheses, and the number of opening curly braces should be equal to number of closing curly braces, and same should be true for square brackets as well. But it will not be good enough. This expression here has one opening parenthesis and one closing parenthesis, but it's not balanced. This next one is balanced, but this one with same number of characters of each type as the second expression is not balanced. So this approach won't work. Apart from count being equal, there are some other properties that must be conserved. Every opening parenthesis must find a closing counterpart to its right, and every closing parenthesis must find an opening counterpart in its left, which is not true in the first expression. And the other property that must be conserved is that a parenthesis can close only when all the parentheses opened after it are closed. This parenthesis has been opened after this square bracket, so this square bracket cannot close unless this parenthesis has closed. Anything that is opened last should be closed first. Well, actually it should not be last opened first closed. In this example here, this is getting opened last, but this guy that is opened previous to this is closed first, and it is fine. The property that must be conserved is that as we scan the expression from left to right, any closer should be for the previous unclosed parenthesis. Any closer should be for the last unclosed. Let's scan some expressions from left to right and see how it's true. Let's scan this last one. We will go from left to right. First character is an opening of square bracket. Second one is an opening parenthesis. Let's mark opening of unclosed parenthesis in red. Okay, now we have a closer here. The third character is a closer. This should be the closer for the last unclosed. So this should be the closer for this one, this guy. This opening parenthesis. Last unclosed now is this guy. Next character once again is an opening parenthesis. Now we have two unclosed parentheses at this stage, and this one is the last unclosed. The next one is a closure. So it should be closer for the last unclosed. Now the last unclosed once again is the opening of square bracket. Now when we have a closure, it should be closer for this guy. We can use this approach to solve this problem. What we can do is we can scan the expression from left to right, and as we scan, at any stage we can keep track of all the unclosed parentheses. Basically what we can do is whenever we get an opening symbol, an opening parenthesis, an opening curly brace, or an opening square bracket, we can add it to a list. If we get a closing symbol, it should be the closer for the last element in the list. In case of an inconsistency, like if the last opening symbol in the list is not of the same type as the closing symbol, or if there is no last opening symbol at all because the list is empty, we can stop this whole process and say that parentheses are not balanced. Else we can remove the last opening symbol in the list because we have got its counterpart, and continue this whole process. Things will be further clear if I will run through an example. I will run through this last example once again. We are going to scan this expression from left to right, and we will maintain a list to keep track of all the opened parentheses that are not yet closed. We will keep a track of all the unclosed parentheses, opened but not closed. Initially this list is empty. The first character that we have got is an opening of square bracket. This will go into the list and we will move to the next character. The next character is an opening parenthesis, so once again it should go to the list. We should always insert at end in the list. The next character is a closing of parenthesis. Now we must look at the last opening symbol in the list, and if it is of the same type, then we have got its counterpart and we should remove this. Now we move on to the next character. This is once again an opening parenthesis. It should go in the list at the end. The next character is a closing of parenthesis, so we will look at the last element in the list. It's an opening parenthesis, so we can remove it from the list. And now we go to the last character, which is a closing of square bracket. Once again we need to look at the last element in the list. We have one element, only one element in the list at this stage. It's an opening of square bracket, so once again we can remove it from the list. Now we are done scanning the list and the list is empty once again. If everything is alright, if parentheses are balanced, we will always end with an empty list. If in the end list is not empty, then some opening parenthesis has not found its closing counterpart and the expression is not balanced. One thing worth noticing here is that we are always inserting or removing one element at a time from the same end of the list. In this whole process, whatever is coming in last in the list is going out first. There is a special kind of list that enforces this behavior, that element should be inserted and removed from the same end, and we call it a stack. In a stack we can insert and remove an element one at a time from the same end in constant time. So what we can do is whenever we get an opening symbol while scanning the list, we can push it onto the stack, and when we get a closing symbol we can check whether the opening symbol at the top of stack is of the same type as the closing symbol. If it's of the same type, we can pop it. If it's not of the same type, we can simply say that parentheses are not balanced. I will quickly write pseudocode for this logic. I'm going to write a function named check balanced parenthesis that will take an expression in the form of a string as argument. First of all, I will store the number of characters in the string in a variable, and then I will create a stack, and I will create a stack of characters. And now I will scan the expression from left to right using a loop. While scanning, if the character is an opening symbol, if it's an opening parenthesis or opening curly brace or opening square bracket, we can push that character onto the stack. Let's say this function push will push a character onto S. Else, if expression I or the character at ith position while scanning is a closing symbol of any of the three types, we can have two scenarios. If stack is empty or top of stack does not pair with the closing symbol. If we have a closing of parenthesis, then the top of stack should be an opening of parenthesis. It cannot be an opening of curly brace. In such a scenario, we can conclude that the parentheses are not balanced. Else, we can perform a pop. Finally, once our scanning is over, we can check whether stack is empty or not. If it's empty, parentheses are balanced. If it's not, they are not balanced. So this is my pseudocode. Let's run through a couple of examples and see whether this works for all scenarios, all test cases or not. Let's first look at this expression. The first thing that we are doing in our code is that we are creating a stack of characters. I have drawn logical representation of a stack here. Okay, now let's scan this string. Let's say we have a 0-based index and the string is just a character array. We are starting the scan, we are going inside the loop. This is a closing of parenthesis, so this if statement will not hold true, so we will go to the else condition, and now we will go inside the else to check for this condition whether stack is empty or not, or whether the top of stack pairs with this closing symbol or not. The stack is empty. If the stack is empty, there is no opening counterpart for this closing symbol, so we will simply return false. Returning means exiting the function, so we are simply concluding here that parentheses are not balanced and exiting. Let's go through this one now. First we have an opening square bracket, so we will go to the first if and push. Next one is an opening parenthesis, once again it will be pushed. Next one is a closing square bracket, so the condition for this else if will be true. We will go inside this else if. Now this time the top of stack is an opening parenthesis. It should have been an opening square bracket, and then only we would have a pair. So this time also we will have to return false and exit. Okay, now let's go through this one. First we will have a push. The next one will also be a push. Now next one is a closer of parenthesis, which pairs with the top of stack, which is opening of parenthesis. So we will have a pop. We will go to the next character, and this one once again is an opening parenthesis, so there will be a push. Next one is a closing parenthesis, and the top is an opening parenthesis. They pair, so there will be a pop. Last character is a closing curly brace, so once again we will see whether top of stack is an opening curly brace or not. Do we have a pair or not? Yes, we have a pair, so there will be a pop. With this, our scanning will finish. And finally stack should be empty. It is empty, so we have balanced parentheses here. Try implementing this pseudocode in a language of your choice and see whether it works for all test cases or not. If you want to look at my implementation, you can check the description of this video for a link. In the coming lessons we will see some more problems on stack. This is it for this lesson. Thanks for watching. Hello everyone. In this lesson, we are going to talk about one important and really interesting topic in computer science where we find application of stack data structure. And this topic is evaluation of arithmetic and logical expressions. So how do we write an expression? I have written some simple arithmetic expressions here. An expression can have constants, variables, and symbols that can be operators or parentheses, and all these components must be arranged according to a set of rules, according to a grammar, and we should be able to parse and evaluate the expression according to this grammar. All these expressions that I have written here have a common structure. We have an operator in between two operands. Operand by definition is an object or value on which operation is performed. In this expression 2 plus 3, 2 and 3 are operands and plus is operator. In the next expression, a and b are operands and minus is operator. In the third expression, this asterisk is for multiplication operation, so this is the operator. The first operand p is a variable and the second operand 2 is a constant. This is the most common way of writing an expression, but this is not the only way. This way of writing an expression in which we write an operator in between operands is called infix notation. Operand doesn't always have to be a constant or variable. Operand can be an expression itself. In this fourth expression that I have written here, one of the operands of multiplication operator is an expression itself. Another operand is a constant. We can have a further complex expression. In this fifth expression that I have written here, both the operands of multiplication operator are expressions. We have three operators in this expression here. For this first plus operator, P and Q, these variables P and Q are operands. For the second plus operator, we have R and S. And for this multiplication operator, the first operand is this expression P plus Q, and the second operand is this expression R plus S. While evaluating expressions with multiple operators, operations will have to be performed in certain order. Like in this fourth example, we will first have to perform the addition and then only we can perform multiplication. In this fifth expression, first we will have to perform these two additions and then we can perform the multiplication. We will come back to evaluation, but if you can see, in all these expressions, operator is placed in between operands. This is the syntax that we are following. One thing that I must point out here, throughout this lesson we are going to talk only about binary operators. An operator that requires exactly two operands is called a binary operator. Technically we can have an operator that may require just one operand or maybe more than two operands, but we are talking only about expressions with binary operators. Okay, so let's now see what all rules we need to apply to evaluate such expressions written in this syntax that we are calling infix notation. For an expression with just one operator, there is no problem, we can simply apply that operator. For an expression with multiple operators and no parenthesis like this, we need to decide an order in which operators should be applied. In this expression, if we will perform the addition first, then this expression will reduce to 10 into 2 and will finally evaluate as 20. But if we will perform the multiplication first, then this expression will reduce to 4 plus 12 and will finally evaluate to 16. So basically we can look at this expression in two ways. We can say that operands for addition operator are 4 and 6, and operands for multiplication are this expression 4 plus 6 and this constant 2. Or we can say that operands for multiplication are 6 and 2, and operands for addition operation are 4 and this expression 6 into 2. There is some ambiguity here, but if you remember your high school mathematics, this problem is resolved by following operator precedence rule. In an algebraic expression, this is the precedence that we follow. First preference is given to parentheses or brackets. Next preference is given to exponents. I'm using this symbol for exponent operator, so if I have to write 2 to the power 3, I'll be writing it something like this. In case of multiple exponentiation operator, we apply the operators from right to left. So if I have something like this, then first this rightmost exponentiation operator will be applied. So this will reduce to 512. If you will apply the left operator first, then this will evaluate to 64. After exponents, next preference is given to multiplication and division, and if it's between multiplication and division operators, then we should go from left to right. After multiplication and division, we have addition and subtraction, and here also we go from left to right. If we have an expression like this with just addition and subtraction operators, then we will apply the leftmost operator first, because the precedence of these operators is same, and this will evaluate to 3. If you will apply the plus operator first, this will evaluate as 1, and that will be wrong. In this second expression 4 plus 6 into 2 that I have written here, if we will apply operator precedence, then multiplication should be performed first. If we want to perform the addition first, then we need to write this 4 plus 6 within parentheses, and now addition will be performed first because precedence of parentheses is greater. I'll take example of another complex expression and try to evaluate it just to make things further clear. So I have an expression here. In this expression we have 4 operators, 1 multiplication, 1 division, 1 subtraction and 1 addition. Multiplication and division have higher precedence. Between these two, multiplication and division, which have same precedence, we will pick the left one first. So we will first reduce this expression like this, and now we will perform the division, and now we have only subtraction and addition. So we will go from left to right, and this is what we will finally get. This right to left and left to right rule that I have written here for operators with equal precedence is better termed as operator associativity. If in case of multiple operators with equal precedence we go from left to right, then we say that the operators are left associative. And if we go from right to left, we say that the operators are right associative. While evaluating an expression in infix form, we first need to look at precedence, and then to resolve conflict among operators with equal precedence, we need to see associativity. All in all, we need to do so many things just to parse and evaluate an infix expression. The use of parentheses becomes really important because that's how we can control the order in which operations should be performed. Parentheses add explicit intent that operation should be performed in this order and also improve readability of expression. I have modified this third expression. We have some parentheses here now, and most often we write infix expressions like this only, using a lot of parentheses. Even though infix notation is the most common way of writing expressions, it's not very easy to parse and evaluate an infix expression without ambiguity. So mathematicians and logicians studied this problem and came up with two other ways of writing expressions that are parenthesis free and can be parsed without ambiguity, without requiring to take care of any of these operator precedence or associativity rules. And these two ways are postfix and prefix notations. Prefix notation was proposed earlier in year 1924 by a Polish logician. Prefix notation is also known as Polish notation. In prefix notation, operator is placed before operands. This expression 2 plus 3 in infix will be written as plus 2 3 in prefix. Plus operator will be placed before the two operands 2 and 3. P minus Q will be written as minus PQ. Once again, just like infix notation, operand in prefix notation doesn't always have to be a constant or variable. Operand can be a complex prefix notation itself. This expression a plus b asterisk c in infix form will be written like this in prefix form. I'll come back to how we can convert infix expression to prefix. First, have a look at this third expression in prefix form. For this multiplication operator, the two operands are variables b and c. These three elements are in prefix syntax. First we have the operator and then we have the two operands. The operands for addition operator are variable a and this prefix expression asterisk bc. In infix expression, we need to use parentheses because an operand can possibly be associated with two operators. Like in this third expression in infix form, b can be associated with both plus and multiplication. To resolve this conflict, we need to use operator precedence and associativity rules, or use parentheses to explicitly specify association. But in prefix form and also in postfix form that we will discuss in some time, an operand can be associated with only one operator. So we do not have this ambiguity. While parsing and evaluating prefix and postfix expressions, we do not need extra information. We do not need all the operator precedence and associativity rules. I'll come back to how we can evaluate prefix notation. I'll first define postfix notation. Postfix notation is also known as reverse Polish notation. This syntax was proposed in 1950s by some computer scientists. In postfix notation, operator is placed after operands. Programmatically, postfix expression is easiest to parse and least costly in terms of time and memory to evaluate, and that's why this was actually invented. Prefix expression can also be evaluated in similar time and memory, but the algorithm to parse and evaluate postfix expression is really straightforward and intuitive, and that's why it's preferred for computation using machines. I'm going to write postfix for these expressions that I had written earlier in other forms. This first expression 2 plus 3 in postfix will be 2 3 plus. To separate the operands, we can use a space or some other delimiter like a comma. That's how you would typically store prefix or postfix in a string when you'll have to write a program. This second expression in postfix will be PQ minus. So as you can see in postfix form, we are placing the operator after the operands. This third expression in postfix will be ABC asterisk and then plus. For this multiplication operator, operands are variables b and c, and for this addition, operands are variable a and this postfix expression bc asterisk. We will see efficient algorithms to convert infix to prefix or postfix in later lessons, For now, let's not bother how we will do this in a program. Let's quickly see how we can do this manually. To convert an expression from infix to any of these other two forms, we need to go step by step, just the way we would go in evaluation. I have picked this expression a plus b into c in infix form. We should first convert the part that should be evaluated first. So we should go in order of precedence. We can also first put all the implicit parentheses. So here we will first convert this b into c. So first we are doing this conversion for multiplication operator, and then we will do this conversion for addition operator. We will bring addition to the front. So this is how the expression will transform. We can use parentheses in intermediate steps, and once we are done with all the steps, we can erase the parentheses. Let's now do the same thing for postfix. We will first do the conversion for multiplication operator, and then in next step we will do it for addition, and now we can get rid of all the parentheses. Parentheses surely adds readability to any of these expressions, to any of these forms. But if we are not bothered about human readability, then for a machine we are actually saving some memory that would be used to store parenthesis information. Infix expression definitely is most human readable, but prefix and postfix are good for machines. So this is infix, prefix and postfix notation for you. In next lesson we will discuss evaluation of prefix and postfix notations. This is it for this lesson. Thanks for watching. In our previous lesson we saw what prefix and postfix expressions are, but we did not discuss how we can evaluate these expressions. In this lesson we will see how we can evaluate prefix and postfix expressions. Algorithms to evaluate prefix and postfix expressions are similar, but I'm going to talk about postfix evaluation first because it's easier to understand and implement, and then I'll talk about evaluation of prefix. Okay, so let's get started. I have written an expression in infix form here, and I first want to convert this to postfix form. As we know, in infix form, operator is written in between operands, and we want to convert to postfix, in which operator is written after operands. We have already seen how we can do this in our previous lesson. We need to go step by step, just the way we would go in evaluation of infix. We need to go in order of precedence, and in each step we need to identify operands of an operator, and we need to bring the operator in front of the operands. What we can actually do is we can first resolve operator precedence and put parentheses at appropriate places. In this expression we'll first do this multiplication, this first multiplication, then we'll do this second multiplication, then we will perform this addition, and finally the subtraction. Okay, now we will go one operator at a time. Operands for this multiplication operator are a and b, so this a asterisk b will become ab asterisk. Now next we'll need to look at this multiplication. This will transform to cd asterisk, and now we can do the change for this addition. The two operands are these two expressions in postfix. So I'm placing the plus operator after these two expressions. Finally, for this last operator, the operands are this complex expression and this variable e. So this is how we will look like after the transformation. Finally, when we are done with all the operators, we can get rid of all the parentheses. They are not needed in postfix expression. This is how you can do the conversion manually. We will discuss efficient ways of doing this programmatically in later lessons. We will discuss algorithms to convert infix to prefix or postfix in later lessons. In this lesson we are only going to look at algorithms to evaluate prefix and postfix expressions. Okay, so we have this postfix expression here and we want to evaluate this expression. Let's say for these values of variables a, b, c, d and e. So we have this expression in terms of values to evaluate. I'll first quickly tell you how you can evaluate a postfix expression manually. What you need to do is you need to scan the expression from left to right and find the first occurrence of an operator. Like here, multiplication is the first operator. In postfix expression, operands of an operator will always lie to its left. For the first operator, the preceding two entities will always be operands. You need to look for the first occurrence of this pattern, operand, operand, operator in the expression. And now you can apply the operator on these two operands. and reduce the expression. So this is what I'm getting after evaluating 2, 3 asterisk. Now we need to repeat this process till we are done with all the operators. Once again, we need to scan the expression from left to right and look for the first operator. If the expression is correct, it will be preceded by 2 values. So basically we need to look for first occurrence of this pattern, operand, operand, operator. So now we can reduce this. We have 6 and then we have 5 into 4, 20. We are using space as delimiter here. There should be some space in between 2 operands. Okay, so this is what I have now. Once again, I'll look for the first occurrence of operand, operand, and operator. We will go on like this till we are done with all the operators. When I'm saying we need to look for first occurrence of this pattern, operand, operand, and operator, what I mean by operand here is a value and not a complex expression itself. The first operator will always be preceded by 2 values, and if you will give this some thought, you will be able to understand why. If you can see, in this expression we are applying the operators in the same order in which we have them while parsing from left to right. So first we are applying this leftmost multiplication on 2 and 3, then we are applying the next multiplication on 5 and 4, then we are performing the addition, and then finally we are performing the subtraction. And whenever we are performing an operation, we are picking the last 2 operands preceding the operator in the expression. So if we have to do this programmatically, if we have to evaluate a postfix expression given to us in a string like this, and let's say operands and operators are separated by space, we can have some other delimiter like comma also to separate operands and operator. Now what we can do is we can parse the string from left to right. In each step in this parsing, in each step in this scanning process, we can get a token that will either be an operator or an operand. What we can do is, as we parse from left to right, we can keep track of all the operands seen so far, and I'll come back to how it will help us. So I'm keeping all the operands seen so far in a list. The first entity that we have here is 2, which is an operand, so it will go to the list. Next we have 3, which once again is operand, so it will go into the list. Next we have this multiplication operator. Now this multiplication should be applied to last 2 operands preceding it, last 2 operands to the left of it, because we already have the elements stored in this list. All we need to do is we need to pick the last 2 from this list and perform the operation. It should be 2 into 3, and with this multiplication we have reduced the expression. This 2, 3 asterisk has now become 6. It has become an operand that can be used by an operator later. We are at this stage right now that I'm showing in the right. I'll continue the scanning. Next we have an operand. We'll push this number 5 onto the list. Next we have 4, which once again will come to the list. And now we have the multiplication operator, and it should be applied to the last 2 operands in the reduced expression. And we should put the result back into the list. This is the stage where we are right now. So this list actually is storing all the operands in the reduced expression preceding the position at which we are during parsing. Now for this addition, we should take out the last 2 elements from the list, and then we should put the result back. Next we have an operand. We are at this stage right now. Next we have an operator, this subtraction. We will perform this subtraction and put the result back. Finally, when I'm done scanning the whole expression, I'll have only 1 element left in the list, and this will be my final answer. This will be my final result. This is an efficient algorithm. We are doing only 1 pass on the string representing the expression, and we have our result. The list that we are using here, if you could notice, is being used in a special way. We are inserting operands one at a time from one side, and then to perform an operation, we are taking out operand from the same side. Whatever is coming in last is getting out first. This whole thing that we are doing here with the list can be done efficiently with a stack, which is nothing but a special kind of list in which elements are inserted and removed from the same side, in which whatever gets in last comes out first. It's called a last in first out structure. Let's do this evaluation again. I have drawn logical representation of stack here, and this time I'm going to use this stack. I'll also write pseudocode for this algorithm. I'm going to write a function named evaluate postfix that will take a string as argument. Let's name this string expression, exp for expression. In my function here, I'll first create a stack. Now, for the sake of simplicity, let's assume that each operand or operator in the expression will be of only one character. So to get a token or operator, we can simply run a loop from 0 till length of expression minus 1. So expression I will be my operand or operator. If expression I is operand, I should push it onto the stack. Else, if expression I is operator, we should do two pop operations in the stack, store the value of the operands in some variable. I'm using variables named op1 and op2. Let's say this pop function will remove an element from top of stack S and also return this element. Once we have the two operands, we can perform the operation. I'm using this variable to store the output. Let's say this function will perform the operation. Now the result should be pushed back onto the stack. If I have to run through this expression with whatever code I have right now, then first entity is 2, which is operand, so it should be pushed onto the stack. Next we have 3. Once again this will go to the stack. Next we have this multiplication operator. So we will come to this else if part of the code. I'll make first pop and I'll store 3 in this variable op1. Well, actually this is the second operand, so I should say this one is op2 and next one will be op1. Once I have popped these two elements, I can perform the operation. As you can see, I'm doing the same stuff that I was doing with the list. The only thing is that I'm showing things vertically. Stack is being shown as a vertical list. I'm inserting or taking out from the top. Now I'll push the result back onto the stack. Now we will move to the next entity, which is operand. It will go onto the stack. Next 4 will also go onto the stack. And now we have this multiplication. So we will perform two pop operations. After this operation is performed, result will be pushed back. Next we have addition. So we will go on like this. We have 26 pushed onto the stack now. Now it's 9 which will go in. And finally we have this subtraction. 26 minus 9. 17 will be pushed onto the stack. At this stage we will be done with the loop. We are done with all the tokens, all the operands and operators. The top of stack can be returned as final result. At this stage we will have only one element in the stack, and this element will be my final result. You will have to take care of some parsing logic in actual implementation. Operand can be a number of multiple digits, and then we will have delimiter like space or comma, so you'll have to take care of that. Parsing operand or operator will be some task. If you want to see my implementation, you can check the description of this video for a link. Okay, so this was postfix evaluation. Let's now quickly see how we can do prefix evaluation. Once again, I've written this expression in infix form, and I'll first convert it to prefix. We will go in order of precedence. I first put this parenthesis. This 2 asterisk 3 will become asterisk 2 3. This 5 into 4 will become asterisk 5 4. And now we will pick this plus operator, whose operands are these two prefix expressions. Finally, for the subtraction operator, this is the first operand and this is the second operand. In the last step we can get rid of all the parentheses. So this is what I have finally. Let's now see how we can evaluate a prefix expression like this. We will do it just like postfix. This time all we need to do is we need to scan from right. So we will go from right to left. Once again we will use a stack. If it's an operand, we can push it onto the stack. So here for this example, 9 will go onto the stack. And now we will go to the next entity in the left. It's 4. Once again we have an operand. It will go onto the stack. Now we have 5. 5 will also be pushed onto the stack. And now we have this multiplication operator. At this stage we need to pop two elements from the stack. This time the first element popped will be the first operand. In postfix the first element popped was the second operand. This time the second element popped will be the second operand. For this multiplication, first operand is 5 and second operand is 4. This order is really important. For multiplication, the order doesn't matter, but for say division or subtraction this will matter. Result 20 will be pushed onto the stack, and we will keep moving left. Now we have 3 and 2, both will go onto the stack, and now we have this multiplication operation. 3 and 2 will be popped and their product 6 will be pushed. Now we have this addition. The two elements at top are 20 and 6, they will be popped, and their sum 26 will be pushed. Finally we have this subtraction. 26 and 9 will be popped out and 17 will be pushed. And finally this is my answer. Prefix evaluation can be performed in a couple of other ways also, but this is easiest and most straightforward. Okay, so this was prefix and postfix evaluation using stack. In coming lessons we will see efficient algorithms to convert infix to prefix or postfix. This is it for this lesson. Thanks for watching. In our previous lesson we saw how we can evaluate prefix and postfix expressions. Now in this lesson we will see an efficient algorithm to convert infix to postfix. We already know of one way of doing this. We have seen how we can do this manually. To convert an infix expression to postfix, we apply operator precedence and associativity rules. Let's do the conversion for this expression that I have written here. The precedence of multiplication operator is higher. So we will first convert this part, b asterisk c. b asterisk c will become bc asterisk. The operator will come in front of the operands. Now we can do the conversion for this addition. For addition the operands are a and this postfix expression. In the final step we can get rid of all the parentheses. So finally this is my postfix expression. We can use this logic in a program also, but it will not be very efficient, and the implementation will also be somewhat complex. I'm going to talk about one algorithm which is really simple and efficient, and in this algorithm we need to parse the infix expression only once from left to right, and we can create the postfix expression. If you can see, in infix to postfix conversion the positions of operands and operators may change, but the order in which operands occur from left to right will not change. The order of operators may change. This is an important observation. In both infix and postfix forms here, the order of operands as we go from left to right is, first we have A, then we have B, and then we have C. But the order of operators is different. In infix, first we have plus and then we have multiplication. In postfix, first we have multiplication and then addition. In postfix form, we will always have the operators in the same order in which they should be executed. I'm going to perform this conversion once again, but this time I'm going to use a different logic. What I'll do is I'll parse the infix expression from left to right. So I'll go from left to right looking at each token that will either be an operand or an operator. In this expression we will start at A. A is an operand. If it's an operand, we can simply append it in the postfix string or expression that we are trying to create. At least for A, it should be very clear that there is nothing that can come before A. Okay, so the first rule is that if it's an operand, we can simply put it in the postfix expression. Moving on, next we have an operator. We cannot put the operator in the postfix expression because we have not seen its right operand yet. While parsing, we have seen only its left operand. We can place it only after its right operand is also placed. So what I'm going to do is I'm going to keep this operator in a separate list or collection and place it later in the postfix expression when it can be placed. And the structure that I'm going to use for storage is stack. A stack is only a special kind of list in which whatever comes in last goes out first. Insertion and deletion happen from the same end. I have pushed plus operator onto the stack here. Moving on, next we have B, which is an operand. As we had said, operand can simply be appended. There is nothing that can come before this operand. The operator in the stack is anyway waiting for the operand to come. Now at this stage, can we place the addition operator in the postfix string? Well, actually what's after B also matters. In this case we have this multiplication operator after B, which has higher precedence, and so the actual operand for addition is this whole expression B asterisk C. We cannot perform the addition until multiplication is finished. So while parsing, when I'm at B and I have not seen what's ahead of B, I cannot decide the fate of the operator in the stack. So let's just move on. Now we have this multiplication operator. I want to make this expression further complex to explain things better. So I'm adding something at tail here in this expression. Now I want to convert this expression to postfix form. I'm not having any parenthesis here. We will see how we can deal with parenthesis later. Let's look at an expression where parenthesis does not override operator precedence. Okay, so right now in this expression, while parsing from left to right, we are at this multiplication operator. The multiplication operator itself cannot go into the postfix expression because we have not seen its right operand yet, and until its right operand is placed in the postfix expression, we cannot place it. The operator that we would be looking at while parsing, that operator itself cannot be placed right away. But looking at that operator, we can decide whether something from the collection, something from the stack, can be placed into the postfix expression that we are constructing or not. Any operator in the stack having higher precedence than the operator that we are looking at can be popped and placed into the postfix expression. Let's just follow this as rule for now, and I'll explain it later. There is only one operator in the stack and it is not having higher precedence than multiplication, so we will not pop it and place it in the postfix expression. Multiplication itself will be pushed. If an element in the stack has something on top of it, that something will always be of higher precedence. So let's move on in this expression now. Now we are at C, which is an operand, so it can simply go. Next we have an operator, subtraction. Subtraction itself cannot go, but as we had said, if there is anything on the stack having higher precedence than the operator that we are looking at, it should be popped out and should go. And the question is why? We are putting these operators in the stack. We are not placing them in the postfix expression because we are not sure whether we are done with their right operand or not. But after that operator, as soon as I'm getting an operator of lower precedence, that marks the boundary of the right operand. For this multiplication operator, C is my right operand. It's this simple variable. For addition, B asterisk C is my right operand. Because subtraction has lower precedence, anything on or after that cannot be part of my right operand. Subtraction, I should say, has lower priority because of the associativity rule. If you remember the order of operation, addition and subtraction have same precedence, but the one that would occur in left would be given preference. So the idea is, anytime for an operator, if I'm getting an operator of lower priority, we can pop it from the stack and place it in the expression. Here we will first pop multiplication and place it, and then we can pop addition. And now we will push subtraction onto the stack. Let's move on now. D is an operand, so it will simply go. Next we have multiplication. There is nothing in the stack having higher precedence than multiplication, so we will pop nothing. Multiplication will go onto the stack. Next we have an operand. It will simply go. Now there are two ways in which we can find the end of right operand for an operator. A is if we get an operator of lesser precedence. B if we reach the end of the expression. Now that we have reached end of expression, we can simply pop and place these operators. So first multiplication will go and then subtraction will go. Let's quickly write pseudocode for whatever I have said so far, and then you can sit with some examples and analyze the logic. I'm going to write a function named infix to postfix that will take a string exp for expression as argument. For the sake of simplicity, let's assume that each operand or operator will be of one character only. In an actual implementation, you can assume them to be tokens of multiple characters. So in my pseudocode here, the first thing that I'll do is I'll create a stack of characters named S. Now I'll run a loop starting 0 till length of expression -1. So I'm looking at each character that can either be an operand or operator. If the character is an operand, we can append it to the postfix string. Well, actually I should have declared and initialized a string before this loop. this is the result string in which I'll be appending. Else, if expression I is operator, we need to look for operators in the stack having higher precedence. So I'll say while stack is not empty and the top of stack has higher precedence, and let's say this function has higher precedence, we'll take two arguments, two operators. So if the top of stack has higher precedence than the operator that we are looking at, we can append the top of stack to the result, which is the variable that will store the postfix string, and then we can pop that operator. I'm assuming that this S is some class that has these functions top and pop, and empty to check whether it's empty or not. Finally, once I'm done with the popping, outside this while loop I need to push the current operator. S is an object of some class that will have these functions top, pop, and empty. Okay, so this is the end of my for loop. At the end of it, I may have some operators left in the stack. I'll pop these operators and append them to the postfix string. I'll use this while loop. I'll say that while the stack is not empty, append the operator at top and pop it. And finally, after this while loop, I can return the result string that will contain my postfix expression. So this is my pseudocode for whatever logic I've explained so far. In my logic, I've not taken care of parentheses. What if my infix expression would have parentheses like this? There will be slight change from what we were doing previously. With parentheses, any part of the expression within parentheses should be treated as independent, complete expression in itself, and no element outside the parentheses will influence its execution. In this expression, this part a plus b is within one parenthesis. Its execution will not be influenced by this multiplication or this subtraction, which is outside it. Similarly, this whole thing is within the outer parenthesis. So this multiplication operator outside will not have any influence on execution of this part as a whole. If parentheses are nested, inner parenthesis is sorted out or resolved first, and then only outer parenthesis can be resolved. With parentheses, we will have some extra rules. We will still go from left to right, and we will still use stack. And let's say I'm going to write the postfix part in right here as I create it. Now while parsing, a token can be an operand, an operator, or an opening or closing of parenthesis. We will have some extra rules. I'll first tell them and then I'll explain. If it's an opening parenthesis, we can push it onto the stack. The first token here in this example is an opening parenthesis, so it will be pushed onto the stack and then we will move on. We have an opening parenthesis once again, so once again we will push it. Now we have an operand. There is no change in rule for operand. It will simply be appended to the postfix part. Next we have an operator. Remember what we were doing for operator earlier. We were looking at top of stack and popping as long as we were getting operator of higher precedence. Earlier, when we were not using parentheses, we could go on popping and empty the stack. But now we need to look at top of stack and pop only till we get an opening parenthesis. Because if we are getting an opening parenthesis, then it's the boundary of the last opened parenthesis, and this operator does not have any influence after that, outside that. So this plus operator does not have any influence outside this opening parenthesis. I'll explain this scenario with some more examples later. Let's first understand the rule. So the rule is, if I'm seeing an operator, I need to look at the top of stack. If it's an operator of higher precedence, I can pop, and then I should look at the next stop. If it's once again an operator of higher precedence, I should pop again, but I should stop when I see an opening parenthesis. At this stage we have an opening parenthesis at top, so we do not need to look below it. Nothing will be popped anyway. Addition, however, will go onto the stack. Remember, after the whole popping game, we push the operator itself. Next we have an operand. It will go and we will move on. Next we have a closing of parenthesis. When I'm getting a closing of parenthesis, I'm getting a logical end of the last opened parenthesis. For part of the expression within that parenthesis, it's coming to the end. And remember what we were doing earlier when we were reaching the end of infix expression. We were popping all the operators out. and placing them. So this time also we need to pop all the operators out, but only those operators that are part of this parenthesis that we are closing. So we need to pop all the operators until we get an opening parenthesis. I'm popping this plus and appending it. Next we have an opening of parenthesis, so I'll stop, but as last step I will pop this opening also, because we are done for this parenthesis. Okay, so the rule for closing of parenthesis is pop until you are getting an opening parenthesis, and then finally pop that particular opening parenthesis also. Let's move on now. Next we have an operator. We need to look at top of stack. It's an opening of parenthesis. This operator will simply be pushed. Next we have an operand. Next we have an operator. Once again we will look at the top. We have multiplication, which is higher precedence. So this should be popped and appended. We will look at the top again. It's an opening of parenthesis, so we should stop looking now. Minus will be pushed now. Next we have an operand. Next we have closing of parenthesis. So we need to pop until we get an opening. Minus will be appended. Finally the opening will also be popped. Next we have an operator, and this will simply go. Next we have an operand, and now we have reached the end of expression. So everything in the stack will be popped and appended. So this finally is my postfix expression. I'll take one more example and convert it to make things further clear. I want to convert this expression. I'll start at the beginning. First we have an operand, then this multiplication operator, which will simply go onto the stack. The stack right now is empty. There is nothing on the top to compare it with. Next we have an opening parenthesis, which will simply go. Next we have an operand, it will be appended. And now we move on to this addition operator. If this opening parenthesis was not there, the top of stack would have been the multiplication operator, which has higher precedence, so it would have been popped. But now we will look at the top, and it's an opening parenthesis, so we cannot look below, and we will simply have to move on. Next we have C. I missed pushing the addition operator last time. Okay, after C we have this closure, so we need to pop until we get an opening, and then we need to pop one opening also. Finally we have reached the end of expression, so everything in the stack will be popped and appended. So this finally is my postfix part, postfix form. In my pseudocode that I had written earlier, only the part within this for loop will change to take care of parenthesis. In case we have an operator, we need to look at top of the stack and pop, but only till we are getting an opening parenthesis. So I have put this extra condition in the while loop. This condition will make sure that we stop once we get an opening parenthesis. Right now in the for loop we are dealing with operand and operators. We will have two more conditions. If it's an opening of parenthesis, we should push, else if it's a closer, we can go on popping and appending. Let's say this function is opening parenthesis. We'll check whether a character is opening of parenthesis or not. In fact, we should use this function here also when I'm checking whether current token is opening or not, because it could be an opening curly brace or opening bracket also. This function will then take care. Let's say this function will take care. And similarly for this last else if, we should use this function is closing parenthesis. Okay, things are consistent now. After this while loop, in the last else if, we should do one extra pop, and this extra pop will pop the opening parenthesis. And now we are done with this else if, and this is closure of my for loop. Rest of the stuff will remain same. After the for loop we can pop the leftovers and append to the string, and finally we can return. So this is my final pseudocode. You can check the description of this video for a link to real implementation, actual source code. Okay, so I'll stop here now. This is it for this lesson. Thanks for watching. Hello everyone. We have been talking about data structures for some time now. As we know, data structures are ways to store and organize data in computers. So far in this series we have discussed some of the data structures like arrays, linked lists, and in last couple of lessons we have talked about stack. In this lesson we are going to introduce you to queues. We are going to talk about QADT just the way we did it for stacks. First we are going to talk about queue as abstract data type, or ADT. As we know, when we talk about a data structure as abstract data type, We define only the features or operations available with the data structure and do not go into implementation details. We will see possible implementations in later lessons. In this lesson, we are only going to discuss logical view of queue data structure. Okay, so let's get started. Queue data structure is exactly what we mean when we say queue in real world. A queue is a structure in which whatever goes in first comes out first. In short, we call queue a FIFO structure. Earlier we had seen stack, which is a last in first out structure, which is called a last in first out structure, or in short LIFO. A stack is a collection in which both insertion and removal happen from the same end, that we call the top of stack. In queue, however, an insertion must happen from one end, that we call rear or tail of the queue, and any removal must happen from the other end, that we can call front or head of the queue. If I have to define queue formally as an abstract data type, then a queue is a list or collection with the restriction or constraint that insertion can be and must be performed at one end, that we call the rear of queue or the tail of queue, and deletion can be performed at other end, that we can call the front of queue or head of queue. Let's now define the interface or operations available with queue. Just like stack, we have two fundamental operations here. An insertion is called enqueue operation. Some people also like to name this operation push. Enqueue operations should insert an element at tail or rear end of queue. Deletion is called dequeue operation. In some implementations, people call this operation pop also. Push and pop are more famous in context of stack. Enqueue and dequeue are more famous in context of queues. While implementing, you can choose any of these names in your interface. Dequeue should remove an element from front or head of the queue, and dequeue typically also returns this element that it removes from the head. The signatures of enqueue and dequeue for a queue of integers can be something like this. Enqueue is returning void here, while dequeue is returning an integer. This integer should be the removed element from the queue. You can design dequeue also to return void. Typically, a third operation, front or peek, is kept just to look at the element at the head, just like the top operation that we had kept in stack. This operation should just return the element at front and should not delete anything. Okay, we can have few more operations. We can have one operation to check whether queue is empty or not. If queue has a limited size, then we can have one operation to check whether queue is full or not. Why I'm calling out these alternate names for operations is also because most of the time we do not write our own implementation of a data structure. We use inbuilt implementations available with language libraries. Interface can be different in different language libraries. For example, if you would use the inbuilt queue in C++, the function to insert is push, while in C# it's enqueue. So we should not confuse. I'll just keep more famous names here. Okay, so these are the operations that I have defined with queue ADT, enqueue, dequeue, front, and is empty. We can insert or remove one element at a time from the queue using enqueue and dequeue. Front is only to look at the element at head. Is empty is only to verify whether queue is empty or not. All these operations that I have written here must take constant time, or in other words, their time complexity should be big O of 1. Logically, a queue can be shown as a figure or container open from two sides. So an element can be inserted or enqueued from one side, and an element can be removed or dequeued from other side. If you remember stack, we show a stack as a container open from one side. So an insertion, or what we call push in context of stack, and removal or pop both must happen from the same side. In queue, insertion and removal should happen from different sides. Let's say I want to create a queue of integers. Let's say initially we have an empty queue. I will first write down one of the operations and then show you the simulation in logical view. Let's say I first want to enqueue number 2. This figure that I'm showing here right now is an empty queue of integers, and I'm saying that I'm performing an enqueue operation here. In a program I would be calling an enqueue function, passing it number 2 as argument. After this enqueue, we have one element in the queue, we have one integer in the queue. Because we have only one element in the queue right now, front and rear of the queue are same. Let's enqueue one more integer. Now I want to insert number 5. 5 will be inserted at rear or tail of the queue. Let's enqueue one more. And now I want to call dequeue operation. So we will pick 2 from head of the queue and it will go out. If dequeue is supposed to return this removed integer, then we will get integer 2 as return. Enqueue and dequeue are the fundamental operations available with queue. In our design we can have some more for our convenience, like we have front and is empty here. A call to front at this stage will get us number 5, integer 5 as return. No integer will be removed from the queue. Calling is empty at this stage can return us a boolean false, or a 0 for false and 1 for true. So this pretty much is how queue works. Now one obvious question can be, what are the real scenarios where we can use queue? What are the use cases of queue data structure? Queue is most often used in a scenario where there is a shared resource that's supposed to serve some requests, but the resource can handle only one request at a time. It can serve only one request at a time. In such a scenario, it makes most sense to queue up the requests. The request that comes first gets served first. Let's say we have a printer shared in a network. Any machine in the network can send a print request to this printer. Printer can serve only one request at a time. It can print only one document at a time. So if a request comes when it's busy, it can't be like, I'm busy, request later. That will be really rude of the printer. What really happens is that the program that manages the printer puts the print request in a queue. As long as there is something in the queue, printer keeps picking up a request from the front of the queue and serves it. Processor on your computer is also a shared resource. A lot of running programs or processes need time of the processor, but the processor can attend to only one process at a time. Processor is the guy who has to execute all the instructions, who has to perform all the arithmetic and logical operations. So the processes are put in a queue. Queues in general can be used to simulate wait in a number of scenarios. We will discuss some of these applications of queue in detail while solving some problems in later lessons. This is good for an introduction. In next lesson we will see how we can implement queue. This is it for this lesson. Thanks for watching. In our previous lesson we introduced you to queue data structure. We talked about queue as abstract data type, or ADT. As we know, when we talk about a data structure as abstract data type, we define it as a mathematical or logical model. We define only the features or operations available with the data structure and do not go into implementation details. In this lesson we are going to discuss possible implementations of queue. I will do a quick recap of what we have discussed so far. A queue is a list or collection with this restriction, with this constraint, that insertion can be performed at one end, that we call rear of queue or tail of queue, and deletion can be performed at other end, that we call the front of queue or the head of queue. An insertion in queue is called enqueue operation. A deletion is called dequeue operation. I have defined queue ADT with these 4 operations that I have written here. In an actual implementation, all these operations will be functions. Front operation should simply return the element at front of queue. It should not remove any element from the queue. Is empty should simply check whether Q is empty or not. And all these operations must take constant time. NQ, DQ, or looking at the element at front, the time taken for any of these operations must not depend upon a variable like number of elements in Q, or in other words, time complexity of all these operations must be big O of 1. Okay, so let's get started. We are saying that a queue is a special kind of list in which elements can be inserted or removed one at a time, and insertion and removal happen at different ends of the queue. We can insert an element at one end and we can remove an element from the other end. Just the way we did it for stack, we can add these constraints or extra properties of queue to some implementation of a list and create a queue. There are two popular implementations of queue. We can have an array-based implementation and we can have linked list based implementation. Let's first discuss array-based implementation. Let's say we want to create a queue of integers. What we can do is we can first create an array of integers. I have created an array of 10 integers here. I have named this array A. Now what I'm going to do is I'm going to use this array to store my queue. What I'm going to say is that at any point, some part of the array starting an index marked as front till an index marked as rear will be my queue. In this array, I'm showing front of the queue towards left and rear towards right. In earlier examples, I was showing front towards right and rear towards left. Doesn't really matter. Any side can be front and any side can be rear. It's just that an element must always be added from rear side and must always be removed from front. So if at any stage a segment of the array from an index marked as front till an index marked as rear is my queue, and rest of the positions in the array are free space that can be used to expand the queue. To insert an element to NQ, we can increment rear. So we will add a new cell in the queue towards rear end, and in this cell we can write the new value. Element to be inserted can come to this position. I'll fill in some values here at these positions. So we have these integers in the queue, and let's say we want to insert number 5. To insert, we will increment rear. Of course, there should be an available cell in the right, an available empty cell in the right, and now we can write value 5 here. After insertion, new rear index is 7. And the value at index 7 is 5. Now dequeue means we must remove an element from front of the queue. In this example here, a dequeue operation should remove number 2 from the queue. To dequeue, we can simply increment front, because at any point only the cells starting front till rear are part of my queue. By incrementing front, I have discarded index 2 from the queue, and we do not care what value lies in a cell that is not part of the queue. When we will include a cell in the queue, we will overwrite the value in that cell anyway. So just incrementing front is good enough for dequeue operation. Let's quickly write pseudocode for whatever we have discussed so far. In my code, I will have two variables named front and rear, and initially I'll set them both as -1. Let's say for an empty queue, both front and rear will be -1. To check whether queue is empty or not, we can simply check the value of front and rear, and if they're both -1, we can say that queue is empty. I just wrote isEmpty function here. -1 is not a valid index. For an empty queue, there will be no front and rear. In our implementation, we are saying that we will represent empty state of queue by setting both front and rear as -1. Now let's write the NQ function. NQ will take an integer x as argument. There will be a couple of conditions in NQ. If rear is already equal to maximum index available in array A, we cannot insert or NQ an element. In such scenario, we can return and exit. I would rather use a function named isFull to determine whether queue is full or not. If queue is already full, we can't do much. We should simply exit. Else, if queue is empty, We can add a cell to the queue. We can add cell at index 0 in the queue. And now we can set the value at index rear as x. In all other cases, we can first increment rear and then we can fill in value x at index rear. I can get this statement a rear equal x outside these two conditional statements because it's common to them. So this is my enqueue function. In the example array that I'm showing here, let's enqueue some integers. I'll make calls to enqueue function and show you the simulation in the figure here. Let's say first I want to insert number 2 in the queue. I'm making a call to enqueue function passing number 2 as argument. The queue is empty, so we will set both front and rear as 0. Now we will come to this statement. We will write value 2 at index 0. So this is my queue after one enqueue operation. Front and rear of the queue is same. Let's make another call to enqueue. This time I want to insert number 5. This time queue is not empty, so rear will be incremented. We have added a cell to the queue by incrementing rear, and now we will write the value 5 at the new rear index. Let's enqueue one more number. I have enqueued 7. Let's now write dequeue operation. There will be a couple of cases in dequeue. If the queue is already empty, we cannot remove an element. In this case, we can simply print or throw an error and return or exit. There will be one more special case. If the queue has only one element, in this case, front and rear will not be -1, but they will both be equal because we are already checking for -1 case in isEmpty function in the previous if. In this else if, we can simply check whether front is equal to rear or not. If this is the case, a dequeue will make the queue empty. And to mark the queue as empty, we need to set both front and rear as -1. This is what we had said, that we will represent an empty queue by marking both front and rear as -1. In default or normal scenario, we will simply increment front. We should really be careful about corner cases in any implementation. That's where most of the bugs come. Okay, so this finally is my dequeue function. In this example here, at this stage, let's say we want to perform a dequeue. Queue is not empty and we do not have only one element in the queue. So we will simply increment front. Before incrementing, we could set the value in this cell at index 0 as something, but the value in a cell that is not part of queue anymore doesn't really matter. At this stage, it doesn't really matter what we have at index 0 or index 3 or any other index apart from the segment between front and rear. When we will add a cell in the queue, we will overwrite the value in that cell anyway. Let's now perform some more enqueues and dequeues. I'm enqueuing 3 and then I'm enqueuing 1. With each enqueue, we are incrementing rear. I just performed some more enqueue here. Now let's perform a dequeue. If I'll perform one more enqueue here, rear will be equal to maximum index available in the array. Let's enqueue one more. Now at this stage, we cannot enqueue an element anymore because we cannot increment rear. Enqueue operation will fail now. There are 2 unused cells right now, but with whatever logic we have written, we cannot use these 2 cells that are in the left of front. In fact, this is a real problem. As we will dequeue more and more, all the cells left of front index will never be used again. They will simply be wasted. Can we do something to use these cells? Well, we can use the concept of a circular array. Circular array is an idea that we use in a lot of scenarios. The idea is very simple. As we traverse an array, we can imagine that there is no end in the array. From 0 we can go to 1, from 1 we can go to 2, and finally when we will reach the last index in the array, like in this example when we are at index 9, the next index for me is index 0. We can imagine this array something like this. Remember, this is only a logical way of looking at the array. In circular interpretation of array, if I'm pointing to a position and my current position is I, then the next position or next index will not simply be I plus 1. It will be I plus 1 modulo the number of elements in array or the size of array. Let's say n is the number of elements in array. Then the next position will be I plus 1 modulo n, the modulo operation will get us the remainder upon dividing by n. For any I other than n minus 1, this modulo operation will not have any effect. But for I equal n minus 1, next position will be n modulo n, which will be equal to 0. When you divide a number by itself, the remainder is 0. Previous position in circular interpretation of array will be I plus n minus 1 modulo n. We could simply say I minus 1 modulo n just to make sure this expression inside the parenthesis is always positive. I'm adding n here. Give this some thought. You should be able to get why it should be I plus n minus 1 modulo n. Now with this interpretation of array, we can increment rear in an NQ operation as long as there is any unused cell in the array. I'm going to modify functions in my pseudocode now. IsEmpty will remain the same. We are still saying that for an empty queue, front and rear will be -1. Let's scroll down and come to NQ. Now in circular interpretation, I will call my queue full when the position next to rear in circular interpretation, that we will calculate as rear plus 1 modulo n, will be equal to front. So we will have a situation like this. Right now, the next position to rear in circular interpretation is front. So there is no unused cell. The complete array is exhausted. Nothing will change in this condition. If Q is empty, we can simply set front and rear as 0. In the last else condition, we will increment rear like this. We will say rear is equal to rear plus 1 modulo n, where n is number of elements in the array. With this much change, my NQ function is good. Now let's make a call to NQ and insert something in this array here. I want to insert number 15. We will come to this last else condition. Rear right now is 9, so this expression will be 9 plus 1 modulo n. N is 10 here. The size of this array A is 10 here. This will evaluate to 0. Now my new rear is 0. I will write number 15 here. Let's now see what we need to do in the Q function. Nothing will change in the first two conditions. If Q is already empty, or if there is only one element in the queue, we will handle these cases in same manner. In the final else, when we are incrementing front, we need to increment it in a circular manner. So we will say front equal front plus 1 modulo n, where n is number of elements in the array, total number of elements in the array, or size of array. Now let's perform a dequeue. We will come to this condition. Front right now is 2, so this will be 2 plus 1 modulo 10. One more cell is available to us now. This much is the core of our implementation. Front operation will be really straightforward. We simply need to return the element at front index. Here also we first need to check whether Q is empty or not. We should return a front only when front is not equal to -1. All these operations, all these functions that I have written here will take constant time. Their time complexity will be big O of 1. We are performing simple arithmetic and assignments in the functions and not doing anything costly like running a loop. So time taken will not depend upon size of Q or some other variable. I'll leave this here. It should not be very difficult converting this pseudocode to a running program in a language of your choice. If you want to see my code, you can check the description of this video for a link. Thanks for watching. In our previous lesson, we saw how we can implement Q using arrays. Now in this lesson, we will see how we can implement Q using linked list. Q, as we know from our previous discussions, is a structure in which whatever goes in first comes out first. Q data structure is a list or collection with this restriction that insertion can be performed at one end and deletion can be performed at other end. These are typical operations that we define with Q. An insertion is called in Q operation and a deletion is called dequeue. Front operation, front function should simply return the element at front of list, and isEmpty should check whether Q is empty or not. And all these operations must take constant time. Their time complexity should be big O of 1. When we were implementing Q with arrays, we used the idea of a circular array to implement Q. Then in this case, we have a limitation. The limitation is that array will always have a fixed size, and once all the positions in the array are taken, once the array is exhausted, we have two options. We can either deny insertion, so we can say that the queue is full and we cannot insert anything now, or what we can do is we can create a new larger array and copy the elements from previous array to the new larger array, which will be a costly process. We can avoid this problem if we will use linked list to implement queue. Please note that this representation of circular array that I'm showing here is only a logical way of looking at an array. We can show this array like this also. As I was saying, in an array implementation we will have this question, what if array gets filled, and we need to take care of this. We can either say queue is full, or we can create a new larger array and copy elements from previous filled array into this new larger array. The time taken for this copy operation will be proportional to number of elements in filled array, or in other words we can say that the time complexity of this copy operation will be big O of n. There is another problem with array implementation. We can have a large enough array and queue may not be using most of it. Like right now in this array, 90% of the memory is unused. Memory is an important resource and we should always avoid blocking memory unnecessarily. It's not that some amount of unused memory will be a real problem in a modern day machine. It's just that while designing solutions and algorithms, we should analyze and understand these implications. Let's now see how good we will be with a linked list implementation. I have drawn logical view of a linked list of integers here. Coming back to basic definition of queue, as we know, a queue is a list or collection with this constraint, with this property, that an element must always be inserted from one side of the queue that we call the rear of queue, and an element must always be removed from the other side that we call the front of queue. It's really easy to enforce this property in a linked list. A linked list, as we know, is a collection of entities that we call nodes, and these nodes are stored at non-contiguous locations in memory. Each node contains two fields, one to store data and another to store address of the next node or reference to the next node. Let's assume that nodes in this figure are at addresses 100, 200 and 300 respectively. I have also filled in the address fields. The identity of linked list that we always keep with us is address of the head node. We often name the pointer or reference variable that would store this address head. Okay, so now we are saying that we want to use linked list to implement queue. These are the typical operations that we define with a queue. We can use a linked list like a queue. We can pick one side for insertion or an queue operation. So a node in the linked list must always be inserted from this side. The other side will then be used for dequeue. So if we are picking head side for enqueue operation, a dequeue must always happen from tail. If we are picking tail for enqueue operation, then dequeue must always happen from head. Whatever side we are picking for whatever operation, we need to be taking care of one requirement, and the requirement is that these operations must take constant time, or in other words, their time complexity must be big O of 1. As we know from our previous lessons, the cost of insertion or removal from head side is big O of 1, but the cost of insertion or removal from tail side is big O of n. So here's the deal. In a normal implementation of linked list, if we will insert at one side and remove from other side, then one of these operations, enqueue or dequeue, depending on how we are picking the sides, will cost us big O of n. But the requirement that we have is that both these operations must take constant time. So we definitely need to do something to make sure that both enqueue and dequeue operations take constant time. Let's call this side front and this side rear. So I want to enqueue a node from this side and I want to dequeue from this side. We are good for dequeue operation because removal from front will take constant time, but insertion or enqueue operation will be big O of n. Let's first see why insertion at tail will be costly, and then maybe we can try to do something. To insert at rear end, what we will have to do is first we will have to create a node. We have a new node here. Let's say I've got this node at address 350 and the integer that I want to enqueue is 7. The address part of this node can be set as null. Now what we need to do is we need to build this link we need to set the address part of the last node as address of this newly created node. And to do so, we first need to have a pointer pointing to this last node, storing the address of this last node. In a linked list, the only identity that we always keep with us is address of the head node. To get a pointer to any other node, we need to start at head. So we will first create a pointer temp and we will initially set it to head. And now in one step we can move this pointer variable to the next of whatever node it is pointing to. We use a statement like temp equal temp.next to move to the next node. So from first node we will go to the second node, and then from second we will go to the third node. In this example, third node is the rear node. And now using this pointer temp, we can write the address part of this node and build this link. This whole traversal that we are having to get a pointer from head to tail is what's taking all the time. What we can do is we can avoid this whole traversal. We can have a pointer variable just like head that should always store the address of rear node. I can call this variable tail or rear. Let's call this rear, and let's call this variable that is storing the address of head node front. In any insertion or removal, we will have to update both front and rear now. But now when we will enqueue, let's say I have got a node at address 450 and I want to insert this node at rear end. Now using the rear pointer, we can update the address field here. So we are building this link, and now we can update rear. We will only have to modify some address fields, and time taken for enqueue operation will not depend upon number of nodes in the linked list. So now with this design, both enqueue and dequeue operations will be constant time operations. The time complexity for both will be big O of 1. Let's quickly see how real code in C will look like for this design. I have declared node as a structure with two fields, one to store data and another to store address of next node. And now instead of declaring a pointer variable named head, a pointer to node named head, I'm declaring two pointers, a pointer to node named front and another pointer to node named rear, and initially I'm setting them both as null. Let's say I'm defining these two variables in global scope, so they will be accessible to all functions. My enqueue function will take an integer as argument. In this function, I'll first create a node. I'll use malloc in C or new operator in C++ to create a node in what we call dynamic memory. I'm pointing to the newly created node using this variable which is pointer to node named temp. Now we can have two cases in insertion or enqueue operation. If there is no element in the queue, if the queue is empty, in this case both front and rear will be null. We will simply set both front and rear as address of this new node being pointed to by temp, and we will return or exit. Else, because we already have a pointer to rear node, we will first set the address part of current rear as the address of this newly created node, and then we will modify the address in rear variable to make it point to this newly created node. While writing all of this, I'm assuming that you already know how to implement a linked list. If you want to refresh your concepts, you can check earlier lessons in this series, or you can check the description of this video for a link to lesson on linked list implementation in C or C++. This code will be further clear if I'll show things moving in a simulation. Let's say initially we have an empty queue, so both front and rear will be null. Null is only a macro for address 0. At this stage, let's say we are making a call to enqueue function passing it number 2. Now let's go through the enqueue function and see what will happen. First, we will create a node. Data part of this node will be set as 2 and address part initially will be set as null. Let's say we got this node at address temp at address 100, so a variable named temp is storing this address. This variable is pointing to this node. Right now front and rear are both null, so we will go inside this if condition and simply set both front and rear as 100. When the function will finish execution, temp, which is a local variable, will be cleared from memory. After setting both front and rear as address of this newly created node, we are returning. So this is how the queue will look like after first enqueue. Let's say we are making another call to enqueue function at this stage, passing number 4 as the argument. Once again, a new node will be created. Let's say I got the new node at address 200. This time the queue is not empty, so in this function we will first go to this statement, rear.next equal temp. So we will set the next part of this node at address 100 as the address of the newly created node, which is 200. So we will build this link, and now we will store the address of the new rear node in this variable named rear. So this is how my queue will look like after this second enqueue. Let's do one more enqueue. Let's enqueue number 6. Let's say we got our new node this time at address 300. So this is how our queue will look like. Okay, let's now write dequeue function. In dequeue function, I'll first create a temporary pointer to node in which I'll store the address of the current head or current front. Let's say for this example at this stage I'm making a call to dequeue function. We will have a couple of cases in dequeue also. The queue could be empty, so in this case we can print an error message and return. In case of empty queue, front and rear will both be equal to null. We can check one of these and we will be good. In the case when front and rear will be equal, we will simply set both front and rear as null. In all other cases, we can simply make front point to the next node. So we will simply do a front equal front dot next. But why have we used this temporary pointer to node? Why have I declared this temporary pointer to node in this code? Well, simply incrementing front will not be good enough. In this example, when I'm calling dequeue, I'm first creating temp. Let's walk through whatever code I've written so far. So in the first line I'm creating temp, and then because queue is not empty and there are more than one elements in the queue, I'm setting front as address of the next node. So my queue is good now, all the links are appropriately modified, but this node which was front previously is still in the memory. Anything in dynamic memory has to be explicitly freed. To free this node we will use free function, and to this free function we should be passing address of the node, and that's why we had created temp. With this free, the node will be wiped off from memory. So these are enqueue and dequeue operations for you. And if you can see, there are simple statements in these functions. There are no loops, so these functions will take constant time. Their time complexity will be big O of 1. In the beginning of this lesson, we had also discussed some limitations with array implementation, like what if array gets filled, and that of unused memory. We do not have these limitations in a linked list implementation. We are using some extra memory to store address of next node, but apart from that there is no other major disadvantage. I'll stop here now. You can write rest of the functions like front function to look at the element at front, or is empty function to check whether queue is empty or not yourself. If you want to get my source code, then you can check the description of this video for a link. So thanks for watching. Hello everyone. In this lesson, we'll introduce you to an interesting data structure that has got its application in a wide number of scenarios in computer science. And this data structure is tree. So far in this series, we have talked about what we can call linear data structures. Array, linked list, stack, and queue, all of these are linear data structures. All of these are basically collections of different kinds in which data is arranged in a sequential manner. In all these structures that I'm showing here, we have a logical start and a logical end, and then an element in any of these collections can have a next element and a previous element. So all in all, we have linear or sequential arrangement. Now, as we understand, these data structures are ways to store and organize data in computers. For different kinds of data, we use different kinds of data structure. Our choice of data structure depends upon a number of factors. First of all, it's about what needs to be stored. A certain data structure can be best fit for a particular kind of data. Then we may care for the cost of operations. Quite often we want to minimize the cost of most frequently performed operations. For example, let's say we have a simple list and we are searching for an element in the list most of the time. Then we may want to store the list or collection as an array in sorted order. So we can perform something like binary search really fast. Another factor can be memory consumption. Sometimes we may want to minimize the memory usage. And finally, we may also choose a data structure for ease of implementation, although this may not be the best strategy. Tree is one data structure that's quite often used to represent hierarchical data. For example, let's say we want to show employees in an organization and their positions in organizational hierarchy. Then we can show it something like this. Let's say this is organizational hierarchy of some company. In this company, John is CEO and John has 2 direct reports, Steve and Rama. Then Steve has 3 direct reports. Steve is manager of Lee, Bob and Ella. They may be having some designation. Rama also has 2 direct reports. Then Bob has 2 direct reports, and then Tom has 1 direct report. This particular logical structure that I've drawn here is a tree. Well, you have to look at this structure upside down, and then it will resemble a real tree. The root here is at top, and we are branching out in downward direction. Logical representation of tree data structure is always like this: root at top and branching out in downward direction. Okay, so tree is an efficient way of storing and organizing data that is naturally hierarchical. But this is not the only application of tree in computer science. We will talk about other applications and some of the implementation details, like how we can create such a logical structure in computer's memory later. First, I want to define tree as a logical model. Tree data structure can be defined as a collection of entities called nodes linked together to simulate a hierarchy. Tree is a non-linear data structure. It's a hierarchical structure. The topmost node in the tree is called root of the tree. Each node will contain some data, and this can be data of any type. In the tree that I'm showing in right here, data is name of employee and designation. So we can have an object with 2 string fields, one to store name and another to store designation. Okay, so each node will contain some data and may contain link or reference to some other nodes that can be called its children. Now I'm introducing you to some vocabulary that we use for tree data structure. What I'm going to do here is I'm going to number these nodes in the left tree so I can refer to these nodes using these numbers. I'm numbering these nodes only for my convenience. It's not to show any order. Okay, coming back, as I had said, each node will have some data. We can fill in some data in these circles. It can be data of any type. It can be an integer or a character or a string, or we can simply assume that there is some data filled inside these nodes and we are not showing it. Okay, as we were discussing, a node may have link or reference to some other nodes that will be called its children. Each arrow in this structure here is a link. Okay, now as you can see, the root node, which is numbered 1 by me, and once again this number is not indicative of any order. I could have called the root node number 10 also. So root node has link to these 2 nodes numbered 2 and 3. So 2 and 3 will be called children of 1, and node 1 will be called parent of nodes 2 and 3. I'll write down all these terms that I am talking about. We mentioned root, children and parent. In this tree, 1 is parent of 2 and 3. 2 is child of 1. And now 4, 5 and 6 are children of 2. So node 2 is child of node 1 but parent of nodes 4, 5 and 6. Children of same parent are called sibling. I'm showing siblings in same color here. 2 and 3 are sibling, then 4, 5 and 6 are sibling, then 7, 8 are sibling, and finally 9 and 10 are sibling. I hope you are clear with these terms now. The topmost node in the tree is called root. Root would be the only node without a parent. And then if a node has a direct link to some other node, then we have a parent-child relationship between the nodes. Any node in the tree that does not have a child is called leaf node. All these nodes marked in black here are leaves. So leaf is one more term. All other nodes with at least one child can be called internal nodes. And we can have some more relationships, like parent of parent can be called grandparent. So 1 is grandparent of 4 and 4 is grandchild of 1. In general, if we can go from node A to B walking through the links, and remember these links are not bidirectional, We have a link from 1 to 2, so we can go from 1 to 2, but we cannot go from 2 to 1. When we are walking the tree, we can walk in only one direction. Okay, so if we can go from node A to node B, then A can be called ancestor of B, and B can be called descendant of A. Let's pick up this node number 10. 1, 2, and 5 are all ancestors of 10, and 10 is a descendant of all of these nodes. We can walk from any of these nodes to 10. Okay, let me now ask you some questions to make sure you understand things. What are the common ancestors of 4 and 9? Ancestors of 4 are 1 and 2, and ancestors of 9 are 1, 2, and 5. So common ancestors will be 1 and 2. Okay, next question. Are 6 and 7 sibling? Sibling must have same parent. 6 and 7 do not have same parent. They have same grandparent. One is grandparent of both. Nodes not having same parent but having same grandparent can be called cousins. So 6 and 7 are cousins, and these relationships are really interesting. We can also say that node number 3 is uncle of node number 6 because it's sibling of 2, which is father of 6, or I should say parent of 6. So we have quite some terms in vocabulary of tree. Okay, now I'll talk about some properties of tree. Tree can be called a recursive data structure. We can define tree recursively as a structure that consists of a distinguished node called root and some subtrees, and the arrangement is such that root of the tree contains link to roots of all the subtrees. T1, T2, and T3 in this figure are subtrees. In the tree that I have drawn in left here, we have two subtrees for root node. I'm showing the root node in red, the left subtree in brown, and the right subtree in yellow. We can further split the left subtree and look at it like node number 2 is root of this subtree, and this particular tree with node number 2 as root has 3 subtrees. I'm showing the 3 subtrees in 3 different colors. Recursion basically is reducing something in a self-similar manner. This recursive property of tree will be used everywhere in all implementation and uses of tree. The next property that I want to talk about is in a tree with n nodes, there will be exactly n minus 1 links or edges. Each arrow in this figure can be called a link or an edge. All nodes except the root node will have exactly one incoming edge. If you can see, I'll pick this node number 2. There is only one incoming link. This is incoming link, and these 3 are outgoing links. There will be one link for each parent-child relationship. So in a valid tree, if there are n nodes, there will be exactly n minus 1 edges. One incoming edge for each node except the root. Okay, now I want to talk about these two properties called depth and height. Depth of some node x in a tree can be defined as length of the path from root to node x. Each edge in the path will contribute 1 unit to the length. So we can also say number of edges in path from root to x. The depth of root node will be 0. Let's pick some other node. For this node numbered 5, we have 2 edges in the path from root. So the depth of this node is 2. In this tree here, depth of nodes 2 and 3 is 1, depth of nodes 4, 5, 6, 7 and 8 is 2, and the depth of nodes 9, 10 and 11 is 3. Okay, now height of a node in tree can be defined as number of edges in longest path from that node to a leaf node. So height of some node x will be equal to number of edges in longest path from x to a leaf. In this figure, for node 3, the longest path from this node to any leaf is 2. So height of node 3 is 2. Node 8 is also a leaf node. I'll mark all the leaf nodes here. A leaf node is a node with 0 child. The longest path from node 3 to any of the leaf nodes is 2. So the height of node 3 is 2. Height of leaf nodes will be 0. So what will be the height of root node in this tree? We can reach all the leaves from root node. Number of edges in longest path is 3. So height of the root node here is 3. We also define height of a tree. Height of tree is defined as height of root node. Height of this tree that I'm showing here is 3. Height and depth are different properties, and height and depth of a node may or may not be same. We often confuse between the two. Based on properties, trees are classified into various categories. There are different kinds of trees that are used in different scenarios. Simplest and most common kind of tree is a tree with this property that any node can have at most 2 children. In this figure, node 2 has 3 children. I'm getting rid of some nodes. And now this is a binary tree. Binary tree is most famous, and throughout this series we will mostly be talking about binary trees. The most common way of implementing tree is dynamically created nodes linked using pointers or references, just the way we do for linked list. We can look at the tree like this. In this structure that I have drawn in right here, node has 3 fields. One of the fields is to store data. Let's say middle cell is to store data. The left cell is to store the address of the left child. And the right cell is to store address of right child. Because this is a binary tree, we cannot have more than 2 children. We can call one of the children left child and another right child. Programmatically in C or C++, we can define node as a structure like this. We have 3 fields here. One to store data. Let's say data type is integer. I have filled in some data in these nodes. So in each node we have 3 fields. We have an integer variable to store the data, and then we have 2 pointers to node. One to store the address of the left child, that will be the root of the left subtree, and another to store the address of the right child. We have kept only 2 pointers because we can have at most 2 children in binary tree. This particular definition of node can be used only for a binary tree. For generic trees that can have any number of children, we use some other structure, and I'll talk about it in later lessons. In fact, we will discuss implementation in detail in later lessons. This is just to give you a brief idea of how things will be like in implementation. Okay, so this is cool. We understand what a tree data structure is. But in the beginning we had said that storing naturally hierarchical data is not the only application of tree. So let's quickly have a look at some of the applications of tree in computer science. First application, of course, is storing naturally hierarchical data. For example, the file system on your disk drive, the file and folder hierarchy, is naturally hierarchical data. It's stored in the form of tree. Next application is organizing data, organizing collections for quick search, insertion and deletion. For example, binary search tree that we'll be discussing a lot in next couple of lessons can give us order of log n time for searching an element in it. A special kind of tree called trie is used to store dictionary. It's really fast and efficient and is used for dynamic spell checking. Tree data structure is also used in network routing algorithms, and this list goes on. We'll talk about different kinds of trees and their applications in later lessons. I'll stop here now. This is good for an introduction. In next couple of lessons we'll talk about binary search tree and its implementation. This is it for this lesson. Thanks for watching. In our previous lesson we introduced you to tree data structure. We discussed tree as a logical model and talked briefly about some of the applications of tree. Now in this lesson we will talk a little bit more about binary trees. As we had seen in our previous lesson, binary tree is a tree with this property that each node in the tree can have at most 2 children. We will first talk about some general properties of binary tree, and then we can discuss some special kind of binary trees like binary search tree, which is a really efficient structure for storing ordered data. In a binary tree, as we were saying, each node can have at most 2 children. In this tree that I've drawn here, nodes have either 0 or 2 children. We could have a node with just 1 child. I have added one more node here, and now we have a node with just 1 child. Because each node in a binary tree can have at most 2 children, We call one of the children left child and another right child. For the root node, this particular node is left child and this one is right child. A node may have both left and right child. And these four nodes have both left and right child, or a node can have either of left and right child. This one has got a left child but has not got a right child. I'll add one more node here. Now this node has a right child but does not have a left child. In a program we would set the reference or pointer to left child as null. So we can say that for this node left child is null, and similarly for this node we can say that the right child is null. For all the other nodes that do not have children, that are leaf nodes, a node with zero child is called leaf node. For all these nodes we can say that both left and right child are null. Based on properties we classify binary trees into different types. I'll draw some more binary trees here. If a tree has just one node, then also it's a binary tree. This structure is also a binary tree. This is also a binary tree. Remember, the only condition is that a node cannot have more than two children. A binary tree is called strict binary tree or proper binary tree if each node can have either 2 or 0 children. This tree that I'm showing here is not a strict binary tree because we have two nodes that have one child. I'll get rid of two nodes and now this is a strict binary tree. We call a binary tree complete binary tree if all levels except possibly the last level are completely filled and all nodes are as far left as possible. All levels except possibly the last level will anyway be filled. So the nodes at the last level, if it's not filled completely, must be as far left as possible. Right now this tree is not a complete binary tree. Nodes at same depth can be called nodes at same level. Root node in a tree has depth 0. Depth of a node is defined as length of path from root to that node. In this figure, let's say nodes at depth 0 are nodes at level 0. I can simply say L0 for level 0. Now these two nodes are at level 1. These four nodes are at level 2. And finally these two nodes are at level 3. The maximum depth of any node in the tree is 3. Maximum depth of a tree is also equal to height of the tree. If we will go numbering all the levels in the tree like L0, L1, L2 and so on, then the maximum number of nodes that we can have at some level I will be equal to 2 to the power I. At level 0 we can have one node, 2 to the power 0 is 1. Then at level 1 we can have at max 2 nodes. At level 2 we can have 2 to the power 2 nodes at max, which is 4. So in general at any level I we can have at max 2 to the power I nodes. You should be able to see this very clearly because each node can have two children. So if we have x nodes at a level, then each of these x nodes can have two children. So at next level we can have at most 2x children. Here in this binary tree we have 4 nodes at level 2, which is the maximum for level 2. Now each of these nodes can possibly have two children. I'm just drawing the arrows here. So at level 3 we can have max 2 times 4, that is 8 nodes. Now for a complete binary tree, all the levels have to be completely filled. We can give exception to the last level or deepest level. It doesn't have to be full, but the nodes have to be as left as possible. This particular tree that I'm showing here is not a complete binary tree because we have two vacant node positions in left here. I'll do slight change in this structure. Now this is a complete binary tree. We can have more nodes at level 3, but there should not be a vacant position in left. I have added one more node here and this still is a complete binary tree. If all the levels are completely filled, such a binary tree can also be called perfect binary tree. In a perfect binary tree, all levels will be completely filled. If h is the height of a perfect binary tree, remember height of a binary tree is length of longest path between root to any of the leaf nodes, or I should say number of edges in longest path from root to any of the leaf nodes. Height of a binary tree will also be equal to max depth. Here for this binary tree, height or max depth is 3. maximum number of nodes in a tree with height h will be equal to, we'll have 2 to the power 0 nodes at level 0, 2 to the power 1 nodes at level 1, and we'll go on summing for height h, will go till 2 to the power h. At deepest level we will have 2 to the power h nodes. Now this will be equal to 2 to the power h plus 1 minus 1. H plus 1 is number of levels here. We can also say 2 to the power number of levels minus 1. In this tree, number of levels is 4. We have L0 till L3. So number of nodes, maximum number of nodes will be 2 to the power 4 minus 1, which is 15. So a perfect binary tree will have maximum number of nodes possible for a height, because all levels will be completely filled. Well, I should say maximum number of nodes in a binary tree with height h. Okay, I can ask you this also. What will be height of a perfect binary tree with n nodes? Let's say n is number of nodes in a perfect binary tree. To find out how height, we'll have to solve this equation. N equal 2 to the power h plus 1 minus 1. Because if height is h, number of nodes will be 2 to the power h plus 1 minus 1. We can solve this equation and the result will be this. Remember, n is number of nodes here. I'll leave the maths for you to understand. Height will be equal to log n plus 1 to the base 2 minus 1. In this perfect binary tree that I'm showing here, number of nodes is 15, so n is 15. N plus 1 will be 16, so the h will be log 16 to the base 2 minus 1. Log 16 to the base 2 will be 4. So the final value will be 4 minus 1 equal 3. In general, for a complete binary tree, we can also calculate height as floor of log n to the base 2. So we need to take integral part of log n to the base 2. Perfect binary tree is also a complete binary tree. Here n is 15. Log of 15 to base 2 is 3.906891. If we'll take the integral part, then this will be 3. I'll not go into proof of how height of complete binary tree will be log n to the base 2. We'll try to see that later. All this maths will be really helpful when we will analyze cost of various operations on binary tree. Cost of a lot of operations on tree in terms of time depends upon the height of tree. For example, in binary search tree, which is a special kind of binary tree, the cost of searching, inserting or removing an element in terms of time is proportional to the height of tree. So in such case, we would want the height of the tree to be less. Height of a tree will be less if the tree will be dense, if the tree will be close to a perfect binary tree or a complete binary tree. Minimum height of a tree with n nodes can be log n to the base 2 when the tree will be a complete binary tree. If we will have an arrangement like this, then the tree will have maximum height. With n nodes, minimum height possible is floor of or integral part of log n to the base 2, and maximum height possible with n nodes is n minus 1 when we will have a sparse tree like this, which is as good as a linked list. Now think about this. If I'm saying that time taken for an operation is proportional to height of the tree, or in other words, I can say that if time complexity of an operation is big O of h, where h is height of the binary tree, then for a complete or perfect binary tree, my time complexity will be big O of log n to the base 2. And in worst case, for this sparse tree, my time complexity will be big O of n. Order of log n is almost best running time possible. For n as high as 2 to the power 100, log n to the base 2 is just 100. With order of n running time, if n will be 2 to the power 100, we won't be able to finish our computation in years, even with most powerful machines ever made. So here's the thing, quite often we want to keep the height of a binary tree minimum possible, or most commonly we say that we try to keep a binary tree balanced. We call a binary tree balanced binary tree if for each node the difference between height of left and right subtree is not more than some number k. Mostly k would be 1. So we can say that for each node difference between height of left and right subtree should not be more than 1. There is something that I want to talk about height of a tree. We had defined height earlier as number of edges in longest path from root to a leaf. Height of a tree with just one node, where the node itself will be a leaf node, will be 0. We can define an empty tree as a tree with no node, and we can say that height of an empty tree is -1. So height of tree with just one node is 0 and height of an empty tree is -1. Quite often people calculate height as number of nodes in longest path from root to a leaf. In this figure I have drawn one of the longest paths from root to a leaf. We have 3 edges in this path, so the height is 3. If we will count number of nodes in the path, height will be 4. This looks very intuitive, and I have seen this definition of height at a lot of places. If we will count the nodes, height of tree with just one node will be equal to 1, and then we can say height of an empty tree will be 0. But this is not the correct definition, and we are not going to use this assumption. We are going to say that height of an empty tree is -1 and height of tree with one node is 0. The difference between heights of left and right subtrees of a node can be calculated as absolute value of height of left subtree minus height of right subtree. And in this calculation, height of a subtree can be -1 also. For this leaf node here in this figure, both left and right subtrees are empty. So both h left or height of left subtree and h right or height of right subtree will be -1, but the difference overall will be 0. For all nodes in a perfect tree, difference will be 0. I have got rid of some nodes in this tree, and now by the side of each node I have written the value of diff. This is still a balanced binary tree because the maximum diff for any node is 1. Let's get rid of some more nodes in this tree, and now this is not balanced because one of the nodes has diff 2. For this particular node, height of left subtree is 1 and height of right subtree is -1 because right subtree is empty. So the absolute value of difference is 2. We try to keep a tree balanced to make sure it's dense and its height is minimized. If height is minimized, cost of various operations that depend upon height are minimized. Okay, the next thing that I want to talk about very briefly is how we can store binary trees in memory. One of the ways that we had seen in our previous lesson, which is most commonly used, is dynamically created nodes linked to each other using pointers or references. For a binary tree of integers in C or C++, we can define a node like this. Data type here is integer, so we have a field to store data, and we have 2 pointer variables, one to store address of left child and another to store address of right child. This of course is the most common way. Nodes dynamically created at random locations in memory linked together through pointers. But in some special cases we use arrays also. Arrays are typically used for complete binary trees. I have drawn a perfect binary tree here. Let's say this is a tree of integers. What we can do is we can number these nodes from 0 starting at root and going level by level from left to right. So we'll go like 0, 1, 2, 3, 4, 5 and 6. Now I can create an array of 7 integers, and these numbers can be used as indices for these nodes. So at 0th position I'll fill 2, at 1th position I'll fill 4, at 2th position we'll have 1, and I'll go on like this. We have filled in all the data in the array, but how will we store the information about the links? How will we know that the left child of root has value 4 and the right child of root has value 1? Well, in case of complete binary tree, if we will number the nodes like this, then for a node at index I, the index of left child will be 2i plus 1 and the index of right child will be 2i plus 2. And remember, this is true only for a complete binary tree. For 0, left child is 2i plus 1 for I equals 0 will be 1 and 2i plus 2 will be 2. Now for 1, left child is at index 3, right child is at index 4. For I equal 2, 2i plus 1 will be 5 and 2i plus 2 will be 6. We will discuss array implementation in detail when we will talk about a special kind of binary tree called heap. Arrays are used to implement heaps. I'll stop here now. In our next lesson we will talk about binary search tree, which is also a special kind of binary tree that gives us a really efficient storing structure in which we can search something quickly as well as update it quickly. This is it for this lesson. Thanks for watching. In our previous lesson we talked about binary trees in general. Now in this lesson we are going to talk about binary search tree, a special kind of binary tree which is an efficient structure to organize data for quick search as well as quick update. But before I start talking about binary search trees, I want you to think of a problem. What data structure will you use to store a modifiable collection? So let's say you have a collection and it can be a collection of any data type. Records in the collection can be of any type. Now you want to store this collection in computer's memory in some structure, and then you want to be able to quickly search for a record in the collection, and you also want to be able to modify the collection. You want to be able to insert an element in the collection or remove an element from the collection. So what data structure will you use? Well, you can use an array or a linked list. These are two well-known data structures in which we can store a collection. Now what will be the running time of these operations, search, insertion or removal, if we will use an array or a linked list? Let's first talk about arrays, and for sake of simplicity let's say we want to store integers. To store a modifiable list or collection of integers, we can create a large enough array and we can store the records in some part of the array. We can keep the end of the list marked. In this array that I'm showing here, we have integers from 0 till 3, we have records from 0 till 3, and rest of the array is available space. Now to search some X in the collection, we will have to scan the array from index 0 till end, and in worst case we may have to look at all the elements in the list. If n is the number of elements in the list, time taken will be proportional to n, or in other words we can say the time complexity of this operation will be big O of n. Okay, now what will be the cost of insertion? Let's say we want to insert number 5 in this list. So if there is some available space, all these cells in yellow are available, we can add one more cell by incrementing this marker end, and we can fill in the integer to be added. The time taken for this operation will be constant. Running time will not depend upon number of elements in the collection. So we can say that time complexity will be big O of 1. Okay, now what about removal? Let's say we want to remove 1 from the collection. What we'll have to do is we'll have to shift all records to the right of 1 by 1 position to the left, and then we can decrement end. The cost of removal in worst case once again will be big O of n. In worst case we will have to shift n minus 1 elements. Here the cost of insertion will be big O of 1 if the array will have some available space. So the array has to be large enough. If the array gets filled, what we can do is we can create a new larger array. Typically we create an array twice the size of the filled up array. So we can create a new larger array and then we can copy the content of the filled up array into this new larger array. The copy operation will cost us big O of n. We have discussed this idea of dynamic array quite a bit in our previous lessons. So insertion will be big O of 1 if array is not filled up, and it will be big O of n if array is filled up. For now let's just assume that the array will always be large enough. Let's now discuss the cost of these operations if we will use a linked list. If we would use a linked list, I have drawn a linked list of integers here. Data type can be anything. The cost of search operation once again will be big O of n, where n is number of records in the collection or number of nodes in the linked list. To search, in worst case we will have to traverse the whole list. We will have to look at all the nodes. The cost of insertion in a linked list is big O of 1 at head, and it's big O of n at tail. We can choose to insert at head to keep the cost low. So running time of insertion we can say is big O of 1, or in other words we will take constant time. Removal once again will be big O of n. We will first have to traverse the linked list and search the record, and in worst case we may have to look at all the nodes. Okay, so this is the cost of operations if we are going to use array or linked list. Insertion definitely is fast, but how good is big O of n for an operation like search? What do you think? If we are searching for a record X, then in the worst case, we will have to compare this record X with all the n records in the collection. Let's say our machine can perform 1,000,000 comparisons in 1 second. So we can say that machine can perform 10 to the power 6 comparisons in 1 second. So cost of one comparison will be 10 to the power minus 6 second. Machines in today's world deal with really large data. It's very much possible for real world data to have 100 million or billion records. A lot of countries in this world have population more than 100 million. 2 countries have more than 1 billion people living in them. If we will have data about all the people living in a country, then it can easily be 100 million records. Okay, so if we are saying that the cost of one comparison is 10 to the power minus 6 second, if n will be 100 million, time taken will be 100 seconds. 100 seconds for a search is not reasonable, and search may be a frequently performed operation. Can we do something better? Can we do better than big O of n? Well, in an array, we can perform binary search if it's sorted. And the running time of binary search is big O of log n, which is the best running time to have. I have drawn this array of integers here. Records in the array are sorted. Here the data type is integer. For some other data type, for some complex data type, we should be able to sort the collection based on some property or some key of the records. We should be able to compare the keys of records, and the comparison logic will be different for different data types. For a collection of strings, for example, we may want to have the records sorted in dictionary or lexicographical order. So we will compare and see which string will come first in dictionary order. Now this is the requirement that we have for binary search. The data structure should be an array and the records must be sorted. Okay, so the cost of search operation can be minimized if we will use a sorted array, but in insertion or removal we will have to make sure that the array is sorted afterwards. In this array, if I want to insert number 5 at this stage, I can't simply put 5 at index 6. What I'll have to do is I'll first have to find the position at which I can insert 5 in the sorted list. We can find the position in order of log n time using binary search. We can perform a binary search to find the first integer greater than 5 in the list. So we can find the position quickly. In this case it's index 2, but then we will have to shift all the records starting this position, one position to the right. And now I can insert 5. So even though we can find the position at which a record should be inserted quickly in big O of log n, this shifting in worst case will cost us big O of n. So the running time overall for an insertion will be big O of n. And similarly, the cost of removal will also be big O of n. We will have to shift some records. Okay, so when we are using sorted array, cost of search operation is minimized. In binary search for n records, we will have at max log n to the base 2 comparisons. So if we can perform million comparisons in a second, then for n equal 2 to the power 31, which is greater than 2 billion, we are going to take only 31 microseconds. Log of 2 to the power 31 to base 2 will be 31. Okay, we are fine with search now. We will be good for any practical value of n. But what about insertion and removal? They are still big O of n. Can we do something better here? Well, if we will use this data structure called binary search tree, I'm writing it in short, BST for binary search tree, then the cost of all these 3 operations can be big O of log n. In average case, the cost of all the operations will be big O of n in worst case, but we can avoid the worst case by making sure that the tree is always balanced. We had talked about balanced binary tree in our previous lesson. Binary search tree is only a special kind of binary tree. To make sure that the cost of these operations is always big O of log n, we should keep the binary search tree balanced. We'll talk about this in detail later. Let's first see what a binary search tree is and how cost of these operations is minimized when we use a binary search tree. Binary search tree is a binary tree in which for each node, value of all the nodes in left subtree is lesser and value of all the nodes in right subtree is greater. I have drawn binary tree as a recursive structure here. As we know, in a binary tree, each node can have at most 2 children. We can call one of the children left child. If we will look at the tree as a recursive structure, left child will be the root of left subtree, and similarly right child will be the root of right subtree. Now for a binary tree to be called binary search tree, value of all the nodes in left subtree must be lesser, or we can say lesser or equal to handle duplicates, and the value of all the nodes in right subtree must be greater, and this must be true for all the nodes. So in this recursive structure here, both left and right subtrees must also be binary search trees. I'll draw a binary search tree of integers. Now I have drawn a binary search tree of integers here. Let's see whether this property that for each node value of all the nodes in left subtree must be lesser or equal and value of all the nodes in right subtree must be greater is true or not. Let's first look at the root node. Nodes in the left subtree have values 10, 8 and 12. So they are all lesser than 15. And in right subtree we have 17, 20 and 25. They are all greater than 15. So we are good for the root node. Now let's look at this node with value 10. In left we have 8, which is lesser. In right we have 12, which is greater. So we are good. We are good for this node too, having value 20. And we don't need to bother about leaf nodes because they do not have children. So this is a binary search tree. Now what if I change this value 12 to 16? Now is this still a binary search tree? Well, for node with value 10 we are good. The node with value 16 is in its right, so not a problem. But for the root node, we have a node in left subtree with higher value now. So this tree is not a binary search tree. I'll revert back and make the value 12 again. Now as we were saying, we can search, insert or delete in a binary search tree in big O of log n time in average case. How is it really possible? Let's first talk about search. If these integers that I have here in the tree were in a sorted array, we could have performed binary search. And what do we do in binary search? Let's say we want to search number 10 in this array. What we do in binary search is we first define the complete list as our search space. The number can exist only within the search space. I'll mark search space using these 2 pointers, start and end. Now we compare the number to be searched or the element to be searched with mid element of the search space or the median. And if the record being searched, if the element being searched is lesser, we go searching in the left half, else we go searching in the right half. In case of equality, we have found the element. In this case 10 is lesser than 15, so we will go searching towards left. Our search space is reduced now to half. Once again we will compare to the mid element and bingo, this time we have got a match. In binary search we start with n elements in search space, and then if mid element is not the element that we are looking for, we reduce the search space to n by 2 and we go on reducing the search space to half till we either find the record that we are looking for or we get to only one element in search space and be done. In this whole reduction, if we will go from n to n by 2 to n by 4 to n by 8 and so on, we will have log n to the base 2 steps. If we are taking k steps, then n upon 2 to the power k will be equal to 1, which will imply 2 to the power k will be equal to n and k will be equal to log n to the base 2. So this is why running time of binary search is big O of log n. Now if we'll use this binary search tree to store the integers, search operation will be very similar. Let's say we want to search for number 12. What we'll do is we'll start at root and then we will compare the value to be searched, the integer to be searched with value of root. If it's equal, we are done with the search. If it's lesser, We know that we need to go to the left subtree because in a binary search tree, all the elements in left subtree are lesser and all the elements in right subtree are greater. Now we'll go and look at the left child of node with value 15. We know that number 12 that we are looking for can exist in this subtree only, and anything apart from this subtree is discarded. So we have reduced the search space to only these three nodes having value 10, 8 and 12. Now once again we'll compare 12 with 10. We are not equal. 12 is greater. So we know that we need to go looking in right subtree of this node with value 10. So now our search space is reduced to just one node. Once again we will compare the value here at this node and we have a match. So searching an element in binary search tree is basically this traversal in which at each step we will go either towards left or right, and hence at each step we will discard one of the subtrees. If the tree is balanced, we call a tree balanced if for all nodes the difference between the heights of left and right subtrees is not greater than 1. So if the tree is balanced, we will start with a search space of n nodes, and when we will discard one of the subtrees, we will discard n by 2 nodes, so our search space will be reduced to n by 2. And then in next step we will reduce the search space to n by 4. We will go on reducing like this till we find the element, or till our search space is reduced to only one node when we will be done. So the search here is also a binary search, and that's why the name binary search tree. This tree that I'm showing here is balanced. In fact, this is a perfect binary tree, but with same records we can have an unbalanced tree like this. This tree has got the same integer values as we had in the previous structure, and this is also a binary search tree, but this is unbalanced. This is as good as a linked list. In this tree there is no right subtree for any of the nodes. Search space will be reduced by only 1 at each step. From n nodes in search space we will go to n-1 nodes, and then to n-2 nodes, all the way till 1 will be n steps. In binary search tree, in average case, cost of search, insertion or deletion is big O of log n, and in worst case, this is the worst case arrangement that I'm showing you, running time will be big O of n. We always try to avoid the worst case by trying to keep the binary search tree balanced. With same records in the tree, there can be multiple possible arrangements. For these integers in this tree, another arrangement is this. For all the nodes we have nothing to discard in left subtree in a search. This is another arrangement. This is still balanced because for all the nodes the difference between the heights of left and right subtrees is not greater than 1. But this is the best arrangement when we have a perfect binary tree. At each step we will have exactly n by 2 nodes to discard. Okay, now to insert some record in binary search tree, we will first have to find the position at which we can insert, and we can find the position in big O of log n time. Let's say we want to insert 19 in this tree. What we will do is we will start at the root. If the value to be inserted is lesser or equal, if there is no child, insert as left child or go left. If the value is greater and there is no right child, insert as right child or go right. In this case 19 is greater, so we will go right. Now we are at 20. 19 is lesser and left subtree is not empty. We have a left child, so we will go left. Now we are at 17. 19 is greater than 17, so it should go in right of 17. There is no right child of 17, so we will create a node with value 19 and link it to this node with value 17 as right child. Because we are using pointers or references here, just like linked list, no shifting is needed. Like an array, creating a link will take constant time. So overall insertion will also cost us like search. To delete also, we will first have to search the node. Search once again will be big O of log n, and deleting the node will only mean adjusting some links. So removal also is going to be like search, big O of log n in average case. Binary search tree gets unbalanced during insertion and deletion. So often during insertion and deletion we restore the balancing. There are ways to do it, and we will talk about all of this in detail in later lessons. In next lesson we will discuss implementation of binary search tree in detail. This is it for this lesson. Thanks for watching. In our previous lesson, we saw what binary search trees are. Now in this lesson, we are going to implement binary search tree. We will be writing some code for binary search tree. Prerequisite for this lesson is that you must understand the concepts of pointers and dynamic memory allocation in C++. If you have already followed this series and seen our lessons on linked list, then implementation of binary search tree or binary tree in general is not going to be very different. We will have nodes and links here as well. Okay, so let's get started. Binary search tree or BST, as we know, is a binary tree in which for each node, value of all the nodes in left subtree is lesser or equal and value of all the nodes in right subtree is greater. We can draw BST as a recursive structure like this. Value of all the nodes in left subtree must be lesser or equal and value of all the nodes in right subtree must be greater, and this must be true for all nodes and not just the root node. So in this recursive definition here, both left and right subtrees must also be binary search trees. I have drawn a binary search tree of integers here. Now the question is, how can we create this non-linear logical structure in computer's memory? I had talked about this briefly when we had discussed binary trees. The most popular way is dynamically created nodes linked to each other using pointers or references, just the way we do it for linked lists. Because in a binary search tree or in a binary tree in general, each node can have at most 2 children, we can define node as an object with 3 fields, something like what I'm showing here. We can have a field to store data, another to store address or reference to left child, and another to store address or reference to right child. If there is no left or right child for a node, reference can be set as null. In C or C++, we can define node like this. There is a field to store data. Here the data type is integer, but it can be anything. There is one field which is pointer to node. Node asterisk means pointer to node. This one is to store the address of left child, and we have another one to store the address of right child. This definition of node is very similar to definition of node for doubly linked list. Remember, in doubly linked list also each node had 2 links, one to previous node and another to next node, but doubly linked list was a linear arrangement. This definition of node is for a binary tree. We could also name this something like BST node, but node is also fine. Let's go with node. Now in our implementation, just like linked list, all the nodes will be created in dynamic memory or heap section of applications memory using malloc function in C or new operator in C++. We can use malloc in C++ as well. Now as we know, any object created in dynamic memory or heap section of applications memory cannot have a name or identifier. It has to be accessed through a pointer. Malloc or new operator return us pointer to the object created in heap. If you want to revise some of these concepts of dynamic memory allocation, you can check the description of this video for link to a lesson. It's really important that you understand this concept of stack and heap in applications memory really well. Now for a linked list, if you remember, the information that we always keep with us is address of the head node. If we know the head node, we can access all other nodes using links. In case of trees, the information that we always keep with us is address of the root node. If we know the root node, we can access all other nodes in the tree using links. To create a tree, we first need to declare a pointer to BST node. I'll rather call node BST node here, BST for binary search tree. So to create a tree, we first need to declare a pointer to BST node that will always store the address of root node. I have declared a pointer to node here named root PTR, PTR for pointer. In C, you can't just write BST node asterisk root PTR. You will have to write struct space BST node asterisk. You will have to write struct here as well. I'm gonna write C++ here. But anyway, right now I'm trying to explain the logic. We will not bother about minute details of implementation. In this logical structure of tree that I'm showing here, each node, as you can see, has 3 fields, 3 cells. Leftmost cell is to store the address of left child and rightmost cell is to store address of right child. Let's say root node is at address 200 in memory and I'll assume some random addresses for all other nodes as well. Now I can fill in these left and right cells for each node with addresses of left and right children. In our definition, data is first field, but in this logical structure I'm showing data in the middle. Okay, so for each node I have filled in addresses for both left and right child. Address is 0 or null if there is no child. Now, as we were saying, identity of the tree is address of the root node. We need to have a pointer to node in which we can store the address of the root node. We must have a variable of type pointer to node to store the address of root node. All these rectangles with 3 cells are nodes. They are created using malloc or new operator and live in heap section of application's memory. We cannot have name or identifier for them. They are always accessed through pointers. This root PTR, root pointer, has to be a local or global variable. We will discuss this in a little more detail in some time. Quite often we like to name this root pointer just root. We can do so, but we must not confuse. This is pointer to root and not the root itself. To create a BST, as I was saying, we first need to declare this pointer. Initially, we can set this pointer as null to say that the tree is empty. A tree with no node can be called empty tree, and for empty tree, root pointer should be set as null. We can do this declaration and setting the root as null in main function in our program. Actually, let's just write this code in a real compiler. I'm writing C++ here. As you can see, in the main function I have declared this pointer to node, which will always store the address of root node of my tree, and I'm initially setting this as null to say that the tree is empty. With this much of code, we have created an empty tree. But what's the point of having an empty tree? We should have some data in it. So what I want to do now is I want to write a function to be able to insert a node in the tree. I will write a function named insert that will take address of the root node and data to be inserted as argument, and this function will insert a node with this data at appropriate position in the tree. In the main function, I'll make calls to this insert function, passing it address of root and the data to be inserted. Let's say first I want to insert number 15, and then I want to insert number 10, and then number 20. We can insert more, but let's first write the logic for insert function. Before I write the logic for insert function, I want to write a function to create a new node in dynamic memory or heap. This function getNewNode should take an integer, the data to be inserted, as argument, create a node in heap using new or malloc, and return back the address of this new node. I'm creating the new node here using this new operator. The operator will return me the address of the newly created node, which I'm collecting in this variable of type pointer to BST node. In C, instead of new operator, we will have to use malloc. We can use malloc in C++ as well. C++ is only a superset of C. Malloc will also do here. Now anything in dynamic memory or heap is always accessed through pointer. Now using this pointer new node, we can access the fields of the newly created node. I'll have to dereference this pointer using asterisk operator. So I'm writing asterisk new node, and now I can access the fields. We have 3 fields in node, data, and 2 pointers to node, left and right. I've set the data here. Instead of writing asterisk new node dot data, we have this alternate syntax that we could use. We could simply write new node arrow data, and this will mean the same. We have used this syntax quite a lot in our lessons on linked list. Now for the new node, we can set the left and right child as null, and finally we can return the address of the new node. Okay, coming back to the insert function. We can have a couple of cases in insertion. First of all, tree may be empty. For this first insertion, when we are inserting this number 15, tree will be empty. If tree is empty, we can simply create a new node and set it as root. With this statement, root equal get new node, I'm setting root as address of the new node, but there is something not alright here. This root is local variable of insert function, and its scope is only within this function. We want this root in main, to be modified. This guy is a local variable of main function. There are two ways of doing this. We can either return the address of the new root. So return type of insert function will be pointer to BST node and not void. And here in the main function we will have to write statement like root equal insert and the arguments. So we will have to collect the return and update our root in main function. Another way is that we can pass the address of this root of main to the insert function. This root is already a pointer to node, so its address can be collected in a pointer to pointer. So insert function, in insert function, first argument will be a pointer to pointer, and here we can pass the address. We'll say ampersand root to pass the address. We can name this argument root, or we can name this argument root ptr. We can name this whatever. Now what we need to do is we need to dereference this using asterisk operator to access the value in root of main, and we can also set the value in root of main. So here with this statement we are setting the value, and the return type now can be void. This pointer to pointer thing gets a little tricky. I'll go with the former approach. Actually, there is another way. Instead of declaring root as a local variable in main function, we can declare root as global variable. Global variable, as we know, has to be declared outside all the functions. If root would be global variable, it would be accessible to all the functions, and we will not have to pass the address stored in it as argument. Anyway, coming back to the logic for insertion, as we were saying, if the tree is empty, we can simply create a new node and we can simply set it as root. At this stage we wanted to insert 15. If we will make call to the insert function, address of root is 0 or null. Null is only a macro for 0, and the second argument is the number to be inserted. In this call to insert function we will make call to get new node. Let's say we got this new node at address 200. Get new node function will return us address 200, which we can set as root here, but this root is a local variable. We will return this address 200 back to the main function, and in the main function we are actually doing this root equal insert. So in the main function we are building this link. Okay, our next call in the main function was to insert number 10. At this stage root is 200, the address in root is 200, and the value to be inserted is 10. Now the tree is not empty, so what do we do? If the tree is not empty, we can basically have two cases. If the data to be inserted is lesser or equal, we need to insert it in the left subtree of root, and if the data to be inserted is greater, we need to insert it in right subtree of the root. So we can reduce this problem in a self-similar manner, in a recursive manner. Recursion is one thing that we are going to use almost all the time while working with trees. In this function, I'll say that if the data to be inserted is less than or equal to the data in root, then make a recursive call to insert data in left subtree. The root of the left subtree will be the left child. So in this recursive call we are passing address of left child and data as argument, and after the data is inserted in left subtree, the root of the left subtree can change. Insert function will return the address of the new root of the left subtree, and we need to set it as left child of the current node. In this example tree here, right now both left and right subtree are empty. We are trying to insert number 10, so we have made call to this function insert. From main function we have called insert, passing it address 200 and value or data 10. Now 10 is lesser than 15, so control will come to this line and a call will be made to insert data in left subtree. Now left subtree is empty, so address of root for left subtree is 0. Data to be inserted passed as argument is 10. Now this first insert call will wait for this insert below to finish and return. For this last insert call, root is null. Let's say we got this node at address 150. Now this insert call will return back 150, and execution of first insert call will resume at this line, and now this particular address will be set as 150, so we will build this link. And now this insert call can finish. It can return back the current root. Actually this return root should be there for all cases, so I'm taking it out and I have it after all these conditions. Of course, we will have one more else here. If the data is greater, we need to go insert in right subtree. The third call in insert function was to insert number 20. Now this time we will go to this else statement, this statement in else. Let's say we got this new node at address 300. So this guy will return 300. For this node at 200, right child will be set as 300. And now this call to insert can finish. The return will be 200. Okay, at this stage, what if a call is made to insert number 25? We are at root right now, the node with address 200. 25 is greater, so we need to go and insert in right subtree. Right subtree is not empty this time. So once again, for this call also, we will come to this else, last else, because 25 is greater than 20. Now in this call, we will go to the first if. A node will be created. Let's say we got this node in heap at address 500. This particular call, insert 025, will return 500 and finish. Now for the node at 300, right child will be set as 500, so this link will get built. Now this guy will return 300. The root for this subtree has not changed, and this first call to insert will also wrap up. It will return to 200. So we are looking good for all cases. This insert function will work for all cases. We could write this insert function without using recursion. I encourage you to do so. You will have to use some temporary pointer to node and loops. Recursion is very intuitive here, and recursion is intuitive in pretty much everything that we do with trees. So it's really important that we understand recursion really well. Okay, I'll write one more function now to search some data in BST. In the main function here, I have made some more calls to insert. Now I want to write a function named search that should take as argument address of the root node and the data to be searched, and this function should return me true if data is there in the tree, false otherwise. Once again, we will have a couple of cases. If the root is null, then we can return false. If the data in root is equal to the data that we are looking for, then we can return true. Else we can have two cases. Either we need to go and search in the left subtree, or we need to go in the right subtree. So once again, I'm using recursion here. I am making recursive call to search function in these two cases. If you have understood the previous recursion, then this is very similar. Let's test this code now. What I've done here is I've asked the user to enter a number to be searched, and then I'm making call to this search function, and if this function is returning me true, I'm printing found, else I'm printing not found. Let's run this code and see what happens. I have moved multiple insert statements in one line because I'm short of space here. Let's say we want to search for number 8. 8 is found, and now let's say we want to search for 22. 22 is not found. So we are looking good. I'll stop here now. You can check the description of this video for link to all the source code. We will do a lot more with trees in coming lessons. In our next lesson, we will go a little deeper and try to see how things move in various sections of application's memory, how things move in stack and heap sections of memory when we execute these functions. It will give you a lot of clarity. This is it for this lesson. Thanks for watching. In our previous lesson, we wrote some code for binary search tree. We wrote functions to insert and search data in BST. Now in this lesson, we will go a little deeper and try to understand how things move in various sections of application's memory when these functions get executed. And this will give you a lot of clarity. This will give you some general insight into how memory is managed for execution of a program, and how recursion, which is so frequently used in case of trees, works. The concepts that I'm going to talk about in this lesson have been discussed earlier in some of our previous lessons, but it will be good to go through these concepts again when we are implementing trees. So here is the code that we had written. We have this function getNewNode to create a new node in dynamic memory, and then we have this function insert to insert a new node in the tree, and then we have this function to search some data in the tree, and finally this is the main function. You can check the description of this video for link to this source code. Now in main function here, we have this pointer to BST node named root. to store the address of root node of my tree, and I'm initially setting it as null to create an empty tree, and then I'm making some calls to insert function to insert some data in the tree, and finally I'm asking user to input a number, and I'm making call to search function to find this number in the tree. If the search function is returning me true, I'm printing found, else I'm printing not found. Let's see what will happen in memory when this program will execute. The memory that is allocated to a program or application for its execution in a typical architecture can be divided into these 4 segments. There is one segment called text segment to store all the instructions in the program. The instructions would be compiled instructions in machine language. There is another segment to store all the global variables. A variable that is declared outside all the functions is called global variable. It is accessible to all the functions. The next segment, stack, is basically scratch space for function call execution. All the local variables, the variables that are declared within functions, live in stack. And finally, the 4th section, heap, which we also call the free store, is the dynamic memory that can grow or shrink as per our need. The size of all of the segments is fixed. The size of all of the segments is decided at compile time, but heap can grow during runtime, and we cannot control allocation or deallocation of memory in any other segment during runtime, but we can control allocation and deallocation in heap. We have discussed all of this in detail in our lesson on dynamic memory allocation. You can check the description for a link. Now what I'm going to do here is I'm going to draw stack and heap sections as these 2 rectangular containers. I'm kind of zooming into these 2 sections. Now I'll show you how things will move in these 2 sections of application's memory when this program will execute. When this program will start execution, first the main function will be called. Now whenever a function is called, some amount of memory from the stack is allocated for its execution. The allocated memory is called stack frame of the function call. All the local variables and the state of execution of the function call would be stored in the stack frame of the function call. In the main function we have this local variable root, which is pointer to BST node. So I'm showing root here in this stack frame. We will execute the instructions sequentially. In the first line in main function we have declared root, and we are initializing it and setting it as null. Null is only a macro for address 0. So here in this figure I'm setting address in root as 0. Now in the next line we are making a call to insert function. So what will happen is execution of main will pause at this stage, and a new stack frame will be allocated for execution of insert. Main will wait for this insert above to finish and return. Once this insert call finishes, main will resume at line 2. We have these 2 local variables root and data in insert function, in which we are collecting the arguments. Now for this call to insert function we will go inside the first if condition here, because root is null. At this line we will make call to get new node function. So once again execution of this insert call will pause, and a new stack frame will be allocated for execution of get new node function. We have 2 local variables in get new node, data, in which we are collecting the argument, and this pointer to BST node named new node. Now in this function we are using new operator to create a BST node in heap. Let's say we got a new node at address 200. New operator will return us this address 200, so this address will be set here in new node. So we have this link here, and now using this pointer new node we are setting value in these 3 fields of node. Let's say the first field is to store data, so we are setting value 15 here, and let's say this second cell is to store address of left child. This is being set as null, and the address of right child is also being set as null. And now get new node will return the address of new node and finish its execution. Whenever a function call finishes, the stack frame allocated to it is reclaimed. Call to insert function will resume at this line, and the return of get new node address 200 will be set in this root, which is local variable for insert call, And now insert function, this particular call to insert function will return the address of root, the address stored in this variable root, which is 200 now, and finish. And now main will resume at this line, and root of main will be set as 200. The return of this insert call, insert root 15, will be set here. Now in the execution of main, control will go to the next line, and we have this call to insert function to insert number 10. Once again, execution of main will be paused and a stack frame will be allocated for execution of insert. Now this time for insert call, root is not null, so we will not go inside the first if. We will access the data field of this node at address 200 using this pointer named root in insert function, and we will compare it with this value 10. 10 is lesser than 15, so we will go to this line, and now we are making a recursive call here. Recursion is a function calling itself, and a function calling itself is not any different from a function A calling another function B. So what will happen here is that execution of this particular insert call will be paused, and a new stack frame will be allocated for execution of this another insert call, to which the arguments passed are address 0 in this local variable root, left child of node at address 200 is null, so we are passing 0 in root, and in data we are passing 10. Now for this particular insert call, control will go inside first if, and we will make a call to get new node function at this line. So execution of this insert will pause, and we will go to get new node function. Here we are creating a new node in heap. Let's say we got this new node at address 150. Now get new node will return 150 and finish. Execution of this call to insert will resume at this line. Return of get new node will be set here. And now this call to insert will return address 150 and finish. Insert below will resume at this line. And now in this insert call, left child of this node at address 200 will be set as return of the previous insert call, which is 150. So now these two nodes are linked. And finally this insert call will finish. Control will return back to main at this line. Root will be rewritten as 200, but earlier also it was 200, it's not changing. Next in the main function we have call to insert number 20. I'm not going to show the simulation for this one. Once again the allocated memory in stack will grow and shrink, and finally when the control will return back to main function after this insert call is over, we will have a node in heap with value 20 set as right child of this node at 200. Let's say we got this new node with value 20 at address 300. So as you can see, the address of right child in node at address 200 is set as 300. Now next one is to insert number 25. This one is interesting. Let's see what will happen for this one. Main will be paused and we will go to this call to insert. In the root, which is local to this call, address passed is 200, and we have passed number 25 in data. Now here 25 is greater than the value in this node at address 200. So we will go inside this last else condition. We need to insert in the right subtree. So another call to insert will be made. We will pass address 300 as root, and data passed will be 25 only. Now for this call, once again the value in node at 300, for this call root is 300, is lesser than 25. 25 is greater than 20. So once again we will come to this last else and make a recursive call to insert in the right subtree. The right subtree is empty this time. So for this insert call at top, the address in root here will be 0. So for this call, we will go to the first if and make a call to get new node. Let's say this new node returns us node at address 100. I'm short of space, so I'm not showing everything in get new node stack frame here. We will return back to this insert call at top, and now this root is set as 100, address of the newly created node. And now this call to insert will finish. We will come back to this insert below, and this insert will resume at this line inside the last else, and the right child of node at address 300 will be set as 100. and now this insert will return back address 300, whatever is set in its root, and this insert below will resume at this line inside the last else. Right child of node at address 200 will be set as 300. It was 300 previously also, so even after overwriting we will not change, and this insert will finish now. Finally, main will resume at this line. Root of main will be set as return of this insert call. It will only be overwritten with same value. It's really important that this root in main and all the links in nodes are properly updated. Quite often, because of bugs in our code, we'll lose some links or some unwanted links are created. Now, as you can see, we are creating all the nodes in heap here. Heap gives us this flexibility that we can decide the creation of node during runtime, and we can control the lifetime of anything in heap. Any memory claimed in heap has to be explicitly deallocated using free in C or delete operator in C++, else the memory in heap remains allocated till the program is running. The memory in stack, as you can see, gets deallocated when function call finishes. The rest of the function calls here in main function will execute in similar manner. I'll leave it for you to see and think about. Right now we have this tree in the heap. Logically, memory itself is a linear structure, and this is how tree, which is a non-linear structure, which is logically a non-linear structure, will fit in it, the way I'm showing the nodes at random locations linked to each other in this heap. I hope this explanation gave you some clarity. In coming lessons we will solve some problems on tree. This is it for this lesson. Thanks for watching. In our previous lessons we wrote some basic code for binary search tree, but to solidify our concepts we need to write some more code, so I've picked this simple problem for you. Given a binary search tree, we want to find minimum and maximum element in it. Let's see how we can solve this problem. I have drawn logical representation of a binary search tree of integers here. As we know, in a binary search tree, for all nodes, value of nodes in left subtree is lesser and value of nodes in right subtree is greater. This is how we can define node for a binary search tree in C, C++. We can have a structure with three fields, one to store data, another to store address of left child, and another to store address of right child. As we had seen earlier, in BST implementation, identity of the tree that we always keep with us, that we pass to functions, is address of the root node. So what I want to do here is I first want to write a function named findMin that should take address of the root node as argument and return me the minimum element in the tree. And just like findMin, we can write another function named findMax that can return us the maximum element in BST. Let's first see how we can find the minimum element. There are two possible approaches here. We can write an iterative solution in which we can use a simple loop to find the minimum element, or we can use recursion. Let's first see the iterative solution. If we have a pointer to the root node and we want to find the minimum element in BST, then from root we need to go left as long as it's possible to go using the left links. Because in a BST, for all nodes in left have lesser value and nodes in right have greater value, so we need to go left as long as it's possible. We can start with a temporary pointer to root node. We can name this pointer temp, or we can name this pointer current to say that we are currently pointing to this node. In my function here I have declared this pointer to BST node named current, and initially I'm setting the address of root in it. And with this pointer we can go to the left child with a statement like current equal current arrow left. We first need to check if there is a left child, and then we need to move the pointer. We can use a while loop like this. If the left child of current node is not null, we can move this pointer current to the left child with this statement current equal current arrow left. Here in this example, currently we are pointing to this node with value 15. It has a left child, so we can move to this node with value 10. Once again, this node too has a left child, so we can go left again. Now this node with value 8 does not have a left child, so we cannot go towards left any further. We will come out of the while loop, and at this point the node that we are pointing to has minimum value, so we can return the data in that node. There is one case that we are missing in this function. If the tree is empty, We can throw some error. We can return some value indicative of empty tree. If I know that the tree would have only positive values, I can return something like -1. So here in my function I've added this condition: if root is equal to null, that is if the tree is empty, print this error and return -1. One more thing, we do not need to use this extra pointer to BST node named current. Root here is a local variable and we can use this root itself. So we can write our code like this: while left of root is not equal to null, we can go left with this statement, root equal root arrow left, and finally we can return root arrow data, which is only an alternate syntax for asterisk root dot data. Modifying this local root is not going to modify my root in main function or whatever function I'm calling this find min function from. So this is our iterative solution to find minimum element in BST. The logic for finding maximum is similar. The only difference will be that instead of going left, we will have to go right all the time. I leave it for you to implement. Let's now see how we can find minimum element using recursion. If we want to reduce this problem in a recursive manner, in a self-similar manner, then what we can say is, if the left subtree is not empty, then we can reduce the problem to finding minimum in left subtree. If left subtree is empty, we already know the minimum, because we cannot have a minimum in right subtree. Here is the recursion that we can write. Root being null is a corner case. If root is null, that is if the tree is empty, we can throw error. Else, if left child of root is null, we can return the data in root. Else, if left child is not null, or in other words, if the left subtree is not empty, we can reduce the problem to searching minimum in the left subtree. So we are making this recursive call to find min, passing it address of the left child, passing it address of the root of left subtree. Left child would be the root of left subtree. This second else if is our base condition to exit from recursion. If you had understood the recursion that we had written earlier to insert a node in BST, then this recursion should not be very difficult for you to understand. So here is our recursive solution to find minimum in a BST. To find maximum element, all we need to do is we need to go searching in right subtree. Okay, I'll stop here now. In coming lessons, we will solve some more interesting problems on BST. Thanks for watching. In this lesson, we are going to write code to find height, or what we can also call maximum depth of a binary tree. We have already discussed depth and height in our first introductory lesson on trees, but I'll do a quick recap here. First of all, I've drawn a binary tree here. I have not filled in any data in the nodes. Data can be anything. Binary tree, as we know, is a tree in which each node can have at most 2 children. So a node can have 0, 1 or 2 children. I'll just number these nodes so I can refer to them. I'll say this root node is number 1, and I'll go level by level from left to right, counting 2, 3, 4 and so on. Now height of a tree is defined as number of edges in longest path from root to a leaf node. In this example tree, 4, 6, 7, 8 and 9 are leaf nodes. A leaf node is a node with 0 children. Number of edges in longest path from root to a leaf node is 3. For both 8 and 9, number of edges in path from root is 3. So height of the tree is 3. Actually, we can define height of a node in the tree as number of edges in longest path from that node to a leaf node. So height of a tree basically is height of the root node. In this example tree, height of node 3 is 1, height of node 2 is 2, and height of node 1 is 3. And because this is the root node, this is also the height of the tree. Height of a leaf node would be 0. So if a tree has only one node, then the root node itself would be a leaf node, and so height of the tree would be 0. So this is definition of height of a tree. We often also talk about depth, and we often confuse between depth and height, but these two are different properties. Depth of a node is defined as number of edges in path from root to that node. Basically, depth is distance from root, and height is distance from deepest accessible leaf node. For node 2 in this example tree, depth is 1 and height is 2. For node number 9, which is a leaf node, depth is 3 and height is 0. For root node, depth is 0 and height is 3. Height of a tree would be equal to maximum depth of any node in the tree. So height and max depth, these two terms are used for each other. Okay, let's now see how we can calculate height or max depth of a binary tree. I'm going to write a function named find height that will take reference or address of the root node as argument and return me the height of the binary tree. Now the logic to calculate height can be something like this. For any node, if we can somehow calculate the height of its left subtree and also the height of its right subtree, then the height of that node would be greater of the heights of left and right subtrees plus 1. For the root node in this tree, height of the left subtree is 2 and height of the right subtree is 1. So height of the root node would be greater of these two values plus 1. Plus 1 for the edge connecting the root node to the subtree. So height of the root node, which would also be the height of the tree, is 3 here. In our code, we can calculate height of left and right subtrees using recursion. What I'll do here in find height function is I'll first make a recursive call to find height of the left subtree. We can say to find height of left subtree or to find height of left child. Both will mean the same. I'm collecting the return of this recursive call in a variable named left height, and now I'll make another recursive call to calculate height of right subtree or right child. Now height of the tree or height of whatever node for which we have made this function call would be greater of these two values, left height and right height, plus 1. Now there is only one more thing missing in this recursion. We need to write the base or exit condition. We cannot go into recursion infinitely. What we can do is we can go on till we make a recursive call with root equal null. And if root is null, that is if the tree or subtree is empty, we can return something. What should we return here? Give this some thought. If I have made a call to find height of, let's say, this leaf node, this node with number 7, then for this guy both left and right children are null. In call for this node number 7, we will make two recursive calls passing null in both the calls. So what should we return? Should we return 0? If these two calls will return 0, then height of 7 will be 1, because in the return statement here we are saying max of left and right height plus 1. But as we had discussed earlier, height of a leaf node should be 0. So if we are returning 0 for root equal null, it's not alright. What we can do is we can return minus 1. When we are returning minus 1, then this edge to null that does not exist but still was getting counted will be balanced with this minus 1. I hope this is making sense. And going by convention also, height of an empty tree is set to be minus 1. So this is pseudocode for my function to find height of a binary tree. Some people define height as number of nodes in longest path from root to a leaf node. We are counting edges here, and this is the right definition. If you want to count number of nodes, then for a leaf node height would be 1, and for empty tree height would be 0. So all you need to do is return 0 here, and this is the code if you want to count number of nodes. But I think the right definition is number of edges, so I'll return minus 1 here. Time complexity of this function is big O of n, where n is number of nodes in the tree. We will make one recursive call corresponding to each node in the tree, so we are kind of visiting each node in the tree once, and so running time will be proportional to number of nodes. I'll skip detailed analysis of running time in this lesson. This is what my find height function will look like in C or C++. Max here is a function that will return greater of two values passed to it as arguments. So this is it for this lesson. Thanks for watching. In this lesson we are going to talk about binary tree traversal. When we are working with trees, we may often want to visit all the nodes in the tree. Now, tree is not a linear data structure like array or linked list. In a linear data structure, there would be a logical start and a logical end. So we can start with a pointer at one of the ends and keep moving it towards the other end. For a linear data structure like linked list, for each node or element we would have only one next element. But tree is not a linear data structure. I have drawn a binary tree here. Data type is character this time. I filled in these characters in the nodes. Now for a tree, at any time if we are pointing to a particular node, then we can have more than one possible directions. We can have more than one possible next nodes. In this binary tree, for example, if we will start with a pointer at root node, then we have two possible directions. From F we can either go left to D or we can go right to J. And of course, if we will go in one direction, then we will somehow have to come back and go into the other direction later. So tree traversal is not so straightforward, and what we are going to discuss in this lesson is algorithms for tree traversal. Tree traversal can formally be defined as the process of visiting each node in the tree exactly once in some order. And by visiting a node, we mean reading or processing data in the node. For us in this lesson, visit will mean printing the data in the node. Based on the order in which nodes are visited, tree traversal algorithms can broadly be classified into two categories. We can either go breadth first or we can go depth first. Breadth first traversal and depth first traversal are general techniques to traverse or search a graph. Graph is a data structure, and we have not talked about graph so far in this series. We will discuss graph in later lessons. For now, just know that tree is only a special kind of graph. And in this lesson, we are going to discuss breadth first and depth first traversal in context of trees. In a tree, in breadth first approach, we would visit all the nodes at same depth or level before visiting the nodes at next level. In this binary tree that I'm showing here, this node with value f, which is the root node, is at level 0. I'm writing L0 here for level 0. Depth of a node is defined as number of edges in path from root to that node. A root node would have depth 0. These two nodes D and J are at depth 1. So we can say that these nodes are at level 1. Now these 4 nodes are at level 2. These 3 nodes are at level 3. And finally this node with value h is at level 4. So what we can do in breadth first approach is that we can start at level 0. We would have only one node at level 0, the root node. So we can visit the root node. I'll write the value in the node as I'm visiting it. Now level 0 is done. Now I can go to level 1 and visit the nodes from left to right. So after F we would visit D and then we would visit J, and now we are done with level 1. So we can go to level 2. We will go like B, then E, then G, and then K. And now we can go to level 3, A, C, and I, and finally I can go to level 4. This kind of breadth first traversal in case of trees is called level order traversal. And we will discuss how we can do this programmatically in some time. But this is the order in which we would visit the nodes. We would go level by level from left to right. In breadth first approach, for any node, we visit all its children before visiting any of its grandchildren. In this tree, first we are visiting F, and then we are visiting D, and then we are not going to any child of D like B or E along the depth. Next we are going to J. But in depth first approach, if we would go to a child, we would complete the whole subtree of the child before going to the next child. In this example tree here, from F, the root node, if we are going left to D, then we should visit all the nodes in this left subtree. That is, we should finish this left subtree in its complete depth. Or in other words, we should finish all the grandchildren of F along this path before going to right child of F, J. And once again, when we will go to J, we will visit all the grandchildren along this path. So basically, we will visit the complete right subtree. In depth first approach, the relative order of visiting the left subtree, the right subtree, and the root node can be different. For example, we can first visit the right subtree and then the root and then the left subtree. Or we can do something like we can first visit the root and then the left subtree and then the right subtree. So the relative order can be different, but the core idea in depth first strategy is that visiting a child is visiting the complete subtree in that path. And remember, visiting a node is reading, processing, or printing the data in that node based on the relative order of left subtree, right subtree, and the root. There are three popular depth first strategies. One way is that we can first visit the root node, then the left subtree, and then the right subtree. Left and right subtrees will be visited recursively in same manner. Such a traversal is called pre-order traversal. Another way is that we can first visit the left subtree, then the root, and then the right subtree. Such a traversal is called in-order traversal. And if root is visited after left and right subtrees, then such a traversal is called post-order traversal. In total, there are 6 possible permutations for left, right, and root, but conventionally, a left subtree is always visited before the right subtree. So these are the 3 strategies that we use. Only the position of root is changing here. If it's before left and right, then it's pre-order. If it's in between, it's in order. And if it's after left and right subtrees, then it's post-order. There is an easy way to remember these 3 depth first algorithms. If we can denote visiting a node or reading the data in that node with letter D, going to the left subtree as L and going to the right subtree as R. So if we can say D for data, L for left, and R for right, then in pre-order for each node we will go DLR. First we will read the data in that node, then we will go left, and once the left subtree is done we will go right. In order traversal, first we will finish the left subtree, then we will read the data in current node, and then we will go right. In post order, for each node first we will go left, once left subtree is done we will go right, and then we will read the data in current node. So pre-order is data left right, in order is left data right, and post order is left right and then data. Pre-order, in-order, and post-order are really easy and intuitive to implement using recursion, but we will discuss implementation later. Let's now see what will be the pre-order, in-order, and post-order traversal for this tree that I've drawn here. Let's first see what will be the pre-order traversal for this binary tree. We need to start at root node, and for each node we first need to read the data, or in other words visit that node. In fact, instead of DLR we could have said VLR here, V for visit. We can use any of these assumptions, V for visit or D for data. I will go with DLR here. So let's start at the root. For each node we first need to read the data. I'm writing F here, the data that I just read. And now I need to go left and finish the complete left subtree. And once all the nodes in the left subtree are visited, then only I can go to the right subtree. The problem here is actually getting reduced in a self-similar or recursive manner. Now we need to focus on this left subtree. Now we are at D, root of this left subtree of F. Once again, for this node we will first read the data, and now we can go left. We will go towards E only when these 3 nodes A, B, and C will be done. Now we are focusing on this subtree comprising of these 3 nodes. Now we are at B, we can read the data, and now we can go left to A. There is nothing in left of A, so we can say that for A, left subtree is done, and there is nothing in right as well, so we can say right is also done. Now for B, left subtree is done, so we can go right to C, and left and right of C are null. And now for D, left subtree is done, so we can go right. Once again for E, left and right are null. And now at this stage for F, complete left subtree is visited, so we can go right. Now we need to go left of J, and there is nothing in left of G, so we can go right. And now we can go left of I. For H there is nothing in left and right. Now at this stage left subtree of I is done and right subtree is null. And now we can go back to J. The left subtree for J is done, so we can go to its right subtree. Finally we have K here, and we are done with all the nodes. This is how we can perform a pre-order traversal manually. Actual implementation would be a simple recursion, and we will discuss it later. Let's now see what will be the in-order traversal for this binary tree. In in-order traversal, we will first finish visiting the left subtree, then visit the current node, and then go right. Once again, we will start at the root and we will first go left. Now we will first finish this subtree. Once again for D, we will first go left to B, and from B we will go to A. Now for A, there is nothing left, so we can say that for this guy, left subtree is done. So we can read the data, and now we can go to its right, but there is nothing in right as well, so this guy is done. Now for B, left subtree is done, so we can read the data, and now for B we can go right. For C, once again, there is nothing left, so we can read the data, and there is nothing in right as well. Now left of D is completely done, so we can visit it, read the data here. Now we can go to its right to E. For E, once again, left and right are null. At this stage, left subtree of F is done, so we can read the data, and now we can go to right of F. If we will go on like this, this finally will be my in-order traversal. This tree that I'm showing here is actually a binary search tree. For each node, the value of nodes in left is lesser and the value of nodes in right is greater. So if we are printing in this order, left subtree and then the current node and then the right subtree, then we would get a sorted list. In-order traversal of a binary search tree would give you a sorted list. Okay, now you should be able to figure out the post-order traversal. This is what we will get for post-order traversal. I leave it for you to see whether this is correct or not. I'll stop here now. In next lesson, we will discuss implementation of these tree traversal algorithms. Thanks for watching. In this lesson, we are going to write code for level order traversal of a binary tree. As we had discussed in our previous lesson, in level order traversal, we visit all nodes at a particular depth or level in the tree before visiting the nodes at next deeper level. For this binary tree that I'm showing here, if I have to traverse the tree and print the data in nodes in level order, then this is how we will go. We will start at level 0 and print F, and now we are done with level 0, so we can go to level 1 and we can visit the nodes at level 1 from left to right. From F we will go to D, and from D we will go to J. Now level 1 is done, so we can go to level 2. So we will go like B, E, G and then K, and now we can go to next level A, C, I, and finally we will be done at H. This is the order in which we should visit the nodes, but the question is, how can we visit the nodes in this order in a program? Like linked list, we can't just have one pointer and keep moving it. If I'll start with a pointer at root, let's say I have a pointer named current to point to the current node that I'm visiting, then it's possible for me to go from F to D using this pointer because there is a link. So I can go left to D, but from D I cannot go to J because there is no link from D to J. The only way we can go to J is from F, and once we have moved the pointer to D, we can't even go back to F because there is no backward link from D to F. So what can we do to traverse the nodes in level order? Clearly we can't go with just one pointer. What we can do is, as we visit a node, we can keep reference or address of all its children in a queue, so we can visit them later. A node in the queue can be called discovered node, whose address is known to us but we have not visited it yet. Initially we can start with the address of root node in the queue to mean that initially this is the only discovered node. Let's say for this example tree, address of the root node is 400, and I'll assume some random addresses for other nodes as well. I will mark a discovered node in yellow. Okay, now initially I'm enqueuing the root node, and by storing a node in the queue, I'll mean storing the address of the node in the queue. So initially we are starting with one discovered node. Now as long as the queue has some discovered node, at least one discovered node, that is, as long as the queue is not empty, we can take out a node from the front, visit it, and then enqueue its children. Visiting a node for us is printing the value in that node, so I'll write F here. And now I'll enqueue the children of this root node. First I'll enqueue the left child and then the right child. I'll mark visited node in another color. Okay, now we have one visited node and two discovered node. And now once again we can take out the node at front of the queue, visit it, and enqueue its children. By using a queue, we are doing two things here. First of all, as we are moving from a node, we are not losing reference to its children because we are storing the references. And then, because queue is a first in, first out structure, so a node that is discovered first, that is inserted first, will be visited first. So we will get this ordered that we are desiring. Give this some thought and it's not very difficult to see. Okay, so now we can dequeue and visit this node at address 200. And once again, before I move on from this node, I need to enqueue its children. So now at this stage, we have 2 visited nodes, 3 discovered nodes, and 6 undiscovered nodes. And now we can take out the next node from front of queue. We'll visit it and enqueue its children. If we will go on like this, all the nodes will be visited in the order that we are desiring. At this stage, we can dequeue node at 120, visit it, and enqueue its children. So we will go on like this until all the nodes are visited and the queue is empty. After B, we will have E here. Nothing will go into the queue this time. Next, we will have G here, and the address of I will go into the queue. Now K will be visited. Now at this stage, we have reference to 3 nodes in the queue. Now we will visit this node at 320 with value A. And then we have C, and now we will print I, and the node with value H, the node with data H will go into the queue. Finally, we will visit this node, and now we are done with all the nodes. The queue is empty. Once the queue is empty, we are done with our traversal. So this is the algorithm for level order traversal of a binary tree. As you saw in this approach, at any time we are keeping a bunch of addresses in the memory in the queue instead of using just one pointer to move around. So of course we are using a lot of extra memory, and I'll talk about the space complexity of this algorithm in some time. I hope you got the core logic right. Let's now write code for this algorithm. I'm going to write C++ here. This is how I'm defining node for my binary tree. I have a structure here with 3 fields, one to store data, and the data type is character this time, because in the example tree that we were showing earlier, data type was character. And we have 2 more fields that are pointers to node, one to store the address of left child and another to store the address of right child. Now what I want to do here is I want to write a function named level order that should take address of the root node as argument and print the data in the nodes in level order. Now to test this function, I'll have to write a lot of code. To create and insert nodes in a binary tree, I'll have to write some more functions. I'll skip writing all that code. You can pick the code for creation and insertion from previous lessons. All I'll write is this function, level order. Now in this function here, I'll first take care of one corner case. If the tree is empty, that is, if root is null, we can simply return. Else, if the tree is not empty, we need to create a queue. I'm not going to write my own implementation of queue here. In C++, we can use the queue in standard template library. And to use it, first we'll have to write a statement like hash include queue here. And now I can create a queue of any type. In this function, I'll create a queue of pointer to node with a statement like this. Now, as we had discussed earlier, initially we start with one discovered node in the queue. The only node known to us initially is the root node. With this statement queue.push root, I have inserted the address of root node in the queue. And now I'll run this while loop, for which the condition is that the queue should not be empty. And what I really mean here is that while there is at least one discovered node, we should go inside the loop, and inside the loop we should take out a node from the front. This function front returns the element at front of the queue, and because the data type is pointer to node, I am collecting the return of this function in this pointer to node named current. Now I can visit this node being pointed by current, and by visiting, if we mean reading the data in that node, I'll simply print the data. And now we want to push the addresses of children of this node into the queue. So I'll say that if the left child is not null, insert it into the queue, and similarly if right child is not null, push it into the queue, or rather push its address into the queue. And I'll write one more statement to remove the element from front of the queue. With call to front, the element is not removed from the queue. With this call pop, we are removing the element. Okay, so this is implementation of level order traversal in C++. You can check the description of this video for a link to source code, and there you can also find all the extra code to test this function. Let's now talk about time and space complexity of level order traversal. If there are n nodes in the tree, and in this algorithm visit to a node is reading the data in that node and inserting its children in the queue, then a visit to a node will take constant time, and each node will be visited exactly once, so time taken will be proportional to the number of nodes. Or in other words, we can say that the time complexity is big O of n. For all cases, irrespective of the shape of the tree, time complexity of level order traversal will be big O of n. Now let's talk about space complexity. Space complexity, as we know, is the measure of rate of growth of extra memory used with input size. We are not using constant amount of extra memory in this algorithm. We have this queue that will grow and shrink while executing this algorithm. Assuming that the queue is dynamic, maximum amount of extra memory used will depend upon maximum number of elements in the queue at any time. We can have couple of cases. In some cases, extra memory used will be lesser, and in some cases extra memory used will be greater. For a tree like this, where each node has only one child, we will have maximum one element in the queue at any time. During each visit, one node will be taken out from the queue and one node will be inserted. So the amount of extra memory taken will not depend upon the number of nodes. Space complexity will be big O of 1. But for a tree like this, the amount of extra memory used will depend upon the number of nodes in the tree. This is a perfect binary tree. All the levels are full. If you can see, as the algorithm will execute, at some point for each level, all the nodes in that level will be in the queue. In a perfect binary tree, we will have n by 2 nodes at the deepest level. So maximum number of nodes in the queue is going to be at least n by 2. So basically extra memory used is proportional to n, the number of nodes. So space complexity will be big O of n for this case. I'm not going to prove it, but for average case, space complexity will be big O of n. So for both worst and average cases, we will be big O of n in terms of space complexity. And when we are saying best, average and worst cases here, it's only going by space complexity. Time complexity will be big O of n for all cases. So this is time and space complexity analysis of level order traversal. I'll stop here now. In next lesson, we will discuss depth first traversal algorithms, pre-order, in-order, and post-order. This is it for this lesson. Thanks for watching. In our previous lesson, we talked about level order traversal of binary tree, which is basically breadth first traversal. Now in this lesson, we are going to discuss these three depth first algorithms: pre-order, in-order, and post-order. I have drawn a binary tree here. Data type filled in the nodes is character. Now, as we had discussed in earlier lessons, in depth first traversal of binary tree, if we go in one direction, then we visit all the nodes in that direction. Or in other words, we visit the complete subtree in that direction, and then only we go in other direction. In this example tree that I have drawn here, if I'm at root and I'm going left, then I'll visit all the nodes in this left subtree, and then only I can go right. And once again, when I'll go right, I'll visit all the nodes in this right subtree. If you can see, in this approach, we are reducing the problem in a self-similar or recursive manner. We can say that in total, visiting all the nodes in the tree is visiting the root node, visiting the left subtree, and visiting the right subtree. Remember, by visiting a node, we mean reading or processing the data in that node, and by visiting a subtree, we mean visiting all the nodes in the subtree. In depth first strategy, relative order of visiting the left subtree, right subtree, and the root can be different. For example, we can first visit the right subtree, then the root, and then the left subtree. Or we can first visit the root and then the left subtree and then the right subtree. Conventionally, left subtree is always visited before right subtree. With this constraint, we will have three permutations. We can first visit the root and then the left subtree and then the right subtree, and such a traversal will be called pre-order traversal. Or we can first visit the left subtree, then the root and then the right subtree, and such a traversal will be called in-order traversal. And we can also go left, right and then root, and such a traversal will be called post-order traversal. Left and right subtrees will be visited recursively in same manner as the original tree. So in pre-order, once again for the subtrees we will go root, left and then right. In order we'll keep going left, root and then right. The actual implementation of these algorithms is really easy and intuitive. Let's first see code for pre-order traversal. I've first written the algorithm in words here. In pre-order traversal we first need to visit the root, then the left subtree and then the right subtree. Now I want to write a function that should take pointer or reference to root node as argument and print data in all the nodes in pre-order. Let's say visiting a node for us is printing the data in that node. In C or C++, my method signature will look something like this. This function will take address of the root node as argument. Argument type is pointer to node. I'll define node as a structure with 3 fields like this. Data type in this definition is character, and there are 2 fields to store the addresses of left and right children. Now in pre-order function, I'll first visit or print the data in root node, and now I'll make a recursive call to visit the left subtree. I have made a recursive call here, and to this call I'm passing address of the left child of my current root, because left child will be the root of left subtree. And I'll have another call like this to visit the right subtree. There is one more thing that we need to add in this function and we will be done. We cannot go into recursion infinitely. We need to have a base condition where we should exit if a tree or subtree is empty, or in other words, for any call if root is null, we can return or exit. Now with this much of code I'm done with my pre-order function. This will work fine in C or C++. Actually in C make sure you write struct space node instead of writing just node. The rest of the things are fine. It will be good to visualize this recursion. So let's now quickly see how this pre-order function will work if this example tree that I'm showing in right here is passed to it. I'll redraw this tree and show it like this. Here I'm depicting node as a structure with 3 fields. Let's say the leftmost cell here is to store the address of left child, the cell in middle is to store the data, and the rightmost cell is to store the address of right child. Now let's assume some addresses for these nodes. Let's say the root node is at address 200, and I'll assume some random addresses for other nodes as well. And now I can fill in left and right fields for each node. And as we know, the identity of tree that we always keep with us is reference or address of the root node. This is what we pass to all the functions. In our implementation, we often use a variable of type pointer to node named root to store the address of root node. We can name this variable anything. We can name this variable root, or we can name this variable root ptr, but this is just a pointer. This particular block that I'm showing here is for pointer to node, and all these rectangles with 3 cells are nodes. This is how things are organized in memory. Now for this tree, let's say we are making a call to this pre-order function. I'll make a call to pre-order passing it address 200. For this call, root is not null, so we will not return at first line in this function. We will go ahead and print the data in this node at address 200. I'll write output for all print statements here. And now this function will make a recursive call. Execution of this particular function call will pause. It will resume only after this recursive call pre-order 150 finishes. This second call is to visit this left subtree. This call pre-order 150 is to visit this left subtree. Address of the left child of node at 200 is 150. Once again, for this call, root is not null, so we will go ahead and print the data. Data in node at 150 is D, and now once again there will be a recursive call. With this call, pre-order 400, we are saying that we are going to visit this subtree. Once again we will print the data and make another recursive call. Now we have made a call to visit this particular subtree with just one node. For this call we will print the data, and now for node at 250 address of left child is 0 or null. We will make a call preorder 0, but for this call we will simply return because the address in this variable root will be null. We have hit the base condition for our recursion. Call to preorder 0 will finish and preorder 250 will resume. Now in this particular function call we'll make another call for right subtree. For node at 250 even the right child is null. We will have another recursive call passing address 0, but this once again will simply return. And now call to preorder 250 will finish and call to preorder 400 will resume. Now in call to preorder 400 we will make another recursive call to preorder 180. With this call preorder 180 we are visiting this particular subtree with just one node. For this call first we will print the data and then we will make a recursive call to preorder 0. Now preorder 0 will simply return, and then we will have another call to preorder 0 for right child of 180. The recursion will go on like this. There is one thing that I want to talk about here that's happening in this whole process. Even though we are not using any extra memory explicitly in our function, because of the recursion we are growing the function call stack. We have discussed memory management a number of times in our earlier lessons. You can check description of this video for a link to one of those lessons. As we know, for each function call we allocate some amount of memory in what we call stack section of application's memory, and this allocated memory is reclaimed when the function call finishes. At this stage of execution of my recursion for this example, my call stack will look something like this. I'm writing P as shortcut for preorder because I'm short of space here. Let's say we made a call to preorder passing it address 200 from main function. Main function will be at bottom of stack. At any time only the call at top of stack will be executing and all other calls will be paused. Call stack keeps growing and shrinking during execution of a program because memory is allocated for a new function call and it's reclaimed when a function call finishes. So even though we are not using any extra memory explicitly here, we are using memory implicitly in the call stack. So space complexity, which is measure of rate of growth of extra memory used with input, will depend upon the maximum amount of extra memory used in the call stack. I'll talk about space complexity once more later. For now let's come back to this recursion that I was executing. Call to this preorder 0 will finish and preorder 180 will resume. Memory allocated for execution of preorder 0 will be reclaimed. Now for preorder 180 both recursive calls have finished, so this guy will also finish. Even for preorder 400 both calls have finished, so preorder 150 will resume. Now this guy will make a recursive call to preorder function passing it address 450, address of its right child. Memory in the stack will be allocated for execution of preorder 450. Now in this call we will first print the data and then we will make two recursive calls to preorder passing address 0 each time because for this node at 450 both children are null. Both calls will simply return and then preorder 450 will finish. And now preorder 150 will also be done. If you can see, the call stack will grow only till we reach a leaf node, a node with no children, and then it will start shrinking again. Maximum growth of call stack due to this recursion will depend upon maximum depth or height of the tree. We can say that extra space used will be proportional to height of the tree, or in other words, space complexity of this algorithm is big O of h, where h is height of the tree. Okay, coming back to the recursion, we are done with preorder 150, so preorder 200 will resume, and now we will make a call to visit this particular subtree. In this call we will print j and then we will make a call passing address 60. So now we are visiting this particular subtree. Here we will first print g and then this guy will make a call to preorder 0, which will simply return, and then there will be another call to preorder 500. Here we will print I, and then we will make two recursive calls passing address 0 every time because node at 500 is a leaf node with no children. After this guy finishes, preorder 60 will resume. Now this guy will also finish and preorder 350 will resume, and now we will have a call to preorder 700, which once again is a leaf node. So k, which is data in this node, will be printed, and then we will make two calls passing address 0, which will simply return. Now at this stage all these calls can finish. We are done visiting all the nodes. Finally we will return back to the caller of pre-order 200, which probably would be the main function. So this is pre-order traversal for you. I hope you got how this recursion works. Code for in-order and post-order will be very similar. In in-order traversal, my base case will be the same. So I'll say if root is null, then return or exit. If root is not null, I first need to visit the left subtree. I'm visiting the left subtree with this recursive call. Then I need to visit the root. So now I'm writing this printf statement to print the data. And now I can visit the right subtree. So this second recursive call. And this is my in-order function. In-order traversal of this example tree that I have drawn here will be this. This particular binary tree is actually also a binary search tree, and in-order traversal of a binary search tree would give us elements in the tree in sorted order. Okay, let's now write code for post order. For this function, once again the base case will be the same. So I'll say if root is null, return or exit. If root is not null, I first need to visit the left subtree. So I have made this recursive call. Then the right subtree. So I'll have this another recursive call. And now I can visit the root node. Post order traversal for this example tree will be this. So this is pre-order, in-order and post-order for you. You can check the description of this video for a link to all the source code. Let's now quickly talk about time and space complexity of these algorithms. Time complexity of all these three algorithms is big O of n. If you could see, then there was one function call corresponding to each node where we were actually visiting that node, where we were actually printing the data in that node. So running time should actually be proportional to number of nodes. There is a better formal and mathematical way of proving that time complexity of these algorithms is big O of n. You can check the description of this video for a link to that. Space complexity, as we had discussed earlier, will be big O of h, where h is height of the tree. Height of a tree in worst case will be n minus 1. So in worst case, space complexity of these algorithms can be big O of n. In best or average case, height of a tree will be big O of log n to the base 2. So we can say that in best or average case, space complexity will be big O of log n. I'll stop here now. In coming lessons, we will solve some problems on binary tree. Thanks for watching. In this lesson, we are going to solve a simple problem on binary tree, which is also a famous programming interview question. And the problem is, given a binary tree, we need to check if the binary tree is a binary search tree or not. As we know, a binary tree is a tree in which each node can have at most 2 children. All these trees that I have drawn here are binary trees, but not all of them are binary search trees. Binary search tree, as we know, is a binary tree in which for each node, value of all the nodes in left subtree is lesser, and if we want to allow duplicates, we can say lesser or equal, and value of all the nodes in right subtree is greater. We can define binary search tree as a recursive structure like this. Elements in left subtree must be lesser or equal, and elements in right subtree must be greater. And this should be true for all nodes and not just the root node. So left and right subtrees should themselves also be binary search trees. Of these binary trees that I'm showing here, A and C are binary search trees, but B and D are not. In B, for the root node with value 10, we have 11 in its left subtree, which is greater than 10. And in a binary tree, for any node, all values in its left subtree must be lesser. In D, we are good for the root node. The value in root node is 5, and we have 1 in left subtree, which is lesser, and we have 8, 9, and 12 in right subtree, which are greater. So we are good for the root node, but for this node with value 8, we have 9 in its left. So this tree is not a binary search tree. So how should we go about solving this problem? Basically, I want to write a function that should take pointer or reference to root node of a binary tree as argument, and the function should return true if the binary tree is BST, false otherwise. This is how my method signature will look like in C++. In C, we do not have Boolean type, so return type here can be int. We can return 1 for true and 0 for false. I'll also write the definition of node here. For a binary tree, node would be a structure with 3 fields, 1 to store data and 2 to store addresses of left and right children. In my definition of node here, data type is integer, and we have 2 pointers to node to store addresses of left and right children. Okay, coming back to the problem. There are multiple approaches, and we are going to talk about all of them. The first approach that I'm going to talk about is easy to think of, but it's not so efficient. But let's discuss it anyway. We are saying that for a binary tree to be called binary search tree, it should have a recursive structure like this. For the root node, all the elements in left subtree must be lesser or equal, and all the elements in right subtree must be greater, and left and right subtrees should themselves also be binary search trees. So let's just check for all of this. I'm going to write a function named isSubtreeLesser that will take address of root node of a binary tree or subtree and an integer value as argument, and this function will return true if all the elements in the subtree are lesser than this value. And similarly, I'll write another function named isSubtreeGreater that will return true if all the elements in a subtree are greater than a given value. I have just declared these functions. I'll write body of these functions later. Let's come back to this function isBinarySearchTree. In this function, I'm going to say that if all elements in left subtree are lesser, and I'll verify this by making a call to isSubtreeLesser function, passing it address of left child of my current root. Left child would be the root of left subtree, and the data in root. This function call will return true if all the elements in left subtree would be lesser than the data in root. Now the next thing that I want to check for is if elements in right subtree are greater than the data in root or not. These two conditions are not sufficient. We also need to check if left and right subtrees are binary search trees or not. So I'll add 2 more conditions here. I have made a recursive call to isBinarySearchTree function passing it address of left child, and I have made another call passing address of right child. And if all these 4 function calls, isSubtreeLesser, isSubtreeGreater, and isBinarySearchTree for left and right subtrees return true, if all these 4 checks pass, then our tree is a binary search tree. We can return true, else we need to return false. There is only one thing that we are missing in this function now. We are missing the base case. If root is null, that is, if the tree or subtree is empty, we can return true. This is the base case for our recursion where we should stop. With this much of code, isBinarySearchTree function is complete. But let's also write its SubtreeLesser and its SubtreeGreater functions because they're also part of our logic. This function has to be a generic function that should check if all the elements in a given tree are lesser than a given value or not. We will have to traverse the complete tree or subtree and see value in all the nodes and compare these values against this given integer. I'll first handle the base case in this function. If the tree is empty, we can return true. Else we need to check if the data in root is less than or equal to the given value. And we also need to recursively check if left and right subtrees of the current root have lesser value or not. So I'm adding 2 more conditions here. I'm making 2 recursive calls, one for the left subtree and another for the right subtree. If all these 3 conditions are true, then we are good, else we can return false. isSubtreeGreater function will be very similar. Instead of writing these 2 functions, isSubtreeLesser and SubtreeGreater, we could also do something like this. We could find the maximum in left subtree and compare it with the data in root. If maximum of a subtree is lesser, then all the elements are lesser, and similarly, if the minimum of a subtree is greater, all the elements are greater. For the right subtree, we could find the minimum. So instead of writing these 2 functions, isSubtreeLesser and isSubtreeGreater, we could write something like find max and find min, and this would also fit. So this is our solution using one of the approaches. Let's quickly run this code on an example binary tree and see how it will execute. I have drawn a very simple binary tree here, which actually is a binary search tree. Let's assume some addresses for these nodes in the tree. Let's say the root node is at address 200 and I'll assume some random addresses for other nodes as well. To check if this binary tree is a binary search tree or not, we will make a call to isBinarySearchTree function. I'm writing IBST here as shortcut for isBinarySearchTree because I'm short of space here. So I'll make a call to this function, maybe from the main function, passing address 200, address of the root node. For this function call, address in this local variable, address collected in this local variable root, will be 200. Root is not null. Null is only a macro for address 0. For this call, root is not null, so we will not return true at this line. We will go to the next if. Now here we will make a call to isSubtree_lesser function. Arguments passed will be address of left child, which is 150, and 7, the data in node at 200. Execution of the calling function will pause and will resume only after the called function returns. Now in this call to isSubtree_lesser, root is not null, so we will not return true at first line. We will go to the next if. Now here the first condition is if data in root, and the root this time is 150, because this call is for this left subtree, and for this left subtree address of root is 150. Data in root is 4, which is lesser than 7. So the first condition is true, and we can go to the second condition, which is a recursive call. This call will pause and we will go to the next call. Here once again the data in node at 180, 1 is lesser than 7. So first condition is true and we will make a recursive call. Left subtree for node at 180 is null. There is no left child, so we will return at first line. Root is null this time. This particular call will simply return true. Now in this previous call, when root is 180, second condition for if is also true. So we will make another call for right subtree. Once again address passed will be 0 and we will simply return true. And now for this call is isSubtree_lesser 187. All three conditions are true. So this guy can also return true. And now this call ISL 157 will resume. Now this guy will make a recursive call for the right subtree, and this guy after everything will also return true. Now for this call, because all three conditions in the if statement are true, this guy will also return true. And now isBinarySearchTree function will resume. For this call we have evaluated the first condition. We have got true. Now this guy will make another call to isSubtree_creator, passing address of right child and value 7. This guy after everything will return true. And now we will have two recursive calls to check if left and right subtrees are binary search trees or not. We will first have a call for the left subtree. The execution will go on like this, but I want you to see something. In each call to binary search tree function, we are comparing the data in root with all the elements in left subtree and then all the elements in right subtree. This example tree could be really large. Then in that case, in the first call to isBinarySearchTree, for this complete tree, we would recursively traverse this whole left subtree to see whether all the values in this subtree are less than 7 or not. And then we will traverse all nodes in this right subtree to see if values are greater than 7 or not. And then in next call to isBinarySearchTree, when we would be validating whether this particular subtree is BST or not, we would recursively traverse this subtree if values are lesser than 4 or not, and this subtree to see if values are greater than 4 or not. So all in all, during this whole process there will be a lot of traversal. Data in nodes will be read and compared multiple times. If you can see, all nodes in this particular subtree will be traversed once in call to isBinarySearchTree for 200, when we will compare value in these nodes with 7, and then these nodes will once again be traversed in call to isBinarySearchTree for 150, when they will be compared with 4. They will be traversed in call to isSubtree_lesser. All in all, these two functions, isSubtree_lesser and isSubtree_creator, are very expensive. For each node we are looking at all nodes in its subtrees. There is an efficient solution in which we do not need to compare data in a node with data in all nodes in its subtrees. And let's see what the solution is. What we can do is we can define a permissible range for each node, and data in that node must be in that range. We can start at the root node with range -infinity to infinity, because for the root node there is no upper and lower limit. And now as we are traversing, we can set a range for other nodes. When we are going left, we need to reset the upper bound. So for this node at 150, data has to be between -infinity and 7. Data in left child cannot be greater than data in root. If we are going right, we need to set the lower bound. For this node at 300, range would be 7 to infinity. 7 is not included in the range. Data has to be strictly greater than 7. For this node at 180, the range will be -infinity to 4. For this node with value 6, lower bound will be 4 and upper bound would be 7. Now my code will go like this. My function is binary search tree will take two more arguments. An integer to mark the lower bound or min value, and another integer to mark the upper bound or max value. And now instead of checking whether all the elements in left subtree are lesser than the data in root and all the elements in right subtree are greater than the data in root or not, we will simply check whether data in root is in this range or not. So I'll get rid of these two function calls, its subtree lesser and its subtree greater, which are really expensive, and I'll add these two conditions. Data in root must be greater than min value and data in root must be less than max value. These two checks will take constant time. Its subtree lesser and its subtree greater functions were not taking constant time. Running time for them was proportional to number of nodes in the subtree. Okay, now these two recursive calls should also have two more arguments. For the left child, lower bound will not change. Upper bound will be the data in current node. And for the right child, upper bound will not change and lower bound will be the data in current node. This recursion looks good to me. We already have the base case written. The only thing is that the caller of his binary search tree function may only want to pass the address of root node. So what we can do is, instead of naming this function as binary search tree, we can name this function as a utility function like isBSTUtil, and we can have another function named as binary search tree in which we can take only the address of root node, and this function can call isBSTUtil function, passing address of root, minimum possible value in integer variable for -infinity, and maximum possible value in integer variable for +infinity. Int min and int max here are macros for minimum and maximum possible values in int. So this is our solution using second approach, which is quite efficient. In this recursion, we will go to each node once, and at each node we will take constant time to see whether data in that node is in a defined range or not. Time complexity would be big O of n, where n is number of nodes in the binary tree. For the previous algorithm, time complexity was big O of n square. One more thing, in this code I have not handled the case that binary search tree can have duplicates. I'm saying that elements in left subtree must be strictly lesser and elements in right subtree must be strictly greater. I'll leave it for you to see how you will allow duplicates. There is another solution to this problem. You can perform in-order traversal of binary tree, and if the tree is binary search tree, you would read the data in sorted order. In-order traversal of a binary search tree gives a sorted list. You can do some hack while performing in-order traversal and check if you are getting the elements in sorted order or not. During the whole traversal, you only need to keep track of previously read node, and at any time data in a node that you are reading must be greater than data in previously read node. Try implementing this solution, it will be interesting. Okay, I'll stop here now. In coming lessons we will discuss some more problems on binary tree. Thanks for watching. In this lesson we are going to write code to delete a node from binary search tree. In most data structures, deletion is tricky. In case of binary search trees too, it's not so straightforward. So let's first see what all complications we may have while trying to delete a node from binary search tree. I have drawn a binary search tree of integers here. As we know, in a binary search tree, for each node, value of all nodes in its left subtree is lesser and value of all nodes in its right subtree is greater. For example, in this tree, if I'll pick this node with value 5, then we have 3 and 1 in its left subtree, which are lesser, and we have 7 and 9 in its right subtree, which are greater. And you can pick any other node in the tree and this property will be true, else the tree is not a BST. Now when we need to delete a node, this property must be conserved. Let's try to delete some nodes from this example tree and see if we can rearrange things and conserve this property of binary search tree or not. What if I want to delete this node with value 19? To delete a node from tree, we need to do two things. We need to remove the reference of the node from its parent, so the node is detached from the tree. Here we will cut this link. We will set right child of this node with value 17 as null. And the second thing that we need to do is reclaim the memory allocated to the node being deleted, that is, wipe off the node object from memory. This particular node with value 19 that we are trying to delete here is a leaf node. It has no children. And even if we take this guy out by simply cutting this link, that is removing its reference from its parent and then wiping it off from memory, there is no problem. Property of binary search tree that for each node, value of nodes in left should be lesser and value of nodes in right should be greater is conserved. So deleting a leaf node, a node with no children, is really easy. In this tree, these four nodes with values 1, 9, 13 and 19 are leaf nodes. To delete any of these, we just need to cut the link and wipe off the node. That is, clear it from memory. But what if we want to delete a non-leaf node? What if in this example we want to delete this node with value 15? I can't just cut this link, because if I'll cut this link, we will detach not just the node with value 15, but this complete subtree. We have two more nodes in this subtree. We could have had a lot more. We need to make sure that all other nodes except the node with value 15 that's being deleted remain in the tree. So what do we do now? This particular node that we are trying to delete here has two children or two subtrees. I'll come back to case of node with two children later, because this is not so easy to crack. What I want to discuss first is the case when the node being deleted would have only one child. If the node being deleted would have only one child, like in this example, this node with value 7, this guy has only one child. This guy has a right child but does not have a left child. For such a node, what we can do is we can link its parent to this only child. So the child and everything below the child, we could have some more nodes below 9 as well, will remain attached to the tree, and only the node being deleted will be detached. Now we are not losing any other node than the node with value 7. This is my tree after the deletion. Is this still a binary search tree? Yes, it is. Only the right subtree of node with value 5 has changed. Earlier we had 7 and 9 in right subtree of 5, and now we have 9, which is fine. What if we were having some more nodes below 9? Here in this tree I can have a node in left of 9, and the value in this node has to be lesser than 12, greater than 5, greater than 7, and lesser than 9. We are left with only one choice. We can only have 8 here. In right we can have something lesser than 12 and greater than 5, 7 and 9. All in all between 9 and 12. Okay, so if the original tree was this much after deletion, this is how my tree will look like. Okay, so are we good now? Is the tree in right a BST? Well, yes, it is. When we are setting this node with value 9 as right child of the node with value 5, we are basically setting this particular subtree as right subtree of the node with value 5. Now this subtree is already in right of 5, so value of all nodes in this subtree is already greater than 5. And the subtree itself, of course, is a binary search tree. Any subtree in a binary search tree will also be a binary search tree. So even after deletion, even after the rearrangement, property of the tree that for each node, nodes in left should be lesser and nodes in right should be greater in value is conserved. So this is what we need to do to delete a node with just one child, or a node with just one subtree. Connect its parent to its only child and then wipe it off from memory. There are only two nodes in this tree that have only one child. Let's try to delete this other one with value 3. All we need to do here is set 1 as left child of 5. Once again, if there were some more nodes below 1, then also there was no issue. Okay, so now we are good for two cases. We are good for leaf nodes and we are good for nodes with just one child. And now we should think about the third case. What if a node has two children? What should we do in this case? Let's come back to this node with value 15 that we were trying to delete earlier. With two children, we can't do something like connect parent to one of the children. While trying to delete 15, if we will connect 12 to 13, if we will make 13 the right child of 12, then we will include 13 and anything below 13. That is, we will include the left subtree of 15, but we will lose the right subtree of 15. That is 17 and anything below 17. Similarly, if we will make 17 the right child, then we will lose the left subtree of 15. That is 13 and anything below 13. Actually, this case is tricky, and before I talk about a possible solution, I want to insert some more nodes here. I want to have some more nodes in subtrees of 13 and 17. The reason I'm inserting some more nodes here is because I want to discuss a generic case, and that's why I want these two subtrees to have more than one node. Okay, coming back. When I'm trying to delete this node, my intent basically is to remove this value 15 from the tree. My delete function will have signature something like this. It will take pointer or reference to the root node and value to be deleted as argument. So here I'm deleting this particular node because I want to remove 15 from the tree. What I'm going to do now is something with which I can reduce case 3 to either case 1 or case 2. I'll wipe off 15 from this node and I'll fill in some other value in this node. Of course, I can't fill in any random value. What I'll do is I'll look for the minimum in right subtree of this node and I'll fill in that value here. Minimum in right subtree of this node is 17. So I have filled 17 here. We now have two nodes with value 17. But notice that this node has only one child. We can delete this node because we know how to delete a node with one child. And once this node is deleted, my tree will be good. The final arrangement will be a valid arrangement for my BST. But why minimum in right subtree? Why not value in any other leaf node or any other node with one child? Well, we also need to conserve this property that for each node, nodes in left should have lesser value and nodes in right should have greater value. For this node, if I'm bringing in the minimum from its right subtree, then because I'm bringing in something from its right subtree, it will be greater than the previous value. 17 is greater than 15, so all the elements in left of course will be lesser, and because it's the minimum in right subtree, all the elements in right of this guy would either be greater or equal. We'll have a duplicate that will be equal. Once the duplicate is removed, everything else will be fine. In a tree or subtree, if a node has minimum value, it won't have a left child, because if there is a left child, there is something lesser. And this is another property that we are exploiting. Give this some thought. In a tree or subtree, node with minimum value will not have a left child. There may or may not be a right child. If we would have a right child, like here we have a right child, so here we are reducing case 3 to case 2. If there was no child, we would have reduced case 3 to case 1. Okay, so let's get rid of the duplicate. I'll build a link like this, and after deletion, this is what my tree will look like. So this is what we need to do in case 3. We need to find the minimum in right subtree of the targeted node, then copy or fill in this value, and finally we need to delete the duplicate or the node with minimum value from right subtree. There was another possible approach here, and I must talk about it. Instead of going for minimum in right, we could also go for maximum in left subtree. Maximum in left subtree would of course be greater than or equal to all the values in left. Maximum in left subtree of node with value 15 is 14. I'm copying 14 here. Now all the nodes in left are lesser than or equal to 14, and because we are picking something from left subtree, it will still be lesser than the value being deleted. 14 is less than 15. So all the nodes in this right subtree will still be greater. And if we are picking maximum in a tree or subtree, then that node will not have a right child. because if we have something in right, we have something greater, so the value can't be maximum. The node may have a left child. In this case, node with value 14 doesn't have a left child, so we are basically reducing case 3 to case 1. I'll simply get rid of this node. So we are looking good even after deletion. In case 3, we can apply any of these methods, and this is all in logic part. Let's now write code for this logic. I'll write C++ and we will use recursion. If you're not very comfortable applying recursion on trees, then make sure you watch earlier lessons in this series. You can find link to them in description of this video. In my code here, I have defined node as a structure with 3 fields. We have one field to store data, and we have 2 fields that are pointers to node to store addresses of left and right children. And I want to write a function named delete that should take pointer to root node and the data to be deleted as argument. And this function should return pointer to root node because the root may change after deletion. What we are passing to delete function is only a local copy of root's address. If the address is changing, we need to return it back. To delete a given value or data, we first need to find it in the tree, and once we find the node containing that data, we can try to delete it. Remember, the only identity of tree that we pass to functions is address of the root node, and to perform any action on the tree, we need to start at root. So let's first search for the node with this data. First, I'll cover a corner case. If root is null, that is if the tree is empty, we can simply return. I can say return root or return null here. They will mean the same because root is null. Else, if the data that we are looking for is less than the data in root, then it's in the left subtree. The problem can be reduced to deleting the data from left subtree. We need to go and find the data in left subtree. So we can make a recursive call to delete function passing address of the left child and the data to be deleted. Now the root of the left subtree, that is the left child of this current node, may change after deletion, but the good thing is delete function will return address of the modified root of the left subtree, so we can set the return as left child of the current node. Now if data that we are trying to delete is greater than the data in root, we need to go and delete the data from right subtree. And if the data is neither greater nor lesser, that is if it's equal, then we can try deleting the node containing that data. Now let's handle the 3 cases one by one. If there is no child, we can simply delete that node. What I'll do here is I'll first wipe off the node from memory, and this is how I'll do it. What we have in root right now is address of the node to be deleted. I'm using delete operator here, and that's used to deallocate memory of an object in heap. In C, you would use free function. Now root is a dangling pointer because the object in heap is deleted, but root still has its address. So we can set root as null, and now we can return root. Reference of this node in its parent will not be fixed here. Once this recursive call finishes, then somewhere in these 2 statements, in any of these 2 statements, in any of these 2 else ifs, the link will be corrected. I hope this is making sense. Okay, now let's handle other cases. If only the left child is null, then what I want to do is I first want to store the address of current node that I'm trying to delete in a temporary pointer to node, and now I want to move the root, this pointer named root, to the right child. So the right child becomes the root of this subtree, and now we can delete the node that is being pointed to by temp. We will use delete operator. In C we would be using free function, and now we can return root. Similarly, if the right child is null, I'll first store the address of current root in a temporary pointer to node, then I'll make the left child new root of the subtree. So we'll move to the left child, and then I'll delete the previous root whose address I have in temp, and finally I'll return root. Actually we need to return root in all cases, so I'll remove this return root statement from all these if and else if, and write one return root after everything. Let's talk about the third case now. In case of 2 children, what we need to do is we need to search for minimum element in right subtree of the node that we are trying to delete. Let's say this function find min will give me address of the node with minimum value in a tree or subtree. So I'm calling this function find min, and I'm collecting the return in a pointer to node named temp. Now I should set the data in current node that I'm trying to delete as this minimum value, and now the problem is getting reduced to deleting this minimum value from the right subtree of current node. With this much code, I think I'm done with delete function. This looks good to me. Let's quickly run this code on an example tree and see if this works or not. I have drawn a binary search tree here. Let's say these values outside these nodes are addresses of the nodes. Now I want to delete number 15 from this tree, so I'll make a call to delete function passing address of the root, which is 200, and 15, the value to be deleted. In delete function, for this particular call, control will come to this line. A recursive call will be made. Execution of this call delete 200, 15 will pause, and it will resume only after this function below. Delete 350, 15 returns. Now for this call below, we will go inside the third else in case 3. Here we will find the node with minimum value in right, which is 17, which is 400. The value is 17. Address is 400. First we will set the data in node at 350 as 17. And now we are making a recursive call to delete 17 from right subtree of 350. We have only one node in right subtree of 350. Here we have case 1. In this call, we will simply delete the node at 400 and return null. Remember, root will be returned in all calls in the end. Now delete 350, 15 will resume, and in this resumed call, we will set address of right child of node at 350 as null. As you can see, the link in parent is being corrected when the recursion is unfolding and the function call corresponding to the parent is resuming. And now this guy can return, and now in this call we will resume at this line. So right child of node at 200 will be set as 350. It's already 350, but it will be written again, and now this call can also finish. So I hope you got some sense of how this recursion is working. You can find link to all the source code and code to test the delete function in description of this video. This is it for this lesson. Thanks for watching. In this lesson, we are going to solve another interesting problem on binary search tree. And the problem is, given a node in a binary search tree, we need to find its in-order successor. That is the node that would come immediately after the given node in in-order traversal of the binary search tree. As we know, in in-order traversal of a binary tree, we first visit the left subtree, then the root, and then the right subtree. Left and right subtrees are visited recursively in same manner. So for each node, we first visit its left subtree, then the node itself, and then its right subtree. We have already discussed in-order traversal in detail in a previous lesson in this series. You can check the description of this video for a link to it. In-order implementation will basically be a recursive function, something like what I'm showing in right here. There are two recursive calls in this function, one to visit the left subtree and another to visit the right subtree. Time complexity of in-order traversal is big O of n, where n is number of nodes in the tree. We visit each node exactly once, so time taken is proportional to number of nodes in the tree. I have drawn a binary search tree of integers here. Binary search tree, as we know, is a binary tree in which for each node, value of nodes in left is lesser and value of nodes in right is greater. Let's quickly see what will be the in-order traversal for this binary search tree. We'll start at root of the tree. Now for any node, we first need to visit all nodes in its left, and then only we can visit that node. So we will have to go left. Basically, we will make a recursive call to go to left child of this node. For this guy, once again, we have something in left. So we will make another recursive call and go to its left child. Now we are at this node with value 8, and we will have to go left one more time. And now for this node with value 6, which is a leaf node, we have nothing in left. So we can simply say that its left subtree is done, and hence we can visit this guy. visiting for me is reading the data in that node. I'll write the data here. And now for this node there's nothing in write as well, so we can simply say that its write is also done. And now we are completely done for this guy. So recursive call corresponding to this node will finish, and we will go back to call corresponding to its parent. If we will come back to a node from its left child, then it will be unvisited, because we can't visit a node until its left is done. So when we are coming back to 8, 8 is unvisited. So we can simply visit this node, that is, read the data in this node. When I'll visit a node, I'll paint it in yellow. And now there's nothing in write of this node, so we can simply say that write is done. Now we are done with this node, so call corresponding to this node will finish, and we will go back to its parent. Once again we are coming back to the parent from left, so the parent, that is this node with value 10, is unvisited. If we would come back to a node from right, then it would already be visited. So I'm visiting 10, and now we can go to write of 10. So far we have visited 3 nodes. We first visited node with value 6, and then we visited node with value 8. So 8 is successor of 6, and then 10 is successor of 8. Now let's see what will be the successor of 10. For nodes with values 6 and 8, there was nothing in write, so we were unwinding and going to the parent. But for a node, if there would be something in write, that is, if there would be a write subtree, then its successor would definitely be in its write subtree, because after visiting that node we will go right. Now at this stage we are at this node with value 12. For this guy we will first go left, and now we are at node with value 11, which is a leaf node. There is nothing in left, so we can simply say that left is done, and we can print the data, that is, visit this node. So in order successor of 10 is 11. Now for node with value 11 there is nothing in write, so we will go back to its parent, and now we can visit this guy. So after 11 we have 12. There is nothing in write of 12, so call for this guy will finish, and we will go to its parent. Now we are coming back to 10 again, but this time from right, so this guy is already visited. So we need not do anything, we can simply go to its parent. And now we are at this node with value 15. We are coming from left, this guy is unvisited, so we can visit it, and now we can go to its right. We will go on like this. Successor of 15 would be 16, and after 16 we will print 17. Then after 17 we will print 20, then 25, and the last element would be 27. So this is in-order traversal of this binary search tree. Notice that we have printed the integers in sorted order. When we perform in-order traversal on a binary search tree, then elements are visited in sorted order. Now the problem that we want to solve is, given a value in the tree, we want to find its in-order successor. In a binary search tree, it would be the next higher value in the tree. But what's the big deal here? Can't we just perform in-order traversal, and while performing the traversal figure out the successor? Well, we can do so, but it will be expensive. Running time of in-order is big O of n, and we may want to do better. Finding next and previous element in some data could be a frequently performed operation. And good thing about binary search tree is that frequently performed operations like insertion, deletion, and search happen in big O of h, where h is height of the tree. So it would be good if we are able to find successor and predecessor in big O of h. We always try to keep a tree balanced to minimize its height. Height of a balanced binary tree is log n to the base 2, and big O of log n running time for any operation is almost the best running time that we can have. So can we find in-order successor in big O of h? I have redrawn the example tree here. Let's see what we can do in various cases. What node would we visit after this node with value 10? Can we deduce this logically? Well, if you remember the simulation of in-order traversal that we had done earlier, then if we have already visited this node, then we are done with its left subtree, and we have read the data in this node, and we need to go right. Now in the right subtree, we will have to go left as long as it's possible to go. And if we can't go left anymore, like here, there is nothing left of this node with value 11, then this is the node that I'm visiting next. So for our node, if there is a right subtree, then in-order successor would be the leftmost node in its right subtree. In a BST, it would be the node with minimum value in its right subtree. I would say this is case 1. In this case, all we need to do is we need to go as left as possible in right subtree. In a BST, it will also mean finding the minimum in right subtree. Leftmost node will also be the minimum in the subtree. Now this is one case. Our node here had a right subtree. What would be the successor if there would be no right subtree? What node would we visit after this node with value 8? This guy does not have a right subtree. If we have already visited this guy, then we have visited its left and this node itself. And there is nothing in right, so we can say that right is also visited, but we have not found the successor yet. Now where do we go from here? Well, if you remember the simulation that we had done earlier, we need to go to the parent of this node. And if we are going to the parent from left, which is the case here, then the parent would be unvisited. For this node with value 10, we just finished its left subtree and we are coming back. So now we can visit this node. So this is my successor. Let's now pick another node with no right subtree. What would be in-order successor of this node with value 12? What node would we visit next? Now here, once again, we do not have a right subtree for this node, so we must go back to its parent and see if it's unvisited. But if we're going to the parent from right, if the node that we just visited is a right child, which is the case here, then the parent would already be visited because we are coming back after visiting its right subtree. This node must have been visited before going right. So what should we do? Now the recursion will roll back further and we need to go to parent of 10. And now we are going to 15 from left, so this guy is unvisited. So we can visit this node and this is my successor. If the node does not have a right subtree, we need to go to the nearest ancestor, for which given node would be in its left subtree. Here for 12 we first went to 10, but 12 is in right subtree of 10, so we went to the next ancestor 15, and 12 is in left of 15. So this is the nearest ancestor for which 12 is in left, and hence this is my in-order successor. This algorithm works fine, but there is an issue. How do we go from a node to its parent? Well, we can design our tree such that node can have reference to its parent. So far in most lessons we have defined node as a structure with 3 fields, something like this. This is how we would define node in C or C++. We have 1 field to store data and we have 2 pointers to node to store reference or addresses of left and right children. Often it makes a lot of sense to have 1 more field to store the address of parent. We can design our tree like this and then we will not have problem walking the tree up using parent link. We can easily go to the ancestors. But what if there is no link to parent? In this case, what we can do is we can start at root and walk the tree from root to the given node. In a BST, this is really easy. For 12, we will start at root. 12 is lesser than value in root, so we need to go left. And now we are at 10. Now 12 is greater than 10, so we need to go right. And now we are at 12. If we will walk the tree from root to the given node, we will go through all the ancestors of the given node. In-order successor would be the deepest node or deepest ancestor in this path, for which given node would be in left subtree. 12 has only 2 ancestors. We have 10, but 12 is in right of 10. And then we have 15, and 12 is in left of 15. So 15 is my successor. Now let's use this technique to find successor of 6. We will first walk down from root to this node. 6 is in left for all the ancestors, but deepest ancestor for which 6 is in left is this node with value 8. So this is my successor. Remember, we need to look at ancestors only if there is no right subtree. For 6 there is no right subtree. Okay, so the algorithm looks good. Let's now write code for this. In my C++ code here, I'm going to write a function named getSuccessor that will take address of root node and address of another node for which we need to find the successor, and this function will return address of the successor node. We could design this function differently. Instead of taking pointer to the node for which we want to find the successor as argument, we could just take the data as argument, and for this data, for this element, we can find the successor node and return its address, and that's why the return type here is struct node asterisk, because we will be returning address in a pointer. Or what we can also do is we can return the element itself, the successor element itself. We can implement with any of these signatures. Let's implement this one. We will pass the data in current node and we will return back the address of the successor. Now the first thing that we need to do is we need to search the node with this data. I'm going to make call to a function named find that will take address of the root node and the data and will return me pointer to the node with this data. If this function returns me null, that is if the data is not found in the tree, we can simply return null. Else we have the address of the current node in this pointer to node that we have named current. Now in a BST, this search operation will cost us big O of h, where h is height of the tree. Search in a BST is not very expensive. We could have avoided this search if we would have passed address of the current node instead of passing the data as this second argument. But let's go with this. Let's now find the successor of this node. If this node has right subtree, that is if the right subtree is not null, we need to go to the leftmost node in the right subtree. I have declared a temporary pointer to node here, and initially I've set it to current.right, and with this while loop I'll go to the leftmost node. While there is something in the left, keep going, and finally when I'll come out of this loop, I'll have address of leftmost node in the right subtree and I can return this address. This particular node will also be the node with minimum value in right subtree. I'll move this code in another function. I have written this function named findMin that will return node with minimum value in a tree or subtree. In getSuccessor function, I'll simply say return findMin and I'll pass the address of right child of current node. So basically I'm passing the right subtree here. Okay, now let's talk about case 2. If there is no right subtree, what we need to do is we need to walk the tree from root till current node, and we need to find the deepest ancestor for which current node will be in its left subtree. What I'm going to do here is I'm going to declare a pointer to node named successor, and initially I'll set it as null, and I'll have another pointer to node named ancestor, and initially I'll set this as root. And with this while loop we will walk the tree till we have not reached the current node. To walk the tree we will use the property of binary search tree, that for each node value of nodes in left is lesser and value of nodes in right is greater. If data in current node is less than the data in ancestor, then first of all this ancestor may be my in order successor because the current node is in its left. So what we can do is we can set this guy as successor and we can go left. While traversing, if we will find a deeper node with this property that current node will be in its left subtree, then successor will be updated. Else, if the current node lies in right, we simply need to move right. When we'll come out of this while loop, successor will either be null or it will be the address of some node. Not all nodes in the tree will have a successor. Node with maximum value will not have a successor. After coming out of this while loop, we can return the successor. So this is my getSuccessor function, and I think this should work. You can find link to complete source code in description of this video. Overall, time complexity of this function will be big O of h, and this is what we wanted. We wanted to find successor in big O of h. Here we are already performing the search in big O of h. Finding minimum will also take big O of h, and walking the tree from root to a node in BST will also take big O of h. So overall this is big O of h. If you have understood this code, this logic, then it should be very easy for you writing function to find in order predecessor. I encourage you to write it. I'll stop here now. In coming lessons we will solve some more interesting problems on binary trees and binary search trees. Thanks for watching. Hello everyone. So far in this series on data structures, we have talked about some of the linear data structures like array, linked list, stack, and queue. In all these structures, data is arranged in a linear or sequential manner, so we can call them linear data structures. And we have also talked about tree, which is a non-linear data structure. Tree is a hierarchical structure. Now, as we understand, data structures are ways to store and organize data, and for different kinds of data we use different kinds of data structures. In this lesson we are going to introduce you to another non-linear data structure that has got its application in a wide number of scenarios in computer science. It is used to model and represent a variety of systems, and this data structure is graph. When we study data structures, we often first study them as mathematical or logical models. Here also we will first study graph as a mathematical or logical model, and we will go into implementation details later. Okay, so let's get started. A graph, just like a tree, is a collection of objects or entities that we call nodes or vertices connected to each other through a set of edges. But in a tree, connections are bound to be in a certain way. In a tree, there are rules dictating the connection among the nodes. In a tree with n nodes, we must have exactly n-1 edges. One edge for each parent-child relationship. As we know, an edge in a tree is for a parent-child relationship, and all nodes in a tree except the root node would have exactly one parent, and that's why if there are n nodes, there must be exactly n-1 edges. In a tree, all nodes must be reachable from the root, and there must be exactly one possible path from root to a node. Now in a graph, there are no rules dictating the connection among the nodes. A graph contains a set of nodes and a set of edges, and edges can be connecting nodes in any possible way. Tree is only a special kind of graph. Now graph as a concept has been studied extensively in mathematics. If you have taken a course on discrete mathematics, then you must be knowing about graphs already. In computer science, we basically study and implement the same concept of graph from mathematics. The study of graphs is often referred to as graph theory. In pure mathematical terms, we can define graph something like this. A graph G is an ordered pair of a set V of vertices and a set E of edges. Now I'm using some mathematical jargon here. An ordered pair is just a pair of mathematical objects in which the order of objects in the pair matters. This is how we write and represent an ordered pair. Objects separated by comma put within parentheses. Now because the order here matters, we can say that V is the first object in the pair and E is the second object. An ordered pair AB is not equal to BA unless A and B are equal. In our definition of graph here, first object in the pair must always be a set of vertices and the second object must be a set of edges. That's why we are calling the pair an ordered pair. We also have concept of unordered pair. An unordered pair is simply a set of two elements. Order is not important here. We write an unordered pair using curly brackets or braces. Because the order is not important here, unordered pair AB is equal to BA. It doesn't matter which object is first and which object is second. Okay, coming back. So a graph is an ordered pair of a set of vertices and a set of edges, and G equal VE is a formal mathematical notation that we use to define a graph. Now I have a graph drawn here in the right. This graph has 8 vertices and 10 edges. What I want to do is I want to give some names to these vertices, because each node in a graph must have some identification. It can be a name or it can be an index. I'm naming these vertices as V1, V2, V3, V4, V5 and so on. And this naming is not indicative of any order. There is no first, second and third node here. I could give any name to any node. So my set of vertices here is this. We have 8 elements in the set: V1, V2, V3, V4, V5, V6, V7 and V8. So this is my set of vertices for this graph. Now what's my set of edges? To answer this, we first need to know how to represent an edge. An edge is uniquely identified by its 2 endpoints. So we can just write the names of the 2 endpoints of an edge as a pair, and it can be a representation for the edge. But edges can be of 2 types. We can have a directed edge in which connection is one way, or we can have an undirected edge in which connection is two-way. In this example graph that I'm showing here, edges are undirected. But if you remember the tree that I had shown earlier, then we had directed edges in that tree. With this directed edge that I'm showing you here, we are saying that there is a link or path from vertex U to V, but we cannot assume a path from V to U. This connection is one way. For a directed edge, one of the endpoints would be the origin and the other endpoint would be the destination. And we draw the edge with an arrowhead pointing towards the destination. For our edge here, origin is U and destination is V. A directed edge can be represented as an ordered pair. First element in the pair can be the origin and second element can be the destination. So with this directed edge represented as ordered pair UV, we have a path from U to V. If we want a path from V to U, we need to draw another directed edge here with V as origin and U as destination. And this edge can be represented as ordered pair VU. The upper one here is UV and the below one is VU. And they are not same. Now if the edge is undirected, the connection is two-way. An undirected edge can be represented as an unordered pair. Here, because the edge is bidirectional, origin and destination are not fixed. We only need to know what 2 endpoints are being connected by the edge. So now that we know how to represent edges, we can write the set of edges for this example graph here. We have an undirected edge between V1 and V2. Then we have one between V1 and V3. Then we have V1, V4. This is really simple. I'll just go ahead and write all of them. So this is my set of edges. Typically in a graph, all edges would either be directed or undirected. It's possible for a graph to have both directed and undirected edges, but we are not going to study such graphs. We are only going to study graphs in which all edges would either be directed or undirected. A graph with all directed edges is called a directed graph or digraph, and a graph with all undirected edges is called an undirected graph. There is no special name for an undirected graph. Usually, if the graph is directed, we explicitly say that it's a directed graph or digraph. So these are 2 types of graph: directed graph or digraph in which edges are unidirectional or ordered pairs, and undirected graph in which edges are bidirectional or unordered pairs. Now, many real-world systems and problems can be modeled using a graph. Graphs can be used to represent any collection of objects having some kind of pairwise relationship. Let's have a look at some of the interesting examples. A social network like Facebook can be represented as an undirected graph. A user would be a node in the graph, and if 2 users are friends, there would be an edge connecting them. A real social network would have millions and billions of nodes. I can show only few in my diagram here because I'm short of space. Now, social network is an undirected graph because friendship is a mutual relationship. If I'm your friend, you are my friend too. So connections have to be two-way. Now, once a system is modeled as a graph, A lot of problems can easily be solved by applying standard algorithms in graph theory. Like here in this social network, let's say we want to do something like suggest friends to a user. Let's say we want to suggest some connections to Rama. One possible approach to do so can be suggesting friends of friends who are not connected already. Rama has 3 friends, Ella, Bob, and Katie, and friends of these 3 that are not connected to Rama already can be suggested. There is no friend of Ella which is not connected to Rama already. Bob, however, has 3 friends, Tom, Sam, and Lee, that are not friends with Rama, so they can be suggested. And Katie has 2 friends, Lee and Swati, that are not connected to Rama. We have counted Lee already, so in all we can suggest these 4 users to Rama. Now, even though we described this problem in context of a social network, this is a standard graph problem. The problem here in pure graph terms is finding all nodes having length of shortest path from a given node equal to 2. Standard algorithms can be applied to solve this problem. We'll talk about concepts like path in a graph in some time. For now, just know that the problem that we just described in context of a social network is a standard graph problem. Okay, so a social network like Facebook is an undirected graph. Now let's have a look at another example. Interlinked web pages on the internet or the World Wide Web can be represented as a directed graph. A web page that would have a unique address or URL would be a node in the graph, and we can have a directed edge if a page contains link to another page. Now once again, there are billions of pages on the web, but I can show only few here. The edges in this graph are directed because the relationship is not mutual this time. If page A has a link to page B, then it's not necessary that page B will also have a link to page A. Let's say one of the pages on mycodeschool.com has a tutorial on graph, and on this page I have put a link to Wikipedia article on graph. Let's assume that in this example graph that I'm showing you here, page P is my mycodeschool tutorial on graph with this address or URL mycodeschool.com/videos/graph. And let's say page Q is the Wikipedia article on graph with this URL wikipedia.org/wiki/graph. Now on my page, that is page P, I have put a link to Wikipedia page on graph. If you are on page P, you can click on this link and go to page Q. But Wikipedia has not reciprocated to my favor by putting a link back to my page. So if you are on page Q, you cannot click on a link and come to page P. Connection here is one way. And that's why we have drawn a directed edge here. Okay, now once again, if we are able to represent web as a directed graph, we can apply standard graph theory algorithms to solve problems and perform tasks. One of the tasks that search engines like Google perform very regularly is web crawling. Search engines use a program called Web Crawler that systematically browses the World Wide Web to collect and store data about web pages. Search engines can then use this data to provide quick and accurate results against search queries. Now, even though in this context we are using a nice and heavy term like web crawling is basically graph traversal, or in simpler words, act of visiting all nodes in a graph. And no prizes for guessing that there are standard algorithms for graph traversal. We'll be studying graph traversal algorithms in later lessons. Okay, now the next thing that I want to talk about is concept of a weighted graph. Sometimes in a graph, all connections cannot be treated as equal. Some connections can be preferable to others. Like for example, we can represent intercity road network, that is the network of highways and freeways between cities, as an undirected graph. I'm assuming that all highways would be bidirectional. Intracity road network, that is road network within a city, would definitely have one-way roads, and so intracity road network must be represented as a directed graph, but intercity road network in my opinion can be represented as an undirected graph. Now clearly we cannot treat all connections as equal here. Roads would be of different lengths, and to perform a lot of tasks, to solve a lot of problems, we need to take length of roads into account. In such cases, we associate some weight or cost with every edge. We label the edges with their weights. In this case, weight can be length of the roads. So what I'll do here is I'll just label these edges with some values for their lengths. And let's say these values are in kilometers. And now edges in this graph are weighted, and this graph can be called a weighted graph. Let's say in this graph we want to pick the best route from city A to city D. Have a look at these 4 possible routes. I'm showing them in different colors. Now if I would treat all edges as equal, then I would say that the green route through B and C and the red route through E and F are equally good. Both these paths have 3 edges. And this yellow route through E is the best because we have only 2 edges in this path. But with different weights assigned to the connections, I need to add up weights of edges in a path to calculate total cost. When I'm taking weight into account, shortest route is through B and C. Connections have different weights, and this is really important here in this graph. Actually, we can look at all the graphs as weighted graphs. An unweighted graph can basically be seen as a weighted graph in which weight of all the edges is same, and typically we assume the weight as 1. Okay, so we have represented intercity road network as a weighted undirected graph. Social network was an unweighted undirected graph, and World Wide Web was an unweighted directed graph, and this one is a weighted undirected graph. Now this was intercity road network. I think intracity road network, that is road network within a city, can be modeled as a weighted directed graph, because in a city there would be some one-ways. Intersections in intracity road network would be nodes, and road segments would be our edges. And by the way, we can also draw an undirected graph as directed. It's just that for each undirected edge we'll have 2 directed edges. We may not be able to redraw a directed graph as undirected, but we can always redraw an undirected graph as directed. Okay, I'll stop here now. This much is good for an introductory lesson. In next lesson we will talk about some more properties of graph. This is it for this lesson. Thanks for watching. In our previous lesson we introduced you to graphs. We defined graph as a mathematical or logical model and talked about some of the properties and applications of graph. Now in this lesson we will discuss some more properties of graph. But first I want to do a quick recap of what we have discussed in our previous lesson. A graph can be defined as an ordered pair of a set of vertices and a set of edges. We use this formal mathematical notation G equal VE to define a graph. Here V is set of vertices and E is set of edges. Ordered pair is just a pair of mathematical objects in which order of objects in the pair matters. It matters which element is first and which element is second in the pair. Now as we know, to denote number of elements in a set, that we also call cardinality of a set, we use the same notation that we use for modulus or absolute value. So this is how we can denote number of vertices and number of edges in a graph. Number of vertices would be number of elements in set V, and number of edges would be number of elements in set E. Moving forward, this is how I'm going to denote number of vertices and number of edges in all my explanations. Now as we had discussed earlier, edges in a graph can either be directed, that is one-way connections, or undirected, that is two-way connections. A graph with only directed edges is called a directed graph or digraph, and a graph with only undirected edges is called an undirected graph. Now sometimes all connections in a graph cannot be treated as equal, so we label edges with some weight or cost, like what I'm showing here. And a graph in which some value is associated to connections as cost or weight is called a weighted graph. A graph is unweighted if there is no cost distinction among edges. Okay, now we can also have some special kind of edges in a graph. These edges complicate algorithms and make working with graphs difficult, but I'm going to talk about them anyway. An edge is called a self-loop or self-edge if it involves only one vertex. If both endpoints of an edge are same, then it's called a self-loop. We can have a self loop in both directed and undirected graphs, but the question is, why would we ever have a self loop in a graph? Well, sometimes if edges are depicting some relationship or connection that's possible with the same node as origin as well as destination, then we can have a self loop. For example, as we had discussed in our previous lesson, interlinked web pages on the internet or the World Wide Web can be represented as a directed graph. A page with a unique URL can be a node in the graph, and we can have a directed edge if a page contains link to another page. Now we can have a self loop in this graph because it's very much possible for a web page to have a link to itself. Have a look at this web page, mycodeschool.com/videos. In the header, we have links for workouts page, problems page, and videos page. Right now, I'm already on videos page, but I can still click on videos link, and all that will happen with the click is a refresh because I'm already on videos page. My origin and destination are same here. So if I'm representing World Wide Web as a directed graph, the way we just discussed, then we have a self loop here. Now the next special type of edge that I want to talk about is multi-edge. An edge is called a multi-edge if it occurs more than once in a graph. Once again, we can have a multi-edge in both directed and undirected graphs. First multi-edge that I'm showing you here is undirected and the second one is directed. Now once again the question, why should we ever have a multi-edge? Well, let's say we are representing flight network between cities as a graph. A city would be a node and we can have an edge if there is a direct flight connection between any two cities. But then there can be multiple flights between a pair of cities. These flights would have different names and may have different costs. If I want to keep the information about all the flights in my graph, I can draw multi-edges. I can draw one directed edge for each flight, and then I can label an edge with its cost or any other property. I just labeled edges here with some random flight numbers. Now, as we were saying earlier, self-loops and multi-edges often complicate working with graphs. Their presence means we need to take extra care while solving problems. If a graph contains no self-loop or multi-edge, it's called a simple graph. In our lessons, we will mostly be dealing with simple graphs. Now, I want you to answer a very simple question. Given number of vertices in a simple graph, that is a graph with no self-loop or multi-edge, what would be maximum possible number of edges? Well, let's see. Let's say we want to draw a directed graph with 4 vertices. I have drawn 4 vertices here. I'll name these vertices V1, V2, V3 and V4. So this is my set of vertices. Number of elements in set V is 4. Now it's perfectly fine if I choose not to draw any edge here. This will still be a graph. Set of edges can be empty. Nodes can be totally disconnected. So minimum possible number of edges in a graph is 0. Now if this is a directed graph, what do you think can be maximum number of edges here? Well, each node can have directed edges to all other nodes. In this figure here, each node can have directed edges to 3 other nodes. We have 4 nodes in total, so maximum possible number of edges here is 4 into 3, that is 12. I have shown edges originating from a vertex in same color here. This is the maximum that we can draw if there is no self-loop or multi-edge. In general, if there are n vertices, then maximum number of edges in a directed graph would be n into n minus 1. So in a simple directed graph, number of edges would be in this range 0 to n into n minus 1. Now what do you think would be the maximum for an undirected graph? In an undirected graph, we can have only one bidirectional edge between a pair of nodes. We can't have 2 edges in different directions. So here the maximum would be half of the maximum for directed. So if the graph is simple and undirected, number of edges would be in the range 0 to n into n minus 1 by 2. Remember, this is true only if there is no self-loop or multi-edge. Now if you can see, number of edges in a graph can be really large compared to number of vertices. For example, if number of vertices in a directed graph is equal to 10, maximum number of edges would be 90. If number of vertices is 100, maximum number of edges would be 9900. maximum number of edges would be close to square of number of vertices. A graph is called dense if number of edges in the graph is close to maximum possible number of edges. That is, if the number of edges is of the order of square of number of vertices. And a graph is called sparse if the number of edges is really less, typically close to number of vertices and not more than that. There is no defined boundary for what can be called dense and what can be called sparse. It all depends on context. But this is an important classification. While working with graphs, a lot of decisions are made based on whether the graph is dense or sparse. For example, we typically choose a different kind of storage structure in computer's memory for a dense graph. We typically store a dense graph in something called adjacency matrix. And for a sparse graph, we typically use something called adjacency list. I'll be talking about adjacency matrix and adjacency list in next lesson. Okay, now the next concept that I want to talk about is concept of path in a graph. A path in a graph is a sequence of vertices where each adjacent pair in the sequence is connected by an edge. I'm highlighting a path here in this example graph. The sequence of vertices A, B, F, H is a path in this graph. Now we have an undirected graph here. Edges are bidirectional. In a directed graph, all edges must also be aligned in one direction, the direction of the path. A path is called simple path if no vertices are repeated. And if vertices are not repeated, then edges will also not be repeated. So in a simple path, both vertices and edges are not repeated. This path A, B, F, H that I have highlighted here is a simple path, but we could also have a path like this. Here, start vertex is A and end vertex is D. In this path, one edge and two vertices are repeated. In graph theory, there is some inconsistency in use of this term path. Most of the time when we say path, we mean a simple path. And if repetition is possible, we use this term walk. So a path is basically a walk in which no vertices or edges are repeated. A walk is called a trail if vertices can be repeated but edges cannot be repeated. I'm highlighting a trail here in this example graph. Okay, now I want to say this once again. Walk and path are often used as synonyms. But most often when we say path, we mean simple path, a path in which vertices and edges are not repeated. Between two different vertices, if there is a walk in which vertices or edges are repeated, like this walk that I'm showing you here in this example graph, then there must also be a path or simple path, that is a walk in which vertices or edges would not be repeated. In this walk that I'm showing you here, we are starting at A and we are ending our walk at C. There is a simple path from A to C with just one edge. All we need to do is we need to avoid going to B, E, H, D and then coming back again to A. So this is why we mostly talk about simple path between two vertices. Because if any other walk is possible, simple path is also possible. And it makes most sense to look for a simple path. So this is what I'm going to do throughout our lessons. I'm going to say path, and by path I'll mean simple path. And if it's not a simple path, I'll say it explicitly. A graph is called strongly connected if in the graph there is a path from any vertex to any other vertex. If it's an undirected graph, we simply call it connected. And if it's a directed graph, we call it strongly connected. In leftmost and rightmost graphs that I'm showing you here, we have a path from any vertex to any other vertex. But in this graph in the middle, we do not have a path from any vertex to any other vertex. We cannot go from vertex C to A. We can go from A to C, but we cannot go from C to A. So this is not a strongly connected graph. Remember, if it's an undirected graph, we simply say connected, and if it's a directed graph, we say strongly connected. If a directed graph is not strongly connected, but can be turned into connected graph by treating all edges as undirected, then such a directed graph is called weakly connected. If we just ignore the directions of the edges here, this is connected. But I would recommend that you just remember connected and strongly connected. this leftmost undirected graph is connected. I removed one of the edges and now this is not connected. Now we have two disjoint connected components here, but the graph overall is not connected. Connectedness of a graph is a really important property. If you remember, intra-city road network within a city that would have a lot of one-ways can be represented as a directed graph. Now, an intra-city road network should always be strongly connected. We should be able to reach any street from any street, any intersection to any intersection. Okay, now that we understand concept of a path, next I want to talk about cycle in a graph. A walk is called a closed walk if it starts and ends at same vertex, like what I'm showing here. And there is one more condition. The length of the walk must be greater than 0. Length of a walk or path is number of edges in the path. Like for this closed walk that I'm showing you here, length is 5 because we have 5 edges in this walk. So a closed walk is a walk that starts and ends at same vertex, and the length of which is greater than 0. Now some may call closed walk a cycle, but generally we use the term cycle for a simple cycle. A simple cycle is a closed walk in which other than start and end vertices, no other vertex or edge is repeated. Right now what I'm showing you here in this example graph is a simple cycle, or we can just say cycle. A graph with no cycle is called an acyclic graph. A tree, if drawn with undirected edges, would be an example of an undirected acyclic graph. Here in this tree we can have a closed walk, but we cannot have a simple cycle. In this closed walk that I'm showing you here, our edge is repeated. There would be no simple cycle in a tree. And apart from tree, we can have other kind of undirected acyclic graphs also. A tree also has to be connected. Now we can also have a directed acyclic graph. As you can see here also, we do not have any cycle. You cannot have a path of length greater than 0 starting and ending at the same vertex. A directed acyclic graph is often called a DAG. Cycles in a graph cause a lot of issues in designing algorithms for problems like finding shortest route from one vertex to another. And we will talk about cycles a lot when we will study some of these advanced algorithms in coming lessons. For this lesson, I'll stop here now. In our next lesson, we will discuss ways of creating and storing graph in computer's memory. This is it for this lesson. Thanks for watching. Hello everyone. In our previous lessons, we introduced you to graphs, and we also looked at and talked about some of the properties of graph. But so far, we have not discussed how we can implement graph, how we can create a logical structure like graph in computer's memory. So let us try to discuss this. A graph, as we know, contains a set of vertices and a set of edges, and this is how we define graph in pure mathematical terms. A graph G is defined as an ordered pair of a set V of vertices and a set E of edges. Now, to create and store a graph in computer's memory, the simplest thing that we probably can do is that we can create two lists. One to store all the vertices and another to store all the edges. For a list, we can use an array of appropriate size, or we can use an implementation of a dynamic list. In fact, we can use a dynamic list available to us in language libraries, something like vector in C++ or ArrayList in Java. Now, a vertex is identified by its name. So the first list, the list of vertices, would simply be a list of names or strings. I just filled in names of all the vertices for this example graph here. Now what should we fill in this edge list here? An edge is identified by its two endpoints. So what we can do is we can create an edge as an object with two fields. We can define edge as a structure or class with two fields, one to store the start vertex and another to store the end vertex. Edge list would basically be an array or list of this type, struct edge, In these two definitions of edge that I have written here, in the first one I have used character pointers, because in C we typically use character pointers to store or refer to strings. We could use character array also. In C++ or Java, where we can create classes, we have string available to us as a data type, so we can use that also. So we can use any of these for the fields. We can use character pointer or character array or string data type if it's available. Depends on how you want to design your implementation. Now let's fill this edge list here for this example graph. Each row now here has two boxes. Let's say the first one is to store the start vertex and the second one is to store the end vertex. The graph that we have here is an undirected graph, so any vertex can be called start vertex and any vertex can be called end vertex. Order of the vertices is not important here. We have 9 edges here, one between A and B, another between A and C, another between A and D, and then we have BE and BF. Instead of having BF as an entry, we could also have FB, but we just need one of them. And then we have CG, DH, EH, and FH. Actually, there's one more. We also have GH. We have 10 edges in total here and not 9. Now, once again, because this is an undirected graph, if we are saying that there is an edge from F to H, we are also saying that there is an edge from H to F. There is no need to have another entry as HF. We will unnecessarily be using extra memory. If this was a directed graph, FH and HF would have meant two different connections. Which is the start vertex and which is the end vertex would have mattered. Maybe in case of undirected graphs, we should name the fields as first vertex and second vertex, and in case of directed graphs, we should name the fields as start vertex and end vertex. Now our graph here could also be a weighted graph. We could have some cost or weight associated with the edges. As we know, in an unweighted graph, cost of all the connections is equal. But in a weighted graph, different connections would have different weight or different cost. Now in this example graph here, I have associated some weights to these edges. Now how do you think we should store this data, the weight of edges? Well, if the graph is weighted, we can have one more field in the edge object to store the weight. Now an entry in my edge list has 3 fields, one to store the start vertex, one to store the end vertex, and one more to store the weight. So this is one possible way of storing a graph. We can simply create 2 lists, one to store the vertices and another to store the edges. But this is not very efficient. For any possible way of storing and organizing data, we must also see its cost. And when we say cost, we mean 2 things: time cost of various operations and the memory usage. Typically, we measure the rate of growth of time taken with size of input or data, what we also call time complexity. And we measure the rate of growth of memory consumed with size of input or data, what we also call space complexity. Time and space complexities are most commonly expressed in terms of what we call big O notation. For this lesson, I'm assuming that you already know about time and space complexity analysis and big O notation. If you want to revise some of these concepts, then you can check the description of this video for link to some lessons. We always want to minimize the time cost of most frequently performed operations, and we always want to make sure that we do not consume unreasonably high memory. Okay, so let's now analyze this particular structure that we are trying to use to store our graph. Let's first discuss the memory usage. For the first list, the vertex list, least number of rows needed or consumed would be equal to number of vertices. Now each row here in this vertex list is a name or string, and string can be of any length. Right now all strings have just one character because I simply named the nodes A, B, C and so on. But we could have names with multiple characters, And because strings can be of different lengths, all rows may not be consuming the same amount of memory. Like here. Here I'm showing an intra-city road network as a weighted graph. Cities are my nodes and road distances are my weights. Now for this graph, as you can see, names are of different lengths. So all rows in vertex list or all rows in edge list would not cost us same. More characters will cost us more bytes. But we can safely assume that the names will not be too long. We can safely assume that in almost all practical scenarios, average length of strings will be a really small value. If we assume it to be always lesser than some constant, then the total space consumed in this vertex list will be proportional to the number of rows consumed, that is, the number of vertices. Or in other words, we can say that space complexity here is big O of number of vertices. This is how we write number of vertices with two vertical bars. What we basically mean here is number of elements in set V. Now for the edge list, once again, we are storing strings in first two fields of the edge object. So once again, each row here will not consume same amount of memory. But if we are just storing the reference or pointer to a string, like here in the first row, instead of having values filled in these two fields, we could have references or pointers to the names in the vertex list. If we will design things like this, each row will consume same memory. This, in fact, is better because references in most cases would cost us a lot lesser than a copy of the name. And as reference, we can have the actual address of the string. And that's what we are doing when we are saying that start vertex and end vertex can be character pointers. Or maybe a better design would be simply having the index of the name or string in vertex list. Let's say A is at index 0 in the vertex list and B is at index 1 and C is at index 2, and I'll go on like this. Now for start vertex and end vertex, we can have two integer fields. As you can see in both my definitions of edge, start vertex and end vertex are of type int now. And in each row of edge list, first and second field are filled with integer values. I have filled in appropriate values of indices. This definitely is a better design. And if you can see now, each row in edge list would cost us the same amount of memory. So overall space consumed in edge list would be proportional to number of edges, or in other words, space complexity here is big O of number of edges. Okay, so this is analysis of our memory usage. Overall space complexity of this design would be big O of number of vertices plus number of edges. Is this memory usage unreasonably high? Well, we cannot do a lot better than this if we want to store a graph in computer's memory. So we are all right in terms of memory usage. Now let's discuss time cost of operations. What do you think can be most frequently performed operations while working with graph? One of the most frequently performed operations while working with graph would be finding all nodes adjacent to a given node. That is, finding all nodes directly connected to a given node. What do you think would be time cost of finding all nodes directly connected to a given node? Well, we will have to scan the whole edge list. We will have to perform a linear search. We will have to go through all the entries in the list and see if the start or end node in the entry is our given node. For a directed graph, we would see if the start node in the entry is our given node or not, and for an undirected graph, we would see both the start as well as the end node. Running time would be proportional to number of edges, or in other words, time complexity of this operation would be big O of number of edges. Okay, now another frequently performed operation can be finding if two given nodes are connected or not. In this case also, we will have to perform a linear search on the edge list. In worst case, we will have to look at all the entries in the edge list. So worst case running time would be proportional to number of edges. So for this operation too, time complexity is big O of number of edges. Now let's try to see how good or bad this running time big O of number of edges is. If you remember this discussion from our previous lesson, in a simple graph, in a graph with no self loop or multi-edge, if number of vertices, that is the number of elements in set V, is equal to n, then maximum number of edges would be n into n minus 1 if the graph is directed. Each node will be connected to every other node. And of course, minimum number of edges can be 0. We can have a graph with no edge. Maximum number of edges would be n into n minus 1 by 2 if the graph is undirected. But all in all, if you can see, number of edges can go almost up to square of number of vertices. Number of edges can be of the order of square of number of vertices. Let's denote number of vertices here as small v. So number of edges can be of the order of v square. In a graph, typically any operation running in order of number of edges would be considered very costly. We try to keep things in order of number of vertices. When we are comparing the two running times, this is very obvious. Big O of v is a lot better than big O of v square. All in all, this vertex list and edge list kind of representation is not very efficient in terms of time cost of operations. We should think of some other efficient design. We should think of something better. We will talk about another possible way of storing and representing graph in next lesson. This is it for this lesson. Thanks for watching. So in our previous lesson, we discussed one possible way of storing and representing a graph in which we used two lists, one to store the vertices and another to store the edges. A record in vertex list here is name of a node, and a record in edge list is an object containing references to the two endpoints of an edge and also the weight of that edge, because this example graph that I'm showing you here is a weighted graph. We called this kind of representation edge list representation. But we realized that this kind of storage is not very efficient in terms of time cost of most frequently performed operations, like finding nodes adjacent to a given node or finding if two nodes are connected or not. To perform any of these operations, we need to scan the whole edge list. We need to perform a linear search on the edge list. So the time complexity is big O of number of edges. And we know that number of edges in a graph can be really large. In worst case, it can be close to square of number of vertices. In a graph, anything running in order of number of edges is considered very costly. We often want to keep the cost in order of number of vertices. So we should think of some other efficient design. We should think of something better than this. One more possible design is that we can store the edges in a two-dimensional array or matrix. We can have a two-dimensional matrix or array of size v cross v, where v is number of vertices. As you can see, I have drawn an 8 cross 8 array here because number of vertices in my example graph here is 8. Let's name this array A. Now if we want to store a graph that is unweighted, let's just remove the weights from this example graph here, and now our graph is unweighted. And if we have a value or index between 0 and v minus 1 for each vertex, which we have here, if we are storing the vertices in a vertex list, then we have an index between 0 and v minus 1 for each vertex. We can say that A is 0th node, B is 1th node, C is 2th node, and so on. We are picking up indices from the vertex list. Okay, so if the graph is unweighted and each vertex has an index between 0 and v minus 1, then in this matrix or 2D array, we can set ith row and jth column, that is aij, as 1 or boolean value true if there is an edge from I to j, 0 or false otherwise. if I have to fill this matrix for this example graph here, then I'll go vertex by vertex. Vertex 0 is connected to vertex 1, 2, and 3. Vertex 1 is connected to 0, 4, and 5. This is an undirected graph, so if we have an edge from 0 to 1, we also have an edge from 1 to 0. So 1th row and 0th column should also be set as 1. Now let's go to node 2. It's connected to 0 and 6. 3 is connected to 0 and 7. 4 is connected to 1 and 7. 5 once again is connected to 1 and 7. 6 is connected to 2 and 7. And 7 is connected to 3, 4, 5, and 6. All the remaining positions in this array should be set as 0. Notice that this matrix is symmetric. For an undirected graph, this matrix would be symmetric because Aij would be equal to Abi. We would have 2 positions filled for each edge. In fact, to see all the edges in the graph, we need to go through only one of these 2 halves. Now, this would not be true for a directed graph. Only one position will be filled for each edge, and we will have to go through the entire matrix to see all the edges. Okay, now this kind of representation of a graph in which edges or connections are stored in a matrix or 2D array is called adjacency matrix representation. This particular matrix that I have drawn here is an adjacency matrix. Now with this kind of storage or representation, what do you think would be the time cost of finding all nodes adjacent to a given node? Let's say given this vertex list and adjacency matrix, we want to find all nodes adjacent to node named F. If we are given name of a node, then we first need to know its index. And to know the index, we will have to scan the vertex list. There is no other way. Once we figure out the index, like for F, index is 5, then we can go to the row with that index in the adjacency matrix, and we can scan this complete row to find all the adjacent nodes. Scanning the vertex list to figure out the index in worst case will cost us time proportional to the number of vertices, because in worst case we may have to scan the whole list. And scanning a row in the adjacency matrix would once again cost us time proportional to number of vertices, because in a row we would have exactly v columns where v is number of vertices. So overall time cost of this operation is big O of v. Now most of the time while performing operations, we must pass indices to avoid scanning the vertex list all the time. If we know an index, we can figure out the name in constant time, because in an array we can access element at any index in constant time. But if we know a name and want to figure out the index, then it will cost us big O of v. We will have to scan the vertex list. We will have to perform a linear search on it. Okay, moving on. Now what would be the time cost of finding if 2 nodes are connected or not? Now once again the 2 nodes can be given to us as indices or names. If the nodes would be passed as indices, then we simply need to look at value in a particular row and particular column. We simply need to look at Aij for some values of I and j, and this will cost us constant time. You can look at value in any cell in a 2-dimensional array in constant time. So if indices are given, time complexity of this operation would be big O of 1, which simply means that we will take constant time. But if names are given, then we also need to do the scanning to figure out the indices, which will cost us big O of v. Overall time complexity would be big O of v. The constant time access would not mean anything. The scanning of vertex list all the time to figure out the indices can be avoided. We can use some extra memory to create a hash table with names and indices as key value pairs, and then the time cost of finding index from name would also be big O of 1, that is constant. Hash table is a data structure, and I have not talked about it in any of my lessons so far. If you do not know about hash table, just search online for a basic idea of it. Okay, so as you can see, with adjacency matrix representation, our time cost of some of the most frequently performed operations is in order of number of vertices and not in order of number of edges, which can be as high as square of number of vertices. Okay, now if we want to store a weighted graph in adjacency matrix representation, then Aij in the matrix can be set as weight of an edge. For non-existent edges, we can have a default value, like a really large or maximum possible integer value that is never expected to be an edge weight. I have just filled in infinity here to mean that. We can choose the default as infinity, minus infinity, or any other value that would never ever be a valid edge weight. Okay, now for further discussion, I'll come back to an unweighted graph. Adjacency matrix looks really good, so should we not use it always? Well, with this design we have improved on time, but we have gone really high on memory usage. Instead of using memory units exactly equal to number of edges, what we were doing with an edge list kind of storage, here we are using exactly v square units of memory. We are using big O of v square space. We are not just storing the information that these two nodes are connected, we are also storing not of it, that is these two nodes are not connected, which probably is redundant information. If a graph is dense, if the number of edges is really close to v square, then this is good. But if the graph is sparse, that is if number of edges is lot lesser than v square, then we are wasting a lot of memory in storing these zeros. Like for this example graph that I've drawn here, in the edge list we were consuming 10 units of memory. We had 10 rows consumed in the edge list. But here we are consuming 64 units. Most graphs with a really large number of vertices would not be very dense, would not have number of edges anywhere close to v square. Like for example, let's say we are modeling a social network like Facebook as a graph, such that a user in the network is a node and there is an undirected edge if two users are friends. Facebook has 1 billion users, but I'm showing only a few in my example graph here because I'm short of space. Let's just assume that we have 1 billion users in our network. So number of vertices in our graph is 10 to the power 9, which is 1 billion. Now, do you think number of connections in a social network can ever be close to square of number of users? That will mean everyone in the network is a friend of everyone else. A user of our social network will not be friend to all other billion users. We can safely assume that a user on an average would not have more than 1,000 friends. With this assumption, we would have 10 to the power 12 edges in our graph. Actually, this is an undirected graph, so we should do a divide by 2 here so that we do not count an edge twice. So if average number of friends is 1000, then total number of connections in my graph is 5 into 10 to the power 11. Now this is a lot lesser than square of number of vertices. So basically, if we would use an adjacency matrix for this kind of a graph, we would waste a hell lot of space. And moreover, even if we are not looking in relative terms, 10 to the power 18 units of memory, even in absolute sense, is a lot. 10 to the power 18 bytes would be about 1,000 petabytes. Now this really is a lot of space. This much data would never ever fit on one physical disk. 5 into 10 to the power 11 bytes, on the other hand, is just 0.5 terabytes. A typical personal computer these days would have this much of storage. So as you can see, for something like a large social graph, adjacency matrix representation is not very efficient. Adjacency matrix is good when a graph is dense. That is, when the number of edges is close to square of number of vertices. Or sometimes when total number of possible connections, that is V square, is so less that wasted space would not even matter. But most real-world graphs would be sparse and adjacency matrix would not be a good fit. Let's think about another example. Let's think about World Wide Web as a directed graph. If you can think of web pages as nodes in a graph and hyperlinks as directed edges, then a web page would not have link to all other web pages. And once again, number of web pages would be in order of millions. A web page would have link to only a few other web pages. So the graph would be sparse. Most real-world graphs would be sparse, and adjacency matrix, even though it's giving us good running time for most frequently performed operations, would not be a good fit because it's not very efficient in terms of space. So what should we do? Well, there's another representation that gives us similar or maybe even better running time than adjacency matrix and does not consume so much space. It's called adjacency list representation, and we will talk about it in our next lesson. This is it for this lesson. Thanks for watching. So in our previous lesson, we talked about adjacency matrix as a way to store and represent graph. And as we discussed and analyzed this data structure, we saw that it's very efficient in terms of time cost of operations. With this data structure, it costs big O of 1, that is constant time, to find if two nodes are connected or not. And it costs big O of V, where V is number of vertices, to find all nodes adjacent to a given node. But we also saw that adjacency matrix is not very efficient when it comes to space consumption. We consume space in order of square of number of vertices. In adjacency matrix representation, as you know, we store edges in a two-dimensional array or matrix of size V cross V, where V is number of vertices. In my example graph here, we have 8 vertices. That's why I have an 8 cross 8 matrix here. We are consuming 8 square, that is 64 units of space here. Now what's basically happening is that for each vertex, for each node, we have a row in this matrix where we are storing information about all its connections. This is the row for the 0th node, that is A. This is the row for the 1th node, that is B. This is for C, and we can go on like this. So each node has got a row, and a row is basically a one-dimensional array of size equal to number of vertices, that is V. And what exactly are we storing in a row? Let's just look at this first row in which we are storing connections of node A. This two-dimensional matrix or array that we have here is basically an array of one-dimensional arrays. So each row has to be a one-dimensional array. So how are we storing the connections of node A in these 8 cells in this one-dimensional array of size 8? A 0 in the 0th position means that there is no edge starting A and ending at 0th node, which again is A. An edge starting and ending at itself is called a self loop, and there is no self loop on A. A 1 in 1th position here means that there is an edge from A to 1th node, that is B. The way we are storing information here is that index or position in this one-dimensional array is being used to represent endpoint of an edge. For this complete row, for this complete one-dimensional array, start is always the same. It's always the 0th node, that is A. In general, in the adjacency matrix, row index represents the start point and column index represents the endpoint. Now here, when we are looking only at the first row, start is always A, and the indices 0, 1, 2 and so on are representing the endpoints. And the value at a particular index or position tells us whether we have an edge ending at that node or not. 1 here means that the edge exists. 0 would have meant that the edge does not exist. Now when we are storing information like this, if you can see, we are not just storing that B, C and D are connected to A, we are also storing the not of it. We are also storing the information that A, E, F, G and H are not connected to A. If we are storing what all nodes are connected, through that we can also deduce what all nodes are not connected. These zeros, in my opinion, are redundant information causing extra consumption of memory. Most real-world graphs are sparse, that is, number of connections is really small compared to total number of possible connections. So most often there would be too many zeros and very few ones. Think about it. Let's say we are trying to store connections in a social network like Facebook in an adjacency matrix, which would be the most impractical thing to do, in my opinion. But anyway, for the sake of argument, let's say we are trying to do it. Just to store connections of one user, I would have a row or one-dimensional matrix of size 10 to the power 9. On an average, in a social network, you would not have more than 1000 friends. If I have 1000 friends, then in the row used to store my connections, I would only have 1000 ones, and rest, that is 10 to the power 9 minus 1000, would be zeros. And I'm not trying to force you to agree, but just like me, if you also think that these zeros are storing redundant information and are extra consumption of memory, then even if we are storing these ones and zeros in just 1 byte as Boolean values, these many zeros here is almost 1 gigabyte of memory. Ones are just 1 kilobyte. So given this problem, let's try to do something different here. Let's just try to keep the information that these nodes are connected and get rid of the information that these nodes are not connected, because it can be inferred, it can be deduced. And there are a couple of ways in which we can do this. Here, to store connections of A, instead of using an array such that index represents endpoint of an edge and value at that particular index represents whether we have an edge ending there or not, we can simply keep a list of all the nodes to which we are connected. This is the list or set of nodes to which A is connected. We can represent this list either using the indices or using the actual names for the nodes. Let's just use indices because names can be long and may consume more memory. You can always look at the vertex list and find out the name in constant time. Now in a machine we can store this set of nodes, which basically is a set of integers, in something as simple as an array. And this array, as you can see, is a different arrangement from our previous array. In our earlier arrangement, index was representing index of a node in the graph, and value was representing whether there was a connection to that node or not. Here, index does not represent anything, and the values are the actual indices of the nodes to which we are connected. Now, instead of using an array here to store this set of integers, we can also use a linked list. And why just array or linked list? I would argue that we can also use a tree here. In fact, a binary search tree is a good way to store a set of values. There are ways to keep a binary search tree balanced, and if you always keep a binary search tree balanced, you can perform search, insertion, and deletion, all three operations, in order of log of number of nodes. We will discuss cost of operations for any of these possible ways in some time. Right now, all I want to say is that there are a bunch of ways in which we can store connections of a node. For our example graph that we started with, instead of an adjacency matrix, we can try to do something like this. We are still storing the same information. We are still saying that 0th node is connected to 1th, 2th, and 3th node. 1th node is connected to 0th, 4th, and 5th node. 2th node is connected to 0th and 6th node, and so on. But we are consuming a lot less memory here. Programmatically, this adjacency matrix here is just a two-dimensional array of size 8 cross 8. So we are consuming 64 units of space in total. But this structure in write does not have all the rows of same size. How do you think we can create such a structure programmatically? Well, it depends. In C or C++, if you understand pointers, then we can create an array of pointers of size 8, and each pointer can point to a one-dimensional array of different size. 0th pointer can point to an array of size 3 because 0th node has 3 connections and we need an array of size 3. 1th pointer can point to an array of size 3 because 1th node also has 3 connections. 2th node, however, has only 2 connections. So 2th pointer should point to an array of size 2. And we can go on like this. The 7th node has 4 connections. So 7th pointer should point to an array of size 4. If you do not understand any of this pointer thing that I'm doing right now, you can refer to MyCodeSchool's lesson titled Pointers and Arrays, the link to which you can find in the description of this video. But think about it. The basic idea is that each row can be a one-dimensional array of different size. And you can implement this with whatever tools you have in your favorite programming language. Now let's quickly see what are the pros and cons of this structure in the right in comparison to the matrix in the left. We are definitely consuming less memory with the structure in right. With adjacency matrix, our space consumption is proportional to square of number of vertices. While with this second structure, space consumption is proportional to number of edges. And we know that most real-world graphs are sparse. That is, the number of edges is really small in comparison to square of number of vertices. Square of number of vertices is basically total number of possible edges. And for us to reach this number, every node should be connected to every other node. In most graphs, a node is connected to few other nodes and not all other nodes. In this second structure, we are avoiding this typical problem of too much space consumption in an adjacency matrix by only keeping the ones and getting rid of the redundant zeros. Here, for an undirected graph like this one, we would consume exactly 2 into number of edges units of memory. And for a directed graph, we would consume exactly E, that is number of edges units of memory. But all in all, space consumption will be proportional to number of edges. Or in other words, space complexity would be big O of E. So the second structure is definitely better in terms of space consumption. But let's now also try to compare these two structures for time cost of operations. What do you think would be the time cost of finding if two nodes are connected or not? We know that it's constant time or big O of 1 for an adjacency matrix, because if we know the start and end point, we know the cell in which to look for 0 or 1. But in the second structure, we cannot do this. We will have to scan through a row. So if I ask you something like, can you tell me if there is a connection from node 0 to 7? Then you will have to scan this 0th row. You will have to perform a linear search on this 0th row to find 7. Right now, all the rows in this structure are sorted. You can argue that I can keep all the rows sorted and then I can perform a binary search, which would be a lot less costlier. That's fine, but if you just perform a linear search, then in worst case we can have exactly V, that is number of vertices, cells in a row. So if we perform a linear search, in worst case we will take time proportional to number of vertices. And of course the time cost would be big O of log V if we would perform a binary search. Logarithmic runtimes are really good, but to get this here, we always need to keep our rows sorted. Keeping an array always sorted is costly in other ways, and I'll come back to it later. For now, let's just say that this would cost us big O of V. Now, what do you think would be the time cost of finding all nodes adjacent to a given node? That is, finding all neighbors of a node. Well, even in case of adjacency matrix, we now have to scan a complete row. So it would be big O of V for the matrix as well as this second structure here. Because here also, in worst case, we can have V cells in a row, equivalent to having all ones in a row in an adjacency matrix. When we try to see the time cost of an operation, we mostly analyze the worst case. So for this operation, we are big O of V for both. So this is the picture that we are getting. Looks like we are saving some space with this second structure, but we are not saving much on time. Well, I would still argue that it's not true. When we analyze time complexity, we mostly analyze it for the worst case. But what if we already know that we are not going to hit the worst case? If we can go back to our previous assumption that we are dealing with a sparse graph, that we are dealing with a graph in which a node would be connected to few other nodes and not all other nodes, then the second structure will definitely save us time. Things would look better once again if we would analyze them in context of a social network. I'll set some assumptions. Let's say we have 1 billion users in our social network, and the maximum number of friends that anybody has is 10,000. And let's also assume computational power of our machine. Let's say our machine or system can scan or read 10 to the power 6 cells in a second. And this is a reasonable assumption because machines often execute a couple of millions instructions per second. Now, what would be the actual cost of finding all nodes adjacent to a given node in adjacency matrix? Well, we will have to scan a complete row in the matrix. That would be 10 to the power 9 cells, because in a matrix we would always have cells equal to number of vertices. And if we would divide this by 1,000,000, we would get the time in seconds. To scan a row of 10 to the power 9 cells, we would take 1000 seconds, which is also 16.66 minutes. This is unreasonably high. But with the second structure, maximum number of cells in a row would be 10,000, because the number of cells would exactly be equal to number of connections. And this is the maximum number of friends or connections a person in the network has. So here we would take 10 to the power 4 upon 10 to the power 6, that is 10 to the power minus 2 seconds, which is equal to 10 milliseconds. 10 milliseconds is not unreasonable. Now let's try to deduce the cost for the second operation, finding if two nodes are connected or not. In case of adjacency matrix, we would know exactly what cell to read. We would know the memory location of that specific cell, and reading that one cell would cost us 1 upon 10 to the power 6 seconds, which is 1 microsecond. In the second structure, we would not know the exact cell. We will have to scan a row. So once again, maximum time taken would be 10 milliseconds, just like finding adjacent nodes. So now, given this analysis, if you would have to design a social network, what structure would you choose? No-brainer, isn't it? Machine cannot make a user wait for 16 minutes. Would you ever use such a system? Milliseconds is fine, but minutes, it's just too much. So now we know that for most real-world graphs, this second structure is better because it saves us space as well as time. Remember, I'm saying most and not all, because for this logic to be true, for my reasoning to be valid, graph has to be sparse. Number of edges has to be significantly lesser than square of number of vertices. So now, having analyzed space consumption and time cost of at least two most frequently performed operations, looks like this second structure would be better for most graphs. Well, there can be a bunch of operations in a graph, and we should account for all kind of operations. So before making up my mind, I would analyze cost of few more operations. What if after storing this example graph in computer's memory in any of these structures, we decide to add a new edge? Let's say we got a new connection in the graph from A to G. Then how do you think we can store this new information, this new edge, in both these structures? The idea here is to assess that once the structures are created in computer's memory, how would we do if the graph changes? How would we do if a node or edge is inserted or deleted? If a new edge is inserted in case of an adjacency matrix, we just need to go to a specific cell and flip the 0 at that cell to 1. In this case, we would go to 0th row and 6th column and overwrite it with value 1. And if it was a deletion, then we would go to a specific cell and make the 1 0. Now how about this second structure? How would you do it here? We need to add a 6 in the first row. And if you have followed this series on data structures, then you know that it's not possible to dynamically increase size of an existing array. This would not be so straightforward. We will have to create a new array of size 4 for the 0th row. Then we will have to copy content of the old array, write the new value, and then wipe off the old one from the memory. It's tricky implementing a dynamic or changing list using arrays. This creation of new array and copying of old data is costly. And this is the precise reason why we often use another data structure to store dynamic or changing lists. And this another data structure is linked list. So why not use a linked list? Why can't each row be a linked list? Something like this. Logically, we still have a list here, but concrete implementation wise, we are no more using an array that we need to change dynamically. We are using a linked list. It's a lot easier to do insertions and deletions in a linked list. Now, programmatically, to create this kind of structure in computer's memory, we need to create a linked list for each node to store its neighbors. So what we can do is we can create an array of pointers, just like what we had done when we were using arrays. The only difference would be that this time each of these pointers would point to head of a linked list. That would be a node. I have defined node of a linked list here. Node of a linked list would have two fields, one to store data and another to store address of the next node. A0 would be a pointer to head or first node of linked list for A. A1 would be a pointer to head of linked list for B. And we will go on like A2 for C, A3 for D, and so on. Actually, I have drawn the linked lists here in the left, but I have not drawn the array of pointers. Let's say this is my array of pointers. Now A0 here, this one, is a pointer to node, and it points to the head of linked list containing the neighbors of A. Let's assume that head of linked list for A has address 400. So in A0 we would have 400. It's really important to understand what is what here in this structure. This one, A0, is a pointer to node, and all a pointer does is store an address or reference. This one is a node, and it has two fields, one to store data and another a pointer to node to store the address of next node. Let's assume that the address of next node in this first linked list is 450. Then we should have 450 here. And if the next one is at, let's say, 500, then we should have 500 in address part of the second node. The address in last one would be 0 or null. Now this kind of structure in which we store information about neighbors of a node in a linked list is what we typically call an adjacency list. What I have here is an adjacency list for an undirected, unweighted graph. To store a weighted graph in an adjacency list, I would have one more field in node to store weight. I have written some random weights next to the edges in this graph, and to store this extra information I have added one extra field in node, both in logical structure and the code. Alright, now finally with this particular structure that we are calling adjacency list, we should be fine with space consumption. Space consumed will be proportional to number of edges and not to square of number of vertices. Most graphs are sparse and number of edges in most cases is significantly lesser than square of number of vertices. Ideally for space complexity I should say big O of number of edges plus number of vertices, because storing vertices will also consume some memory. But if we can assume that number of vertices will be significantly lesser in comparison to number of edges, then we can simply say big O of number of edges. But it's always good if we do the counting right. Now for time cost of operations, the argument that we were earlier making using a sparse graph like social network is still true. Adjacency list would overall be better than adjacency matrix. Finally, let's come back to the question, how flexible are we with this structure if we need to add a new connection or delete an existing connection? And is there any way we can improve upon it? Well, I'll leave this for you to think, but I'll give you a hint. What if instead of using a linked list to store information about all the neighbors, we use a binary search tree? Do you think we would do better for some of these operations? I think we would do better because the time cost for searching, inserting, and deleting a neighbor would reduce. With this thought, I'll sign off. This is it for this lesson. Thanks for watching.